So hello everybody, welcome to POPL, and it's clear that people are just going to continue to walk in and we're just going to get going so that we start on time. I'm Philippa Gartner, I'm chair of the POPL'24 this year. Oops, what's... Just a few announcements. So COVID's okay in London. You know, we're in the winter season, so it's bubbling a bit. My partner just before Christmas went to a conference in California, got COVID. I didn't have it, but the rest of my family had COVID over Christmas. So please just take a little bit of care. There are hand sanitizers around. If you spot one, just use it because why not? And let's see if we can keep it down. Lunches have been entertaining. So what's happening? There's lunches on the first floor and the third floor. Both rooms are gorgeous. And please, if you come from this land, go up to the first floor. And if you're on the second floor, because that's where the parallel sessions are happening, please go to the third floor. And of course, you can mix and match. But if you find yourself out of food, just go to the other place because there's more than enough food. I just want to mention the DEI lunches. So they're up there, and 2 receptions. In particular, for the reception, the first reception, be a little careful, because we have drinks paid for between 6:15 and 7:15. So make sure you have your drinks in that time. After that, you can still get drinks, and they're still paid for, but at some point we reach a ceiling. So we don't reach a ceiling in that first hour. So be a little bit careful. Don't do it 2 minutes after 7:15. That would be really annoying. And we are doing something slightly different this time. Normally we have women's lunches, but because of Jane Street, we could go more ambitious. And we're doing a DEI for everyone cocktail reception. And so basically, there was a little bit of numbers going down with the women's lunches, and we wanted to try something else. So this is just an experiment. Let's see what happens. This second one is a freebie. So you can still come if you haven't signed up. These are our fabulous industry people, the most fabulous ones being at the top. I want to say something about the organizing committee. So I've been in this environment for decades. I started off in quite small conferences, and then my subject got into this world of POPL and the bigger conferences. And so I didn't know how much work the organizing committee did, because I was organizing in smaller meetings. These guys have been absolutely awesome, and they're the unsung heroes. These ones and these ones. And I would particularly like to introduce Naringa. Many of you know her already. Please stand up, Naringa. So Naringa does the 4 main conferences associated with SIGPlan. So we're getting to know her very well now, and I do know what it means, said affectionately, to pull a Naringa. There's definitely that going on sometimes, and it's delightful. But I also want to emphasize some people here. So Sasha is my PhD student, and also a co-chair of the student volunteers. He has a friend called Manon, who is an artist, She didn't have a professional photograph, so she didn't want to put a photograph up. And so all the signage and what have you around has been done by this artist. And of course, she's professional, we paid her, but these two guys worked very hard. They wanted to do something special for us. And Nat, also a PhD student of mine, saved the day regarding screens. And he worked many, many hours sorting out a problem. So we have, this is the screens for today. We've got the absolute wonderful rotating London Eye, that's Nat. And this POPL logo, the Manon, the artist, is a specialist in font design. And she's taken a modern font that's come right from Victorian times, where it was first developed in the London foundries, and then moved it to now. And that's the T-shirt design. Here's our fabulous PC chair, Derek, and his able assistants. Most of you know them very well already. And, haha, Steve will be the next POPL chair, and he might not know what's going to hit him. But Derek said to me, this is a great location. It's just by the Whiskey Exchange. That was just before the last POPL. Halfway through last year, he said, I've been to the Whiskey Exchange, and I managed to get into IET and get shown round. So that shows the enthusiasm of Derek. And what people might not know is the interference of Derek. He has been absolutely awesome in terms of just getting stuck in and helping with what's going on because of his huge enthusiasm. So absolutely, this is not in any sense, this organization is not, Derek's been helping lots. So what I'm going to do for Derek and for the organizing committee is a tiny, stupid little present of here's a London Eye that's rotating that they'll be able to have sitting on their desks. So if you see it, go, I know what that is. So let's POPL begin. I will describe what was going on there. It's not there for some reason. What should be happening is 9 bongs of the, I'm late, yeah. Here's 9 bongs of Big Ben. Here's the beginning of POPL, and that scene is something that you can see from the roof terrace of this institution. You will be able to go up lunchtime, first break in the afternoon, and at the receptions. So thank you. Welcome to POPL, and Derek, please take over.
All right, great. Okay, that's better. Hi, everyone. I'm Derek Dreyer, program chair, and it's my great pleasure to introduce our first keynote speaker, Azadeh Ferzan. We're running a little late, so I'm going to keep this short and sweet. Azadeh received her PhD in computer science from UIUC. She did a postdoc at CMU, and then has been a professor at University of Toronto since 2008. Yeah, you can get set up here. Oh, I'll try talking to this. She has been a prominent, hopefully, concurrent interference. She's been a prominent member of our community for many years, serving as co-chair of CAV in 2016, program chair of POPL in 2021, and also as a member of the SIGPlan Executive Committee. She's done a lot of exciting work in the areas of concurrency, program analysis, and synthesis. And today she's going to tell us about a new perspective on commutativity and verification. Please join me in welcoming Azadeh Ferzan.
Thank you. Can everyone hear me okay in the room? Fantastic. Thanks for the introduction, Derek, and for the invitation, the opportunity to share our work here today. So today I want to talk about commutativity in verification. So let me jump into commutativity right away. You see two atomic actions on, let's say, a global counter, an increment and a decrement. And we say these soundly commute, and by that we mean that if they appear in any program run, their respective order of execution is not going to change the outcome of the run. Right? So I'm keeping everything high level here. So here is an example of a run that they may appear in. We're ignoring everything else. And I can basically take two of these, commute them, make another kind of swap somewhere else, make another swap somewhere else. And the idea is that no matter how many of these I do, the run that I will end up with is equivalent to the original because every swap did not change the outcome of the run. This simple concept is basically kind of telling us that you have a commutativity relation that is sound in this sense. You have a definition of an equivalence on a set of runs that you can use. And this has basically appeared in many, many places, has had a lot of impact in programming languages research. So I'm going to mention a few for historical context before I get on with my business today. Probably one of the earliest ones has been due to a paper of Lipton in which he used commutativity to make big atomic blocks of code out of small parts and then argue that it's sound to do local reasoning in these big blocks. Now, this paper this idea has been consequently used in a lot of kind of proofs about, papers about proofs of programs, but also other surprising places like type and effect systems, and many more. Another area that the ideas of commutativity reasoning has been very prevalent has been in model checking. In model checking, commutativity reasoning is used to basically curb the time and space of verification. The idea being that if you're looking for a counterexample to a property and you have already checked a run, you can forego the checking of all the commutativity equivalent runs. All of these ideas appear on the banner of partial order reduction methods and have been kind of appearing in thousands of papers, really. Last, for something a little different, it has been used in runtime monitoring and testing of concurrent programs. There, the flavor is a little different. The idea is that if you wanted to just randomly test a concurrent program, it's very unlikely that you see a bad behavior like a data race from a few random samples. So you want to try to extend your testing beyond the observed behavior, and commutativity reasoning is exactly the thing that is used to infer a lot of unobserved behaviors as behaviors of the program and test the whole bunch so that you kind of basically have a higher likelihood of hitting a problem like a data race. Now, the common denominator between the first two methods is this simple idea. If I have checked something or proved something, I can basically skip checking or proving all the other equivalent runs to it. And this concept has given rise to the concept of program reductions. So what is a reduction of a program? You see a simple concurrent program in which the increment and decrement that I showed you appear. If I kind of extend my sound commutativity beyond the counters to all the other actions of the program, which are also commuting because they're local actions, I can argue that that program is behaviorally equivalent to this program. Now, to be more precise, every behavior of the concurrent program, for every behavior of the concurrent program, I have a behavior in the sequential program that is commutativity equivalent to it. And this is exactly what a reduction means in the context of this talk, and as it was introduced by Lipton originally. So that one, of course, is not the only one. You would immediately observe that I can swap the order of, I'm stuck. You can swap the order of, I think the presentation on the other side is stuck. My slides are going ahead. So what is it that we should do? Unplug and plug again. you didn't even feel my unplug. Should I do it one more time or wait for it to come up? Let's see. So that one is not the only one. And if we kind of look at it quickly, we see that, OK, it's OK to reverse the order of the threads. That is also a reduction. But I can play more games with this. I can basically argue that if I execute the two threads in lockstep, for the same reasons, I will get another reduction of the program. And then I can take this idea even further and execute the threads in different paces at lockstep. And you will quickly see that this simple program basically has an infinite space of possibilities of program reductions, which are all sound to verify in place of the original program. Now, let's look at this space and see what sort of opportunity it presents for verification. So the first two sequential programs, we can immediately observe they have quadratically fewer control locations. So if we give them a proof, this proof is going to have quadratically fewer assertions, quadratically fewer verification conditions to check. So we can say that these have a simpler proof in some sense of the word, which is precise, which means I have to spend less time and space in the verification of that proof. But then if I kind of inspect them a little more carefully, I will see that they all share a problem in some sense. All three programs require an annotation like the one that you see on the screen. I need to basically capture the effect of the loop, which has to be captured using a nonlinear assertion. And solvers don't like nonlinearity, which means that if I were in a fully automated setting and I wanted to try to get a solver to give me those annotations and or verify their verification conditions, I would get stuck, even though the programs are super simple and super trivial. On the other hand, if I look at the lockstep reduction, I would immediately see that, yes, same as before, quadratically fewer control locations, so a simpler proof in that sense. But at the same time, this program can be proved correct using a very simple loop invariant. So this one actually can be proven using fully automated techniques. And the proof is, in some sense, simpler in a qualitative sense beyond the quantity issues. So this kind of simple observation with this super simple program is really the foundation of the view of the talk that I want to give to you today, that this presents an opportunity. I can really think about any sort of algorithmic verification scheme as something that tries to actively search for a proof. And while it's trying to search for a proof, it talks to a logical reasoning engine. But logical reasoning engines come with limitations. So the program and the property of choice might force the algorithm to hit an undecidability or a high complexity barrier that is kind of intrinsic to the logical reasoning engine. And if that happens, the algorithm is stuck. There's really nothing that it can do to unstuck itself. But in some cases, like the example that I showed you, there is an opportunity. We can try to say that we're not going to give up. We are going to give up on verifying the program, but we are going to basically search for an alternative program that we can actually prove correct instead. So it's kind of like a paradigm shift in which you view the algorithmic verification scheme as not just a proof search, but a search for a proof and a program concurrently. A program and a proof for it that can be basically replacing the original verification goal soundly. Now, why am I insisting on an automated search for a program? Because most of these reductions are actually quite ugly. When I showed you this one, waved my hands and said, this is a lockstep reduction, it's sound to verify in the place of the original program, I was effectively lying to you. It's not this, it's this that is the sound lockstep reduction of the program. I need to account for all the behaviors in which one loop may overtake the other one in the count of the number of executions, except later on when I have access to logical reasoning, I would prove all of those infeasible. But commutativity reasoning cannot let me prune those parts out. So this is the program, this is the reduction that we will end up verifying. but we still can verify it the way that I mentioned it. So my view is you should not force people to look at this ugliness. You should let algorithms do that. And the idea, once we can actually pull it off, has broad applicability. I'm hoping the tiny example has already convinced you that in concurrent and distributed programs, because there is a lot of redundant behavior due to the interleaving nature of things, you have opportunity to actually kind of look for these alternatives. But also another maybe surprising thing to the audience is the area of relational verification and a specific sub-area of it, hyper-property verification, which is coincidentally where we actually started from in this work. There, because self-composition is used as a proof method, you kind of have exactly the same theme. And for people who know this area, you can kind of think of a program alignment that is used to prove in a self-composition framework as an equivalent of a reduction. So anything we invent that would be useful for the things up there will be useful for the things down here. So same methodology, same solution. Now, I'm hoping that this tiny introduction convinced you that this is a worthwhile goal. So let's try to switch kind of perspective to see, okay, can we actually pull this off? Can we make the new paradigm happen? To do this properly in this talk, I need to lay a foundation. I need to pick an algorithmic verification setup and basically present the ideas to you there. But I want to say something a little bit more, that this choice of mine is not arbitrary. I'm actively choosing what we call operational proofs, and because I fundamentally believe that this is the framework that makes it easier compared to all the others to make this happen. Now, operational proofs are proofs of programs that take an operational view of the program. So we say that the program is correct if we have proved all of its behaviors correct. Or you can kind of think about the simple proof rule in which we say that there is a concept of a proof, which is a set of behaviors that we construct as we go, and we know they're correct. And the correctness of program is basically through the subsumption of the program behaviors by the correct by construction proof behaviors. Now, of course, for this to actually algorithmically happen, I need a few ingredients. I need to be able to represent the proof, represent the program, and have a decidable subsumption check. Only then I can say this proof rule is algorithmically realizable. Now, we have done a lot of research on this kind of framework, which is beyond the topic of this talk. You can check it out if you want. For the purpose of today, I can just very quickly give you a high-level idea. So the algorithm works like this. You start with an empty proof. You kind of ask, does this subsume the program behaviors? Of course not. You get a counterexample whenever the answer is no. Now, you have to check whether this is a real counterexample or not. If it's a real counterexample, you have found a violation, a witness to the violation of the property, you're done. If not, you can actually use your logical reasoning engine now to prove the counterexample correct. And now that you have a proof of counterexample, some magic happens in this box that I'm waving my hands and not explaining, in which you kind of update your proof based on the proof of this behavior. The idea being that kind of your proof now includes the proof of this behavior and all the other behaviors that admit a similar proof. And then I can go back and ask, does it subsume the program now? Whenever the answer is yes, I'm done. Whenever the answer is no, I will go around this loop and basically grow that proof object until I'm done. Now, why am I insisting on liking this framework better than some others? The reason is that the proof, in some sense, grows separately from the program. In a classic setup, I know what program I'm proving from the beginning, so I have options. In this setup, I don't know what program I'm proving. I'm looking for a program to prove, which means I don't have access to the program. And a kind of classic, like axiomatic method that needs to do induction on the structure of this program, which is unknown to me while I'm going around this loop, I at least don't know how to start there, right? But here, I can sort of keep the two separate, make progress, and hope that eventually the two sides will meet and converge. So this is really the reason I like this framework. Now, how do we incorporate commutativity into such a framework? If you understood the idea, a very trivial thing would immediately occur to you. So you say that, OK, you had this proof rule. you're using this framework, why don't you change your subsumption test to a test in which you would every time take your proof object and blow it up to commutativity. Now, whatever you have proved, you have all these other behaviors that are also correct up to commutativity, and you have effectively taken advantage of commutativity reasoning. And it would have been fantastic if I actually could do this. The problem is I can't. Even in the simplest cases, the simplest models for the program and the proof, which are regular languages, this subsumption test becomes undecidable, which means the proof rule is valid, but I cannot have an algorithmic realization of this proof rule. So what is the way out? The way out is exactly the idea of reductions that I showed you as examples basically when we started this talk. So we can say that we can rely on this classic result, which is a theorem that says there are certain classes of reductions of the program that are nicely representable, and therefore we can check the subsumption of their behavior into the proof. So what are these class of reductions? They're called lexicographic reductions, in which you use a simple ordering on the program statements. That simple ordering on the program statements induces an ordering on the program runs. Now you have an ordering on the program runs, and what you do is you say that my representative picker from every equivalence class of the program is going to pick the least element. And this is, canonical, we understand it, but the beauty of the theorem is that it says that now that object that picks these representatives is nicely representable, it's regular. And as such, you can actually test the subsumption like you would before with any normal program, okay? Now, as an example, if I take the concurrent program that I showed you at the beginning, and I say that all the left thread statements are before in order than the right thread statements, and you compute such a reduction, you will get exactly the sequential program, that the first thread starts and then the second thread finishes. If I swap the order, I will get the other concurrent program, and I can play with this order to get all these other programs. So the nice thing about this family of reductions is they kind of select a unique representative from each class, so they're sound and optimal, and more importantly, they're parametric. You can play with the order and get different reductions as a result. So now we can go back to our original proof rule and replace the program with a reduction of it. Now, this reduction would be constructible. That subsumption check would be decidable. So this proof rule can replace my original proof rule. Now, of course, it shouldn't be kind of lost on anyone in the audience that I have not yet delivered on the promise of searching for a reduction. This is just one reduction. But interestingly, just having access to this, let's say, weaker than the ultimate goal proof rule already has a lot of impact. So if you kind of have a portfolio tool in which you pre-select a handful of reduction in advance, so independent of the instances, and over 1,200 standard benchmarks from verification conditions, you compare handful of reductions with no reductions at all, you do significantly better. You can basically solve 50 more benchmarks, and the entire kind of suite of benchmarks can be solved in half of the time. So a lot of power even in this kind of halfway there step. But let's get back to what we wanted to achieve originally. We have an undecidable but ideal rule on the left. We have a decidable but non-ideal one on the right. So we want a middle ground. And the observation is that the one on the left effectively is saying there is a reduction in the universe of all possible reductions, which are typically infinite because we have undecidability. And I'm looking for that golem one, but I cannot because this is undecidable. So how about the middle ground be that we pre-select a set of reductions, which is not everything, but it's an expressive set, and deliver between the two. And hopefully, whenever the original set is infinite, this set of reductions is going to actually be infinite as well. So we basically hit infinitely many reductions inside the possibility of infinitely many reductions originally. And in this set, we are saying we want to check whether one of these reductions is actually subsumed by the proof. So let's go back to our operational loop. And so the subsumption check is going to be replaced by this. But naturally, to make all of this happen, I need to answer a few questions. I need an algorithmic check for this. I have to show that this is actually decidable. But that's not all. Once that subsumption check fails, I need a counterexample. And the question here would be, this counterexample is witnessing the delta between the proof and which one of these infinitely many reductions. And then the relevant question is, okay, that counterexample, when I go back and construct a proof for and advance my proof, is advancing the proof against which one of these infinitely many reductions? If I pick and choose here, I am not doing any better than the kind of halfway rule that was just choosing a reduction anyway, right? So if I answer all of these questions successfully, I have made this whole thing work. And the key is to kind of the selection of a suitable set of reductions that will make all of this come together. So what is this set of reductions? We basically borrow the idea of the classic theorem that I showed you and sort of expand it. The classic theorem was using a flat order on the program statements. We say, how about we actually take what I call contextual orders on program statements. So now you let the program statements to be ordered differently depending the context in the execution that they appear in. So you have, at the end of a different history, a different ordering of the program statements. So now, as opposed to having finitely many flat orderings on the program statements, I have infinitely many contextual orders that I can use in my program. Then we can kind of make this observation that a contextual order like this, in the same exact way that a flat order would induce a lexicographic order on the program runs, which means that now, again, I have a selector to pick a representative from an equivalence class of executions from the program, which means that that selector is going to give me a program reduction. So like before. The difference now is because I have infinitely many, the difference is now because I have infinitely many contextual orders, I will have infinitely many lexicographic orders, and other than some pathological cases, they will give me, in the typical cases with normal programs, infinitely many choices of program reductions. Okay? So this was just the definition of a set of reductions that are suitable. Now let's switch our view to the representation of them, but to make sure that everyone is with me, I will show you a quick example for all of this to kind of set it. So here is a tiny program, just graphically. 2 threads executing blue and purple in parallel, some arbitrary numbers. Let's say for whatever reason, I'm interested in this magic reduction, 2 blues against the purple. Can lexicographic reductions give me this exact reduction? The answer is yes. I can pick a contextual order like this. I can say that at the beginning, I will prefer blue over purple. Whenever the last thing that was executed was purple, I will prefer blue over purple. Whenever the last 2 things that were executed were purple and blue, I will still prefer blue over purple. And only when the last 2 things were blue, I will switch my preference and prefer purple over blue. And you can already see the theme. This is not unlike kind of a priority scheduler, right? But contextual. And this is going to basically, from that program, with the assumption of commutativity of blue and purple, give me exactly the reduction that you see. Now, of course, if you have been paying attention to me, you should say, wait a minute, that reduction doesn't look okay. And you would be right. The actual ugly reduction looks like that. But the example that I showed you is not going to be any different. All the junk on the side are the cases that you have no option in executing things. So whatever ordering you are imposing is not going to matter. You have only one thing to execute, and you will execute that thing. Okay? Now, the class of lexicographic reductions are neat, but the true purpose of them is that we can actually represent them effectively. There is a finite representation for the infinitely many lexicographic reduction. And this is achieved through 3 automata. So there is a simplest class of 3 automata, we call them looping 3 automata, that can represent precisely all the lexicographic reductions of the program up to all contextual orders. And you can kind of think about it as every tree that is recognized by this automaton would correspond to 1 reduction. So the moment we have representation of the reductions as a tree automata, we can rely back on classic automata theory in some sense. Actually, this is a little non-classic. It's a theorem that wasn't in the literature, but we proved, but similar. And we can show that it's decidable now to check whether one of these reductions, one of these trees, is subsumed by a proof, which is a regular language. And more importantly, this can be done in linear time. This problem basically reduces to, the Horn satisfiability problem. And as such, you can do it in linear time. So now we have answered the question, do we have a decision procedure for this? What about the other two questions? So whenever the subsumption passes, we're good. When it fails, what then? And the beauty of the looping tree automata and this class of reductions is, without you putting any more effort, you will get this other theorem for free that says that whenever the subsumption test fails, there are finitely many counterexamples that witness the difference between the proof and the reductions. So you can basically take these finitely many counterexamples, you can test them, you can give them proofs, you can update your proof based on them, and you know that you have made a non-zero progress across the board, across all the many infinitely reductions. Which means that the new algorithm, the new operational loop, basically has exactly the same progress property that the classical one had when we were just trying to prove one program and coming up with a proof for that one single program. All right, so this sort of ends the first part of my talk, in which hopefully I have convinced you that we can deliver on the promise of combining the two searches together algorithmically. Search for a reduction and for a proof of a reduction, all in one unified kind of framework. Just so that I show you that this does make a difference. If I compare the other tool that I showed you earlier, that hand selects a few reductions, with a tool that actually searches for reductions over a category of really challenging benchmarks. These are the ones that you cannot prove without reductions. The one that searches for reductions does almost twice as better. Okay? So it's worthwhile to actually go through this trouble. Now, I have answered this question. We can automate this. I want to briefly, in the second part of the talk, turn my attention back to the first question, but a refinement of it in some sense. So this seems like a lot of effort. Is there really out there enough commutativity to exploit to make this effort worthwhile? And I can answer this question starting by using a few examples to motivate a few ideas. So first, let's turn our attention to the context of message passing concurrent programs or distributed programs. I think it's clear to everyone in the audience that when you have a send and a receive on a same channel in such programs, the send would actually commute to the left of the receive, but the receive would not commute to the left of the send, because the receive could be blocking. We don't have the order of execution doesn't change the outcome anymore. This motivates the idea of an asymmetric commutativity relation, which we call semi-commutativity. So if, I should be able to deal with this as well, otherwise I can't do anything here. But if I'm super keen to commute the receive to the left of the send, I can do that. I can say that, okay, not everywhere I can do this, but in the context in which, in the history of the execution, I have more sends than the receive would actually commute to the left of the send. And this motivates the idea of contextual commutativity, which is commutativity that doesn't globally hold, but holds in certain contexts, and we want to still be able to exploit it in those contexts in which it holds. And finally, even a simpler kind of example, if I have two updates to a global variable, they don't commute under any of the notions that I showed you before. No context, no semi, nothing. But I can kind of ask myself, does it really matter that x is 5 or 7 at the end of the disk? What if for the particular property that I'm trying to prove about the program, it suffices that I show that x is positive at the end of this? Then I can change my view of those statements, to this, and now these two statements would just commute, without any problem. And this motivates the concept of abstract commutativity, taking, dropping the precise meaning of the statement and taking an abstract view of them. So if one is serious about exploiting commutativity out there, one cannot really leave these three options on the table. One should have a way of trying to exploit this. And I want to just very briefly tell you a little bit about what we know about either of these options. Okay? So semi-commutativity is rather easy. I'm not going to really get into it, other than telling you that more or less it can be done the same way that you can deal with a symmetric commutativity relation. The only thing that you will lose in this game is that you have to give up the optimality of your reductions. Now your reductions may have a little bit of junk in them. And this, for the people who know and understand them, effectively gives you the same kind of power of reasoning like Lipton left and right movers that are kind of semi-commutativity type of arguments. Contextual commutativity is far more interesting. In contextual commutativity, I want to be able to say A and B commute in one context, but not in the other context. And the key to make this happen in the framework that I've already presented to you is to choose the right view of a context. And the right view of a context is to take the history as a context. I'm kind of contrasting this against, for example, taking the state as a context. Okay? So I would say that at the end of one history, certain histories things commute. At the end of certain other histories, things don't commute. And then you can see that the commutativity relation can be viewed as a function like this, from histories to a choice of commutativity. And I'm showing you this because it looks super like the contextual orders that I showed you before. And I want to hopefully here wave my hands and tell you exactly the same way that the three automata can enumerate different contextual orders to give me different reductions, they can enumerate different contextual commutativity relations as well. So now I'm enumerating both contextual orders and contextual commutativity relations, and every time a reduction would be based on the particular choice of the commutativity relation and the order at that point. But naturally, this is just enumeration. Not all these contextual commutativity relations are sound. In fact, most of them aren't, because I'm just saying everything goes, right? So what is the solution to this problem? Enumeration easy, enumeration of sound ones super difficult. Now here is where the operational proof rule shines, in my opinion, one more time. Because I'm kind of keeping my proof and my program separate, this object that is enumerating all these programs can just basically enumerate everything. But I can piggyback on the subsumption check to the proof to actually certify the commutativity relation that has been used for the particular choice as well. So now subsumption becomes, are the behaviors of this reduction included in the proof? Yes. Is the commutativity relation you used to construct this reduction sound, in the sense that the proof can actually certify it as sound? And if the answer to both questions is yes, we will basically certify that reduction. And if no, we actually get a bonus out of this. We get counterexamples that are no longer just counterexamples to correctness. They can be counterexamples to not having enough ingredients in the proof for commutativity, which means in our proof effort, we can actually kind of try to add reasoning that just goes there to give us more commutativity. So hopefully we can have enough commutativity to be able to prove one of the reductions correct. All right, just to kind of, again, show you that this does matter, if you don't do any semi or contextual commutativity, as opposed to if you do, it makes a huge difference. Like 3 times more the number of benchmarks can actually be proven. Naturally, the benchmarks were selected to be sophisticated, like message passing programs, array programs, in things in which context and semi-commutativity mattered. But in this class of programs, you really need this to be able to get through. All right, finally, abstract commutativity. This one, in some sense, is the biggest white whale of them all. So it's simple enough to define abstract commutativity. You just use the abstract semantics instead of the concrete semantics to say, when is it sound to say two things commute? But naturally, the trick is, where should this abstraction come from? And is the abstraction that I have picked OK to use in reality? Right? The tension between abstracting too much or too little. So first, in the particular operational framework, we have to kind of understand what soundness means. So we have always in this framework a partial proof object that we are working with. And soundness really means that if I take the closure of this proof object up to the particular commutativity relation, the abstract one, everything in that closure should be correct. This is what soundness means, because this is really fundamentally the idea that I'm using here. Now, fortunately, whenever I have an abstraction candidate and I want to test whether this is true or not, I can easily test it. This is basically kind of thinking, hand-wavy, the proof has ingredients. It's based on a bunch of Hort triples, and I have to just make sure that my abstraction preserves the validity of those Hort triples. The moment that check, which is standard, passes, I know I have this sort of soundness property. So I can always be sure that whenever I have an abstraction, I can check that things are sound, so the loop is operating correctly. But operating correctly is kind of like the minimum requirement. The question is, where should that abstraction come from that would give me the desired commutativity relation, right? So let me take a tiny one slide detour and tell you that if you don't know where it comes from, but you pick a generic one, you still are ahead. So a very, very coarse abstraction. You look at your proof, you see what variables have not even been mentioned in the proof, which means they're maybe irrelevant to the argument. And you existentially abstract away those variables from the semantics of all your statements. With this abstraction, if we compare abstract and concrete commutativity in a lot of benchmarks, in their standard properties that they came with, abstract commutativity will do a little worse than concrete commutativity. But if you switch to a lightweight property, for example, if you're checking memory safety, then abstract commutativity takes over and does significantly better, proves a lot more benchmarks in a fraction of the time. So even if I'm not tailoring my abstraction to my instances, for generic instances, this gives me power. That has to be kind of explored. But going back to the question that I asked, if I have a particular instance, a program and a property, and I'm really searching for a custom tailored abstraction that would get me through that particular kind of obstacle, can I really search for it? And the answer is no, right? And the reason is that the intuition that, well, at least we had, and I think maybe people in the audience would share it, that abstractions and commutativity relations have this nice monotonicity property with respect to each other, right? The more you abstract, the more commutativity you are going to get. Nonsense. It doesn't hold. Here is a kind of tiny example with the same abstraction that I mentioned to you before. These two array accesses in the concrete commute because you know they're to two different cells. But if you abstract away for whatever reason variable I, now they become these two statements, right? You're accessing somewhere, you're updating somewhere in the array. Because you have lost the index information, you cannot separate these two things from each other anymore. And in the abstract, you no longer commute. Okay? So this kind of tells you that by take a pair of statements, move up and down the abstraction ladder, I can gain and lose commutativity as I go, really. But even worse than this is, if you take the whole view of the entire commutativity relation, you can gain commutativity somewhere and you can lose it somewhere else, which means the commutativity relations you get at different abstraction levels are all over the place. They're incomparable in the general together. So if I wanted to try to search for an abstraction, I'm turning an abstraction knob that is basically not connected to anywhere that I care about. And this makes it really difficult to search for an abstraction that would give me a commutativity relation. But like any good researcher, when faced with a problem you cannot solve, switch to one that you actually can solve and hopefully sort of solves the same problem. And this is, okay, for whatever reason, I have been all over the place, collected a bunch of abstractions. They give me different incomparable commutativity, and I want to use them all. I know I cannot pick a best. Can I use them all in one verification goal? And the answer is yes, under circumstances. So this is what we call a stratified commutativity. So we want to kind of basically use these commutativity relations. I'll show you a tiny schematic with two, one concrete and one abstract, but the idea would generalize to any number. Okay? So let's say I have a proof, and I have a concrete commutativity relation. I know everything in the closure of the proof up to that commutativity relation is safe. Then I'll take an abstraction, and I know that this abstraction is safe because I have checked it against my proof. So I know the safety of everything in the closure up to the abstract. Now the combination of the two, because the abstraction is strictly more abstract than the concrete commutativity, is that it's safe to basically take the closures in a strata, right? First up to the concrete, second up to the abstract. And the order really matters, the order of abstractions and the order of taking the closure. So if you did it this way, you would get unsoundness. Why? Because the inside closure is safe, but you have not actually checked, and you have no means of checking that the abstraction is safe with respect to the proof object, which is the closure of the original proof. The entire point of using commutativity was I was too lazy or too stupid to give a proof to that closure, right? So I don't have ingredients for the proof to check against the abstraction. I have no way of saying whether this is safe. But the one in green, safe. So we can actually use this one. So if you kind of think about the beginning of my talk, I told you we really cannot check closures, so we check reductions instead. And I'm here to tell you that, again, because we cannot, of course, check double closures, we can turn that into a double reduction. And here, if you don't follow me, don't worry. I'm just trying to finish the thought, but it's OK if you don't follow me. That is really unknown whether it's decidable or not. But it doesn't matter, because we can do something better, something even better than that double reduction, which is decidable. The only thing that we have to do is we have to throw in the middle the runs that we have already proven correct into the mix. So if we do that, we get a decidable double reduction proof rule. And it basically always works as long as you maintain the order of abstraction, the most abstract outside, the most concrete inside. So this is the way, the condition under which you can combine any number of commutativity relations all in one verification goal. All right. Just kind of to mention this, there are other ways of combining commutativity relations. For example, the tool Civil, that is using ideas of commutativity to verify concurrent programs, actually uses a different scheme in which it combines two commutativity relations that are incomparable with respect to their abstraction. But that one also, in some sense of the word, is boutique. So I'm kind of very interested in the general question of beyond, concrete order on the abstractions, are there other ways in which it's sound to combine commutativity relations? It would be interesting to discover more so that we can actually do more with this, short of solving the original problem that I put behind me. All right, so let's kind of try to wrap up. And with this, I want to turn my attention from the past to the future. If you have been kind of paying attention, even though I have not been saying it very explicitly, everything that I showed you is about safety. And the class of programs that would fit all the kind of theory that I mentioned would be the class of programs in which you have a fixed number of threads, or in the case of relational verification, fixed number of components in the self-composition. Naturally, the obvious kind of thing is how can we go beyond? More expressive properties, more expressive program classes. So I'll just kind of briefly tell you that we have looked at a few of these, but there are a lot more that are pending that one can look at. So we have looked at termination of concurrent programs, how to use this basically for liveness proofs. We have looked at unboundedly many threads case so that we kind of break the fixed thread barrier, and we are kind of currently looking at recursion, in which we cannot deal with concurrency because that would be undecidable, but we can try to maybe deal with hyper safety verification in the context of recursive programs. But a lot of other things like hyper liveness, other program models, basically a lot more research to be done, just expanding expressivity here. But what I want to focus on a little bit more as kind of future work concretely are two things that I kind of view as more grand challenges. The first of them is the fact that anywhere you look in commutativity reasoning, not just this area, all the three things that I opened as historical context, everywhere that I have personally seen, commutativity is always about commutativity of the atomic steps of the program. But you can easily see that, here I don't have a commutativity of a decrement and an assume maybe, especially if the decrement is blocking. But if I kind of look a little further back and I see that I have an increment and a decrement together, which effectively form a skip, that skip would always commute against anything, including this assume. And I don't have to look at context, I don't have to abstract, I don't have to do anything fancy. But this business in which you take commutativity beyond atoms to kind of sequences or blocks of code is effectively unexplored entirely. So ideally, what you want to do is you want to let parts move, and you want to let parts form alliances and move together, and different alliances at different times. This is kind of like the true power that has been left completely untapped in this framework. Of course, there is theoretical evidence a little bit that the moment you want to do this, things become difficult. A lot of classic noise results that all of this rely on immediately get falsified. But we started with Umang to look at this a little bit, and we managed to kind of put our foot kind of through the door, so to speak. We have kind of been able to show that in the simpler context of runtime monitoring and predictive testing, you can actually make this happen a little bit. But I want to emphasize that and you can come see my talk this afternoon if you want to learn more about this. But it's really important to say that work is scratching the surface in one of these categories that I showed you. All the other categories, nothing completely unexplored. It would be wonderful if we see more research in this particular aspect in the future. And lastly, this community has been great at taking classic verification, which is viewed as proof search, and basically creating this kind of cases in which a human and a machine can basically together have a really, really nice alliance and make big verification goals happen. So it would be wonderful if we could answer this, and I have absolutely really no idea, in how we can try to incorporate humans and human insight effectively into this other paradigm that I showed you, which would combine a proof search and a program search. And moreover, the proof search part, as I again showed you a little bit, is not, the program search part is not really just the program search, but implicitly a search for an ideal commutativity relation that would give us the ideal programs as well. So this picture and where human insight can effectively participate in this would be the thing that would actually kind of make it happen for really nice big projects beyond smaller things that fully automated verification can take care of. And I'm hoping that the community will rise to the occasion and kind of help with this, because I don't have that much experience kind of trying to sort out this sort of problems. And with that, thank you for being here and listening to my talk, and I can take questions.
Thank you, Azadeh, for a great talk. We have time for several questions. So come to the mics. There's a mic over here, or are the student volunteers around? Yeah, if you could pass around the mic.
Hi, that was a very nice talk.
Thank you.
I wanted to ask you, have you looked into, using properties of a language to get more commutativity relations? For instance, in Rust, you know that different variables refer to different, mutable variables refer to different disjoint regions of memory, so you get sort of more commutativity than you might in something like C.
That's an excellent question. The answer is no, but mainly because in all of this work we work with a very simple programming language, right? But fundamentally, I can acknowledge, related to your question, that checking commutativity for simple statements easy. As program statements become more and more sophisticated, this starts to become way on the thing, especially with abstractions, because abstractions make the semantics of statements very sophisticated. And then you can basically start checking commutativity of a super sophisticated thing. So I absolutely am with you that any such thing that would basically lift the burden from those tests would be a huge impact in making these ideas work much better.
That was a great talk, thank you. One thing that you didn't touch on is how successful these are in practice. So are these sorts of techniques used in industry every day? Are we a decade away from being able to do that usefully? What's the current status of actually using these things?
So, the entire research is not more than, mine is not more than 5 years old. Like the beginning point was 5 years ago. So naturally not being used in industry every day today. Some of the ideas, for example, the part in which you don't want to enumerate every reduction, but a handful of them, I don't see any delta between what was automated verification before and that. So for that, I don't see any kind of problem of deployment like immediately today. We are not making anything slower or worse. We are just making things faster. The part of actually enumerating a lot of reductions does make things slower, right? You're doing double search instead of a single one. You have to pay a cost for this. So for that, my view is that if that is supposed to happen in practice, we really need to now step out of the theory into this practice of one of the two things. Either kind of pare back, just not search everything, search like a subset that is still good but can be done more effectively, or what I actually mentioned at the end, that you would sort of get a little bit of insight in a form that is not clear to me today from the user. So the user would say, here is an idea of a reduction. Why don't you just go and prove it sound? And then effectively, I would give a big leg up to this search in which I go back exactly to the status quo. So basically the future work that I mentioned is all in the direction of trying to bridge that gap and make it happen. But so depending on how that works out, maybe 5 years.
Thanks a lot. That was a really great talk. I remember, so totally on an unrelated field, but you may see like how it relates. I've seen like on binary and assembly level verification, some work that were also quite close. So if I understand well, the commutativity relates quite closely to observational equivalence with respect to the assertions you want to prove. And I've seen a lot of work on assembly with like more syntactic, like use-defined chains or diffuse chains, that we're also trying to slice the programs with respect to some of the assertions to try to create a kind of normalized form with commutativity, so you can extract chains and you can prove specifically on each of the chains separately. Is there something like a kind of normalized form of what you would like to commute that would be more efficient by saying, like, for instance, you take all the send before, you take, like, can you do this kind of thing also?
If I understand you correctly, because I'm not like intimately familiar with this research that you're mentioning, the lexicographic reductions that I mentioned to you, you can really view them as normal forms, right? The only difference is that they're parametric normal forms. You change your order, you will get a different normal form. And I kind of, to keep this talk high level and pleasant for everybody, I kind of jump over a lot of details. So for example, even if I'm constructing one reduction, I can just construct one, but it will be ugly and huge and completely useless for verification. So a lot of research has gone into how to take a make a compact representation of that thing that would actually kind of have the results that I showed you, that it would work faster, like half the time, right? So there is definitely some connection there. It's just that I don't know the normal forms that you're talking about were constructed with what goal in mind. I can say that these ones were constructed with the goal of the most compact kind of representation I can get. But I don't know whether being small matters there or not. But fundamentally, normal forms are the thing. There is no other way of doing this, right? So.
Great, thanks.
I'm going to take the last question from Discord. I think that the questioner says, I think there are connections between tree automata and e-graphs or quality saturation. What are your thoughts about connections between e-graphs and your techniques?
I mean, I understand exactly at that level that to me, coming from automata theory, e-graphs are tree automata. So beyond knowing, that e-graphs and tree automata are more or less the same representation under two different guises, I don't know what connection there is, but I can maybe answer the question slightly more intelligently by saying that and I think I've seen a little bit research in this team that tree automata, we use tree automata to effectively represent a set of programs that have a particular purpose here. We have actually started looking into this, but with the whole LLM explosion effectively given it up entirely, that you can use e-graphs for the purpose of synthesis, which e-graphs are used. You can use tree automata for the purpose of synthesis in a sense that you can try to enumerate a lot of candidate synthesis programs and then pick the correct one more or less using the mechanism that I showed you for proof checking. So there are definitely those sort of formal connections, but the devil in this case is whether it's going to be effective. And for me personally, the moment enumeration kind of went through machine learning and LLMs, enumerating programs with tree automata for the purpose of synthesis seems like, hold that thought and see what happens before kind of investing too much time in this.
All right, let's all thank Azadeh for a great talk. Just a brief announcement. So in just a few minutes, the next set of session previews will start in the Siemens room. That's one floor up. So if you want to see the session previews, go make a beeline for the Siemens room. Also for the talk sessions, they're going to be parallel tracks. One track is here. The other track is 2 floors up in the Turing room. Okay, the Turing room is smaller than this room, and so there's an overflow room for the Turing room. If the Turing room is full, go to the Mountbatten room, which is connected to it on that side of the building. Okay, thank you.
we are starting the session Synthesis 1, one of the first session in POPL. And we will start with the paper Implementation and Synthesis of Math Library Functions. And this will be presented by POPL'24.
All right, thank you, Sam. Is the audio working? All right, excellent. So actually, the intention was for my student Ian Briggs to give this talk, but then he went and graduated and is now verifying hardware for Amazon. So it feels like I'm in grad school again, very exciting to kick off POPL. So this talk is about what happens when your program evaluates an elementary function, like sine or cosine, x per log. Because the thing is, you and I both know, there's no magic smoke inside these function implementations. They're using the same kind of primitive arithmetic operations that any other numeric code in your program uses. And this task of implementing elementary functions using primitive arithmetic, that's something that humanity's been working on for literally over 100 years. So that's kind of interesting. Why is it so hard? Like, why haven't we licked this problem yet? Most other problems in computing are not this old. Well, there's a lot of reasons. But I think one of them that's relevant to this talk, is this idea of a speed-accuracy trade-off. See, what my students and I have shown in previous work is that if you accept slightly less accurate implementations of sine and cosine, well, there are trade-offs inside those implementations. There are choices you can make. And if you're OK with them being slightly less accurate, they can be quite a bit faster. In fact, depending on what accuracy you're willing to accept, you can see speedups of like 2, 3, 4, 5x. And that makes a real-world difference, especially in numerically intensive programs, like in physics, engineering, high-performance computing, and graphics or AI, that kind of thing. So if these really big speedups are available, as long as your application's willing to tolerate slightly lower accuracy, it really seems like what we should be doing is implementing application-specific versions of these math function implementations, ones that are perfectly suited to the accuracy and the performance requirements of whatever application you're doing. Maybe even not application-specific, maybe call site-specific. Maybe specific to every individual use case of your program. So that'd be cool. We could get big speedups. And again, in prior work, we've shown that this really does happen. You can do this thing. But mostly people don't. This kind of thing is pretty rare. So we asked ourselves, like, why is it rare? Why don't people write application-specific implementations of sine and cosine more often? And yes, OK, so one obvious answer is that there's some background you need. In that 150 years, we figured some stuff out. It might be relevant to your work. Fine. But I think actually the background issue isn't as big of a problem as you might think. First, you can learn it. Second, not all of it is relevant. You can do a pretty good job even without most of it. Honestly, having done some of this kind of work, I can tell you what the biggest reason not to write your own sine or cosine function is because of how many damn typos there are in the process of writing it. It is so easy to write a minus sign instead of a plus sign, and there goes your whole day. Because you have to find that mistake, or worse, you're going to do some kind of optimization work on the assumption you're getting good data, and then your data's total nonsense, of course, because you wrote a minus sign instead of a plus sign. And it's not just that. You can parenthesize things wrong. You can copy and paste some coefficient and lose a couple of digits at the end. You can forget to scale something. This is super common. Just as like a quick personal story here, I wrote the quadratic formula function in the Racket standard library. And supposedly, like, I'm supposed to be good at this kind of thing. And I was quite proud of this implementation. I spent a while on it. I came up with some novel algorithmic approaches that I was very happy with. I put in quite rigorous testing. I wrote a little paper proof of my work. I thought it was good stuff. So we shipped it in Racket, I think 8.6 or 8.7, and all was good. And then 2 years later, I get a bug report. And this bug report has this super carefully crafted quadratic formula. It's just this one formula they could find that it produces the wrong answer. So I was devastated. I was so happy with this work, and here there's a flaw. I look into it, and this is the bug fix. All I had forgotten to do is I had forgotten to rescale some kind of residual parameter. This code matters only for the rarest of inputs. This is an error handling variable in an error handling branch. It's crazy that this guy was even able to find this bug. So OK, that's a funny bug. It's a little embarrassing for me personally. If this is the problem I ship to production, think of how many versions of this I typed into my text editor and then had to debug. How many versions of this threw off earlier attempts at testing or threw off some optimization work I was doing. So that's what this talk is about. This talk is entirely about typos, and specifically it's about this DSL that my students and I have built, megalibem, to catch those typos before they throw off your work. Megalibem is a workbench for writing these application-specific elementary function implementations. It's safe, it's modular, it's tunable, and I'm going to tell you a little bit about it. So let's start kind of at the core of one of these elementary function implementations, which is answering this question. We want to implement some kind of elementary function, but we don't have access to any cool elementary functions. What we've got are like plus, minus, times. If you're feeling spicy, you got division and square root, which means that you only really have access to some small family of functions. If you've got plus, minus, and times, that's polynomials. If you add division, maybe you have rational functions. So at the core of any of these implementations, there's some kind of approximation of the elementary function you want by this restricted family of functions. And this is in real-world implementation. So for example, here's the AMD optimized compute libraries libm implementation of cosine. And what do we have in blue right here? It's a polynomial evaluation. It's a macro that expands to some code that evaluates a polynomial. And of course, if you can do this in C, you can do this same kind of very common operation in our DSL called megalibem. There's a construct called polynomial. You give it a list of coefficients. It evaluates a polynomial. But the superficial similarity of these two expressions belies a key difference at the type level. See, in C, the type of this expression is double. And what that means is that to the C compiler, any double precision value is exactly as good as any other. If you add a minus sign, that's still good. If you delete some terms in your coefficient, that's still fine. You can even, rearrange some stuff. C can't catch those mistakes. In megalibem, however, we're going to try to track the mathematical computation you're doing at the type level. So this term has a type. It says it's an implementation of a mathematical function. And the specific mathematical function for polynomial is that polynomial that you wrote down. Now, we're not trying to implement a polynomial. We're actually trying to implement cosine of x. And so we can express that intent to megalibem using the approx construct. So what approx does is it has a first argument telling you what function you're approximating, a last argument telling you how to do it, and it returns an implementation of cosine of x, its first argument, instead of an implementation of that polynomial. So basically, it's like a kind of cast. But a key thing this gives us is the ability to make the cast safe, because there's this middle argument, this epsilon, and that's an error bound on the difference, on the approximation error between cosine of x and that polynomial. And we can check this error bound at compile time. In fact, we can check it as part of the type system. Let me just show you how that works formally speaking. Let's write down a type rule for approx. This approx returns an implementation of its first argument. Here it returns an implementation of cosine of x. And it does that no matter what its last argument, the actual implementation, is computing. So here we have an implementation of a polynomial, and we cast it to an implementation of cosine. And this kind of cast is safe insofar as the difference between the two functions is bounded by epsilon. And so all of megalibem's type rules, they have these what we call semantic well-formedness conditions. These are mathematical properties, property of pure real numbers, that ensures that the steps you're taking in your implementation are reasonable. And we can check these automatically by dispatching to any number of mathematical tools. So like, it could be Mathematica or MATLAB, or there's loads of these kinds of solvers. Okay, so this is kind of our general approach to keeping things safe. Now let me zoom out a little bit, tell you how we can put these individual safe components together. Here's a more full graph of cosine of x. And if you look at it, one key property of cosine of x is that it's wiggly. And for mathematical reasons that honestly are a little beyond me, wiggly functions are hard to approximate with polynomials. Don't quote me on that theorem, but wiggly, bad. Luckily, there's a trick. We don't have to approximate this whole wiggly function using polynomials, because if you look carefully, this whole function is actually a copy and paste of that blue square right there, just with some flips and shifts added in. And that gives us an implementation technique called range reduction and reconstruction. The idea is, suppose we're going to evaluate cosine of x on this point right here. It's outside that blue region. But what we can do is map it to the corresponding point in that blue region. That's called a reduced input. Then we can evaluate cosine within that blue region using, for example, a polynomial approximation, and that gives us what's called a reduced output. And then we can reconstruct the reduced output, and that gives us the final output for the original input. So this is a super common technique. That's how you do it in C. And you can do the same kind of thing in MegaLibM. There's a construct called right, and it's called right because you extend the valid range of inputs to the right. And this term, it takes E, which is the actual implementation to use in that blue region, as well as a reduction and a reconstruction function. And of course, just like any construct in MegaLibM, this one is safe. So here the type rule says that this is an implementation of f of x if it wraps an implementation of f of x, and moreover, if that reduction, application, and reconstruction is equivalent to the original. So there's the standard well-formedness side condition. But the really interesting thing happens when you nest these range reduction and reconstruction operators together. So here I've used right to extend the original blue region into like half a period of cosine, but I can send it to the left as well, and that gives me a full period of cosine. And then I can use this operator called periodic to actually extend it to the full range of floating point inputs. And of course, throughout the process, MegaLibM will track that range of applicable input variables to make sure that I don't make any mistakes. So that's how our core language, it provides this safety and this modularity. It makes sure you don't make mistakes, and you can build these things step by step. Now let me tell you a little bit about how we actually turn that into usable C implementations. Basically, we compile this code to C. So that's the full story. But there's some decisions you have to make. Even for something as simple as polynomial, there's more than one way that you could potentially implement a polynomial in C. There's Horner's rule, there's a Strins rule, there's all sorts of variations on these. And these decisions, even though they seem kind of trivial, they matter a lot. Horner rule on the left-hand side, for example, that's typically the most accurate way to evaluate a polynomial. But it's not the fastest. This middle rule, a Strins form, that works really well on vector hardware because you can combine some of these operations together. And this last one, that lets you can kind of split the difference between them. You can do a little bit of Horner's rule, a little bit of a Strins rule, mix them in various ways, and try to get the best of both. So if you want to get good performance and accuracy, you do have to mix. You do have to specify how exactly you're planning to do this. And in MegaLibM, you can do this by basically adding annotations to your expressions. These annotations modify the compiled code. They don't modify the type system or the semantics in the real numbers. So here, for example, I can take this polynomial rule, and I can specify a bunch of things about it. I can say do it in 64-bit, use a Strins form, split out some terms, do those terms in a different precision, and all sorts of other things. And other terms in MegaLibM, they have the same kind of properties. We can add new algorithms at the compile time stage using a technique like this. Of course, you'd have to be crazy smart to write this thing from scratch. I don't know anyone who could do it. But our idea in MegaLibM is that you can do this interactively. You can try something, see how that affects speed and accuracy, try something else, and repeat. And in order to support this workflow, MegaLibM is actually embedded inside Jupyter. So you can try something. You can write a little MegaLibM program. And then you can graph it. You can compare two different versions. So here, for example, you can tell that V2 on the right-hand side is slightly more accurate than V1 because the blue dots are lower. And then once you're happy with the results, you can export that to C. So that's kind of the idea of how people can use MegaLibM. And of course, we've used it a bunch. We've managed to replicate a bunch of existing implementations in popular math libraries. And we've typically managed to achieve comparable speed and accuracy to those original implementations. But of course, since we're implementing these in MegaLibM, they're shorter, they're safer, and they're probably a little bit easier to reuse or reuse chunks of. And it's kind of a little funny. In the process of doing this, we've actually found some bugs. Exactly the same kind of bugs that I would make if I were doing this work, so not saying anything wrong about the authors. So like here, for example, this is a little snippet of a library called VDT, the cosine implementation. And if you've been heads down in the C standard, you'll probably immediately recognize that these first two terms are going to be parenthesized by the associativity rule. But that's actually not what you want to do. And MegaLibM, in this case, generates sort of automatically. It generates the more reasonable code, which parenthesizes the last two expressions, and that produces this much more accurate output. So we actually found some of these bugs in the process of this work. And moreover, because MegaLibM is kind of this interactive workbench, we're able to take some of those existing library implementations and just change some stuff. There's some tooling built into MegalabM to like synthesize new polynomials or try out different ways of doing it. And we were able to get faster and more accurate variations on those original functions as part of this MegalabM code. In this last column, you can see that the number of lines changed here is minuscule. We like change 1 or 2 lines of code. That means add 1 or 2 of these annotations, and things work better. So that's MegalabM. It's our safe, modular, and tunable DSL for writing these math libraries. It uses some of the techniques that I've covered throughout this talk, and I'm happy to take any questions that you have.
Hello, can you hear me? Yep.
Yeah.
Thanks
Hello.
for the talk. My name is Arthur Charguero from INRIA. My question is about verification.
Yeah.
What are the plans? What can be done? In particular, can you use a GAPA tool to get some bounds on the errors that you are computing with the various versions that you generate?
That's a great question. So it seems natural to integrate verification into this. We played a little bit with tying this to FP Taylor, which is a tool you're probably familiar with. And that worked OK. Basically, from each of these like constructs in the DSL, we can generate an FP Taylor condition and have it verified. So I think that code bit rotted, but like it could be resurrected. I'm a little less familiar with GAPA, but I'm sure we could do something similar. And I think it would be very attractive, right, to generate verification conditions for these implementations. So yeah, great question. I'd love to do it. It's just my student graduated. And you know that once you become a professor, you lose the ability to program, except via email. So I'm a little stuck right now for how I might do that work.
Time to hire a new student.
I'm doing my best.
Hi, thanks for the great talk. I'm curious, in the rule for approx, you showed how the epsilon sort of was used in verifying that the approx was OK. But it didn't look like epsilon was tracked in the output type. So I'm wondering how those approximations work under composition. Can you use them again in another approx? How do the error bounds propagate?
Yeah, so that's a great question. So here, epsilon is like a local error bound, right? It says this specific approximation, you incur this much error. You're right that this isn't tracked at the type level. So like if we then do some additional range reduction on top of it, maybe that error grows, or maybe it shrinks. I don't know. I've done related work on tracking how these errors kind of propagate through the program, and I think also it's a little related to this question about verification. Right now, these error bounds don't contribute in any way to like the compiled output or to the type checking besides this local one. But yeah, I think that would be interesting. I've been hoping to integrate some of this approx functionality into my tool Herbie, which is kind of like where my research typically ends up being deployed, and there we'd have to track it.
Thank you.
If you're a student who wants to do some of the work that people are asking me questions about, like I'm in the market, talk to me.
I'm not actually a student, but I am interested in doing some of the work. But first, I'm going to make your life a little bit more difficult. There are a few numbers that are extremely difficult to compute, say, the sine of.
That's right.
And certain implementations will literally just handle these by case.
That's right.
And sort of start, OK, if it's this thing, here's the answer, don't ask why. Can you do that? How does that fit in? Because doesn't that sort of pluck holes in your type system?
It's a great question. So, there's parts of the DSL I didn't show here. One of them is a construct called split, which literally lets you just add an if statement and handle multiple cases. It's still safe in the sense that all of the cases have to have the same type. But that type could be we implement cosine of x on the range from this number x to itself, literally a point interval, and then of course we can verify that by just checking that you wrote down the correct output. I will say, you can immediately notice floating point expertise because Martin started with there are a couple of numbers. Yeah. Any other questions? Probably time for one more.
Yeah, super interesting work. Is it possible in your little DSL and type system to implement arbitrary computable functions with loops and things like that?
No.
Other than polynomial, if you want maybe to compute Newton's method or I don't know.
Yeah, that's a great question. No, there's no option for loops. There's some limited support for conditionals. I'm not sure this is like a deep, moral statement, but it's much easier to verify loopless programs. Obviously, the concerns about like type systems, et cetera, are simpler. And to be honest, typically these mathematical functions don't do that, right? Even, you mentioned Newton's method, for example. That's pretty common for use inside implementations. But typically you have some fixed number of iterations because each iteration like improves your error bound and you know the maximum number of these. That also, by the way, makes it much easier to determine like how fast a program is because typically you only have a couple of program paths. So it's, you can approximate that by like the program is just this fast for all inputs.
Thanks.
All right. So I think that's it for me. And let's switch to our next speaker. You need the clicker? It's mine, but you can use it. No? All right.
Is Shi Kyung Yu, and he will be presenting enhanced enumeration techniques for syntax-guided synthesis for bit vector manipulations.
Okay, can you hear? All right. So yeah, this is joint work with my student Yuan Tian Ding. Unfortunately, he could not be here due to some visa issues, so I'm here to present. So the talk is about syntax-guided synthesis, or SYGUS. The idea is that to capture the user's intent for a synthesizer, we need to provide not only semantic specifications, which talks about what the program's supposed to do, what's the functionality, but also syntactic constraints, what the program should look like, right? That can dramatically reduce the search space and help the synthesizer find a solution faster. So let's take a concrete example to see. Hacker's Delight example number 25 in SYGUS interchange format. The SYGUS interchange format is a common format to represent SYGUS problems and accepted in many competing SYGUS solvers. And Hacker's Delight is just an excellent book which exhibits a lot of interesting examples of tasks that can be represented using bit vector expressions. So a lot of tricky and elegant examples. But from the point of view of synthesis, they are extremely challenging. Okay, in the example 25, it just says, compute the higher order half of the product of bit vectors x and y. Okay, this task can be translated into a bunch of examples from the point of view of programming by example, right? So we have some random examples. For example, if x equals 8000, y equals 0088, then the output should be 0055. And you can have a bunch of examples to characterize the specification. And besides this semantic specification, we also ask for a syntactic constraint, basically what operators you are allowed to use, right? This could be quite arbitrary, but you want to allow most common bit vector operations and get it represented as a context-free grammar. And here, the interesting thing is that you can you can provide some constant as your hint to the synthesizer, right? For example, the 00FF is just a mask of the second half of the bit vector, right? So because the question explicitly asked about first half, second half, this could be a key constant that help you distinguish first half and second half. And the number constant 8 is just number of bits you want to shift if you want to switch between first and second half. All right? So we don't really know what the program is, but we know, okay, these are probably what you want to use. And taking both the two pieces, the syntax-guided synthesizer is supposed to generate a solution which satisfies semantic specification, also follow the syntactic constraints, which is an instance of the grammar. Okay, for example, this on the screen, this is a solution found by our SYGUS solver, Drive Things. So it looks not so difficult, but it's already beyond the capability of all existing SYGUS solvers. And this talk, the contribution of the paper is mostly about the techniques behind how we find solutions for challenging problems like this. Okay, before I tell you what we did, let's see what has been done in the community. Okay, for bit vector synthesis, or more generally, syntax-guided synthesis, there are two major approaches. One is bottom-up enumeration. So you have a syntax constraint that represents essentially a search space. You have an infinite space of candidates from the search space, and the synthesizer is just going to take a semantic specification and search for a solution. And because the search space is infinitely large, the key question is how do you search, in what order? Right? The most naive way is to search based on size. You start from the smallest possible solutions and move on to larger ones. And also you can do better search if you get equipped with equivalence, right? Some candidates could be semantically different, but essentially the same programs. They are semantically equivalent, so you don't have to search all of them. You can search one of them and discard a lot of solutions. So the next talking session is about observational equivalence. So, but in different contexts, but you would get the idea as well. And of course, you can do probability-based search, right? You can, not all candidates are born equal. Different operators have different likelihood. You can assign some probability, and you can steer the search better to a solution. Okay, you have a lot of interesting ideas going on. And another big idea is top-down deduction. You take the semantic specification, ask the question, what can be the top-level operator? Okay, if you pick one operator, for example, you want to have an add, then the question is what can be the left operand, what can be the right operand? And you can split the specification to two sub-specifications, right? And the two subtasks can be divide and conquer, and you can keep doing the splitting downward. Okay, this is another major idea, and you can imagine that there's a lot of novel ideas to combine these two ideas, right? So for example, you can do top-down deduction to get the top-level operator synthesized, and from the leaves, you can also start from small enumerations, and the two directions meet in the middle, something like that. A lot of interesting ideas, but the question is, do they really work for bit vectors? Well, not really, because evidenced by a lot of unsolved problems like Hacker's Delight. So what's the problem, right? So what makes bit vectors so difficult? So from the point of view of top-down deduction, the problem is that you have too many different ways to decompose, right? Even if you have a very simple example, you have two inputs, 1, 1, and 1, 0, you want to have 0, 1 as the output, right? So what can be the top-level operator? It turns out to be the case that almost every operator can serve as a top-level operator. And even if you stick with a single operator XOR, right, it's not too hard to figure out that you can have arbitrary combination, right? So the left or right operand can be 0, 1, 1, 0, 1, 1, 0, 0, right? And if you have, well, 64 bits or something, it can be a disaster, as you can imagine. So it does not really helpful if you have so many different ways to decompose. And bottom-up enumeration, of course, we know that there's an exponential blow-up, but things are especially bad when it comes to bit vectors because you have more than a dozen commonly used operators, right? The search space grows extremely fast when you have larger expressions. So our first idea is to have a normal way to combine the two directions, which we call bottom-up deduction. So what does that mean? Let's take a look at a different example. So Hacker's Delight, example number 19, difficulty level 5. I put the example here, but you don't really have to understand it, right? All you need to know is that you want to synthesize a function with 3 parameters, x, m, k. And the arrowed bar shows the order of search if we follow the size order strictly. And if you search along the way, at some point, you can find the expected solution, right? But you have to search an astronomical number of candidates before you can hit the candidate. And you can do a lot of probability equivalence techniques, right? You may get 1 or 2 orders of magnitude speed up, but that does not change the story much. So what do? We can keep multiple pools of candidates. Okay, what can serve as, if we want to have XOR as the top level operator, what can be the left operand or what can be the right operand? And when we get to a candidate psi left shift k, okay? This is not a solution, obviously. But note that this is actually the right operand of the expected solution, right? We can reason, we can do a deduction and determine that, okay, it can serve as the right operand of a solution if the top level operator is XOR. We don't really know what the left operand could be. We don't know if that part will cooperate. It's just angelic wishful thinking, and we just keep the candidates there in the candidate pool. And later at a point, we find the other piece of the solution, and we can put it in the left operand pool. Right? XOR is commutative, so we don't really have two different pools, but conceptually we have two different pools. But once we have the two pieces, we can immediately put them together and check if they can be combined to find to be a solution. Right? That makes the search much faster than a brute force search. So that's a bottom-up deduction idea. It can help us solve the Hacker's Delight number 19. But for 25, we still need a final push. We need another pair of techniques. The second one is term graph-based enumeration. So look at the solution. We have the psi, which is a commonly used sub-expression. In the tree representation, it makes the tree really large. So this is quite common. You see many common sub-expressions because for bit vectors, you don't really have functions, right? So if you have some common components, you have to repeat. But if we do a term graph representation, you just have one single copy of the common shared sub-expressions. That makes the representation much more compact. And if you search along the side of the term graph, you can prioritize the search to these kind of expressions. All right, this is a very simple idea, but we were a bit surprised that it's not actually explored in the community. And it helped a lot in some cases. So one more thing is large language model guidance. Well, in 2023, when we prepared for the submission, it's not too surprising that we ask ourselves, oh, can we get the job done by ChatGPT? Right? We did try. The good news, or I should say bad news, is that ChatGPT cannot get it solved. Right? But if we lower our expectation, if we say, okay, can you give us some useful sub-expressions that we can reuse? And it did quite a good job. And if you ask a question many times and you just see what's the repeatedly proposed sub-expressions, it becomes quite robust. You get some key components suggested by ChatGPT. Okay, for example, here, the P1, P2, P3, P4, right? You have the upper half of X product with upper half of Y, right? The combination of upper half, lower half of X and Y, right? That's quite understandable because in the prompt we have some keywords like product and higher order half and lower order half, right? They kind of capture the keywords and know that the product of these combinations, higher order half, lower order half, can be helpful, right? So they are actually helpful. This, if we give these components as hint to a synthesizer, right? So this could be used for extended grammar. So we can get the search much more efficient. All right, so let me move on to evaluation. So we have implemented all the ideas in our Cyger solver called Drive Things. It was a Cyger solver just supporting conditional linear integer arithmetic. Now it supports bit vectors as well. So it's available if you have any synthesis questions, give it a try. So we have tested over 20 benchmarks from Hacker's Delight and more than 700 benchmarks from the Cyger's competition and 500 benchmarks on the obfuscation. And we compare the performance with CVC4, Droid, Probe, and Simba. Okay, all state-of-the-art Cygus solvers. So how many can be solved and unsolved? It turns out that we can solve all the problems from Hacker's Delight and case splitting. We have 15 problems unsolved for the obfuscation. This is better in every category than every other solver. And some benchmarks were solved by only one solver. DryThings uniquely solved 31 benchmarks. Simba solved 4. Droid solved 3. Here's the result for Hacker's Delight. So starting from example 19, going on, they were not solved before, right? And for the simpler ones, we are like 1 order of magnitude than existing solvers faster. Here's a cactus plot for performance on case splitting. We are consistently faster than other solvers. And in terms of size, the solution size, we were not smallest one for easier benchmarks, but it tends to be smaller when benchmarks are more challenging. And we have similar observation for the obfuscation benchmarks. So I'm running out of time, so I don't want to talk too much about ablation studies, but takeaway is that every single idea is critical for some of the benchmarks, and we have all these techniques combined together, we can get all the Hacker's Delight benchmarks solved. All right? So yeah, that's what we have, a bunch of techniques: bottom-up deduction, term graph-based enumeration, and large language model guidance for bit vector synthesis. But I think the techniques can be general and useful in other contexts as well. So thank you for your attention.
Nice talk. Just a question. So this, you evaluated on bit vectors, but it seems like the techniques could be useful in other settings. Have you evaluated Dryad synth on other Cygus benchmarks?
We had the CLIA solver. The DryThings was built for CLIA. We had a POPL'24 paper talking about our algorithm. But when we move on to bit vector, we found it's extremely challenging, and we need a set of new techniques to address bit vectors. But yeah, I think the techniques can be generalized. We are revisiting CLIA algorithm and see if they can be helpful in that context as well.
Hi, great talk. I had a question about the bottom-up deduction step, specifically when you have something like something left shift by k, is that a complete term, or is that a term with a hole in it?
This part?
Yes.
So can you repeat your question?
Yes. So basically, when you're saying that I can put something like something left shift by k on the left side or on the right side, is this a complete program term? Like, is this something that you know what it evaluates to, or is it something where you don't know what you're left shifting yet, I guess?
So when you put a candidate in the pool, it means that it's a potential candidate. Okay, it can serve as a left or right operand of an XOR. I don't know what the other operand could be, but it's satisfiable, right? It's if I can find a solution on the other side, they put together can form a solution. I don't have a full solution. I have a partial solution. I just keep the candidate in the pool and keep moving on the search. So I'm keeping multiple pools, right? So for XOR, I have left pool, right pool, right? So what's the left operand, what's the right operand? For each operator, I'm going to keep a bunch of candidate pools, right? Okay. And it's not necessarily just one level. Sometimes we do 2 levels. XOR, what's the left operand, what's the right operand. So if we keep enough number of pools, that we can eagerly find candidates so that they can put together to form a full solution.
Okay, yeah, so I understand the part with the pools. I think the part that I was confused by is like maybe a concrete example would be, would this term look something like x plus 3 left shift by k, Or would it be something like, I don't know, +3, left shift by k? Like, basically, is this a term that you can evaluate already when you put it in the pool?
Yeah.
It is.
If
okay,
you put
great.
something, it's already.
Okay, thanks. That's just that was my question.
Okay.
If there is no more questions, let's thank the speaker again. So our next talk is efficient bottom-up synthesis for programs with local variables. This will be presented by Xiang Li and Xianggu Zhu.
Hello, good morning. I'm Xiang Li, and this is Xiangyu Zhou. So today we're here to present a new, more efficient synthesis algorithm for programs with local variables. To start, let's see an example of a program with both local variable and data dependencies. So one that comes to mind immediately is fold, which is a very common higher-order function in many languages. So fold takes in 3 arguments: a list to fold over, the initial value of the accumulator, and then a lambda function that takes in the accumulator, the current element, and gives the new value for the accumulator. So we see that there are 2 local variables, ac and elem, and that the value of ac depends on the results of previous iterations. So there are data dependencies. Synthesizing programs like fold turns out to be very challenging. So several prior works have tried to tackle this problem using either bottom-up or top-down synthesis approaches, but all of them have to fall back to some form of enumeration in the worst case. And we want to avoid enumeration because it can be very slow. So we thought, can the classic approach of bottom-up enumeration with observational equivalence work for programs like fold? And unfortunately, it turns out that it's quite challenging. And Peleg et al. Summarize it as a chicken and egg problem, in the sense that the accumulator values are required to evaluate the programs. But on the other hand, we need to know the programs before we can obtain those values. To see this in an example, let's see a fold program, and let's execute it. So we see that we need to execute the first iteration to know that the accumulator value will be 7, and we will then be able to plug 7 into the second iteration to evaluate the second iteration. And on the other hand, we need to know the program has a body of ac times 2 plus 1 before we can obtain those accumulator values for each iteration. So we thought, how about like top-down if bottom-up is very challenging? Well, the most like naive top-down is you can sort of list all the potential bodies for the fold and just evaluate each of those programs separately for 3 iterations, and then check their output to see if one of them produced the desired output. But this is obviously very slow because this is just full enumeration. But we observe that there are some advantages that we can take. We can take advantage of many shared properties, because those subprograms actually share outputs within one iteration or even across iterations. So we thought this is a very good opportunity to apply observational equivalence for those bodies of the fold. That's how we propose the idea of lifted interpretation, which combines top-down interpretation of all programs in a grammar with a bottom-up enumeration, with observational equivalence. So here on the left, it's a very familiar top-down interpretation of all the subprograms in the grammar. And on the right, we construct equivalence classes of those subprograms from bottom up. So this might sound a little bit abstract. So let's take a simple example. So those are the 2 fold programs we saw earlier, ACK times 2 plus 1, and ACK plus LM times 2. So we'll start by going down, walking down the tree until we hit a terminal in the grammar. And then we're going to evaluate ACK. So I want you to focus on the big curly brace on the right. So that's how we represent a context in the equivalence class. So the context now for the first iteration consists of three things. First is the list, which stays the same for all the iterations. Second is the current value for the accumulator, which starts at 3. And third is the current element, which is 2 for the first iteration. So this equivalence class on the right groups all the programs that produce the output of 3 given the current context. And currently, there's only one subprogram, which is ACK. We can continue the interpretation and then see the literal 2, create a new equivalence class on the right. We can do the multiplication, create a new equivalence class of programs that output value 6 on the right. And then we can finish interpreting the first subprogram, ACK times 2 plus 1, create a new equivalence class of programs that output 7 on the right. Now we can continue this process for the second subprogram. And then we see that ACK has already been seen when we evaluate the first subprogram, so we don't create a new equivalence class. And then LM also produces 2, but for clarity of illustration, we're going to separate them into a separate class. 2 is already seen, so we don't create a new one. And then LM times 2 produces 4. So that's a new output, so we need to create a new equivalence class. And lastly, we can finish executing the second subprogram. And we notice that it produced the same output as the first subprogram, namely 7. So we can merge that into the same equivalence class that we constructed earlier. So we notice that there are already plenty of sharing going on in the equivalence classes for this simple example. And we can continue this process for the second and third iteration.
Okay. No. Oh, yes. Okay. So we have illustrated a small toy language for fold function. And now we want to apply it to solve a more complicated real-world problem. So we chose a domain of web automation, where in this domain, the main task is to automate interactions on the web page. For example, to scrape a list of item price on some shopping website. This time we use the domain-specific language, which is much more complicated and bigger than the language in the previous example. And here are some important components. So programs in this language is a sequence of statements, or it can be a skip symbol when it is at the end of the sequence. A statement can be a singleton action, like a click, or it can be a loop procedure. That is commonly used to loop through a list of items and to apply actions on each of it. So as you may notice, we use the lambda expression to represent the loop body, which in turns introduce local variable in this domain. Finally, we'll have the selector, which is used within the statement to locate some web element. And the fact is that there can be tons of alternative selectors for each statement, which makes the program space to blow up very quickly. So this is also why this domain of the problem is very challenging to solve. So in synthesis problem, we use so-called tree semantics in this domain to evaluate our programs. That is, given a program and a context, it should give you back an action trace and a new context. And here's an example. So given one program in our language like this, there's one click followed by a loop statement. We will evaluate as following. So given an initial web page pi 0, the first statement click will be evaluated on pi 0 and output some web page pi 1. And evaluating the second statement, the loop will start to iterate through a list of items. And within its body, we will continue on pi 1, output some pi 2. And at some point, we will stop and output some web page pi n. All the actions being acted will be recorded as an output action trace. And most importantly, you may notice that there exists a data dependency. So that is, one statement has to be executed under the context that is computed by evaluating its previous statement. So therefore, when we are evaluating programs with local variables in this domain, in other words, the loop procedure, we may again have the chicken and egg problem. So let me put up the previous program from the last slide again. So when we are evaluating the loop, when the first iteration starts, we will start on some input web page pi 1 with a binding of the first, bind the local loop variable to the first item of the list. After the first iteration, we'll get some web page pi 3. And when the second iteration starts, we will continue on pi 3 with a new binding. So that is, one iteration also has to be executed under the context from its last iteration. So similar to the fold function example, we may not be able to reduce the space without considering the local context. So to address this issue, we applied lifted interpretation in web automation, which is to use trace semantics to create this context output pair to represent those equivalence classes of the subprograms. In this way, we build equivalence classes and evaluate programs simultaneously to reduce the space. And the whole procedure will be very similar to the one with the fold function. And we don't cover very detailed rundown, so we will recommend to you to read the paper for detailed algorithm in this application. So for evaluation, we used a set of 131 real-world benchmarks in web automation domain. And we implemented our approach in an artifact called Arborist. We compared against two other baselines where web robot is the state-of-art technique in web automation domain. And for setup, our goal is to ask the synthesizers to find one program within a 1 second time limit set for interactive program synthesis. So the result shows that our artifact can solve 93.9% of the total benchmarks, which is significantly more than the other baselines. And worth to mention, on the newly collected and generally more challenging benchmarks, we can solve 2.5 times more and use 6 times faster time than the state-of-art technique. So here's the final page for takeaway. We proposed lifted interpretation, which is to interpret all programs from top down and construct equivalence classes of subprograms from bottom up. In this way, we can efficiently reduce the space of programs with local variables. And we outperform the state-of-art technique to solve more benchmarks and use that time on the web automation benchmarks. We're now open to any questions. Thank you.
Nice talk. So you evaluate on the web automation, but there's probably a lot of domains where you have things like side effects or loops or where this might be useful. Any plans to, expand onto other domains?
Yeah. So good question. So in this work, we only applied on web automation domain. So that's the only evaluation we did. But the message we want to convey, including using a small toy language for demonstrating our approach, is that our approach can be potentially generalized to any programs with use of local variables. And well, worth to mention, the programs with data dependency is something that's a very interesting case, but our approach is general, and we hope there's can be more opportunity for evaluation.
Thank you for the great talk. I'm wondering whether, like, what would happen if you try to do local variables that are not defined by the higher order function? Could you handle assignments or maybe even arbitrary fresh variables, or is it going to stop you from terminating?
So our approach is general to all programs with local variables. So actually, we don't care about data dependency or like fold left or fold right, or whether it's a for loop. So like in our web automation evaluation, we have actually two types of loops. One that's looping over a spreadsheet data column, and another is actually looping over the selectors on the website. And we also have a while loop, actually. So it's like general to any sort of structure with local variables.
But do you need to know them in advance, or can you also do fresh variables when you enumerate?
Oh, so I believe we do need to know the variables. So it's like a lambda, you need to know the variables.
Makes sense, thank you.
Yeah.
I have a question. So when you are using this data dependence analysis, how difficult it is for this particular domain, and what are the problems you see for the other domains in this case?
So we don't actually do analysis in the technique, but if you are talking about the complexity of the web automation domain, then we believe it's quite challenging because basically there is dependency everywhere. So we have to know the web page of the previous action to do the evaluation for all the other subsequent statements. So it's sort of like a very good domain to evaluate our technique.
Okay, if there is no other questions, let's thank the speakers. So our next speaker is Stephen Mell, and he will be presenting optimal program synthesis via abstract interpretation.
Can you hear me okay? All right. I'm Stephen. I'm going to be presenting some work that I did with my advisors, Steve Zdanswick and Osbert Bastani, on optimal program synthesis via abstract interpretation. So to start off with, there's been a lot of recent interest in using program synthesis for data science, like end-user programming sorts of tasks. And so for instance, biologists often have a lot of video of animals, such as mice interacting, and they might want to identify when the mice are engaging in certain behaviors. Or a fisheries regulator might have a lot of vessel tracks, and they might be interested in looking for suspicious behavior that might be indicative of illegal fishing. Or an autonomous driving engineer might have video of a traffic camera and might be interested in rare driving behaviors that they need to account for. So focusing on this example a little bit, suppose I'm an autonomous driving engineer, and I've taken many hours of video from this traffic camera, and I've run an off-the-shelf object tracker. And I've gotten these tracks that I've put in red. And maybe, as an example, I'm interested in finding cars that make this particular turn. Like, how would I go about doing that? How would I go about bringing them out of all of these? Well, I might sort of draw these two lines in blue and in green, and I might sort of say the cars I'm interested in are the ones that at first are in the blue lane, then anything happens while they're making the turn, and then they're in the green lane. But really, I've just drawn two lines, so I can't say that. I have to say something more like the distance between a car and the blue line is less than some threshold theta 1, and then anything happens, and then the distance between the car and the green line is less than some threshold theta 2. And this is a challenging problem, because even if I'm an expert, I can't necessarily just like look at the video and say, oh, it's like 20 pixels is the right threshold. So how would you do it? One thing you could do is you could synthesize these parameters. And for good measure, we're just going to synthesize the entire programs from labeled data. So we have a set of, in this case, trajectories of cars, x, a set of human labels, y, and we're trying to find a program such that when we evaluate the program on each trajectory, we get the human label. There's another problem, though, which is that if this is labeled by a human, you might make mistakes, and the data is very fuzzy, and so it may be impossible to actually do perfect classification. So instead, we want to do optimal synthesis, where we have some objective u, say accuracy, or in our implementation and in practice, you might use something like F1 score. And we're trying to find a program P that maximizes the accuracy, for instance, of its predictions. There is other work in this area. There is some work called NEAR, which use gradient-based optimization methods on this problem, but it doesn't have any optimality guarantee. And there's prior work on optimal synthesis using SMT solvers, but that work isn't really focused on these sorts of objectives. It's focused on rather different sorts of objectives, and we compare to this work. So in our work, we're trying to find an efficient, optimal solution to this optimization problem, and we do so by using abstract interpretation to construct a search heuristic. If you're familiar, this is actually an admissible A-star search heuristic, but it's OK if you're not familiar with that. So in the rest of this talk, I'm going to review the sort of standard technique of enumerative synthesis. I'm going to show our algorithm, including introducing notions of generalized partial programs and abstract semantics. And I'll show our implementation on two different existing domain-specific languages, and finally an evaluation showing orders of magnitude speed up over the SMT-based approach. So jumping into a concrete example of a synthesis task you might want to solve, suppose I have two car trajectories, x1 and x2, and each one's a sequence of frames. So maybe x1, on the first frame, the car is 0.75 from the lane. It also has some velocity, some acceleration. There are subsequent frames where maybe the distance is 0.5. You have another trajectory. And I, as a human, have labeled the first one true, an instance of the behavior, the second one false, not an instance of behavior. So the language that I'm going to be using here is sort of like regular expressions or temporal logic, where you might have predicates like the distance is less than theta or the distance is greater than theta, where here theta are real numbers between 0 and 1. You might also have conjunctions, disjunctions, or sequencings of these programs. And for concreteness, I'll be focusing a lot on programs of this form, where the distance is greater than a threshold, and then the distance is less than a threshold. And so the semantics of these sorts of programs are that they map trajectories to Booleans. And so for instance, maybe if we have the parameters 0.2, 0.1, the semantics on the x1 are false, and maybe on x2 it's also false. So now we have our predictions. And so now we have our objective function we're trying to maximize, and that's a function of the predictions, which is sort of Boolean to the n, and it maps those to a real number. And so for instance, accuracy of some predictions y prime with respect to ground truth y are just the number of places where these labels agree divided by the size of the data set. And so if we're evaluating the accuracy of this particular program, we know that it outputs predictions false, false, and while those differ from the ground truth on x1, it was supposed to be true, but agree on x2, and so we get accuracy 1/2. So to reiterate, our goal here is to find a program that maximizes the accuracy of its predictions on the data set. So how would you typically do this? A standard approach would be using enumerative synthesis, where you have your grammar, and you actually augment that grammar with a whole, which I'm writing question mark, question mark. So these are our partial programs. And now you can form a search tree, where the initial node in the search tree is just a whole, and then the children of each node in the search tree are what you get if you fill that hole with productions from the grammar. So for instance, you might have distance less than some threshold, or you might have whole and whole, or whole then whole. You can kind of continue this process until you get down to this example we saw before, where we have distance greater than some number, and then distance less than some threshold. The sort of programs beneath this can be parameterized by this unit square of parameters, theta 1 and theta 2. And so one thing you could do, you could just sort of do a grid search. You could just pick a dense grid of points. And now you have concrete programs, so you can evaluate them. So for instance, maybe if we have point 0, 0, we'd get the predictions false, false. We already saw the accuracy was 1/2. You could continue that. Maybe eventually you get some different predictions, say false, true. The accuracy would actually be 0. You continue until maybe you get accuracy 1. And then you've evaluated all these programs. The challenge here is this is a really high branching factor for our search. Like this was a branching factor of 100, and we can't really say usually for sure that we're done until we've considered almost every program in the space. So we want to do better than this. And the key insight here is that partial programs represent nested sets of concrete programs. So what do I mean by that? Well, this whole sort of represents the set of all programs, whereas distance less than whole represents all the programs that are distance less than followed by some concrete number. Or conjunction and sequencing of wholes are all the programs that begin with a conjunction or begin with a sequencing. And these sets of these children, they actually form a partition of the set of their parent. So these are all the possible ways that you could fill that first hole. And you can also sort of drill down all the way to a concrete program, and you find that this path is a decreasing sequence of sets that converges to a concrete program. So if we focus on this area that was causing us trouble with the high branching factor, what we're going to do is, rather than branching directly to these concrete programs, we're going to use some sort of interval-constrained hole, which will give us more structure on our space. So in particular, we'll introduce a new construct to our partial programs, which is that of a bounded hole. And what that's supposed to represent is just all the programs you get by filling that hole with a number inside the interval. But this sort of lets us have a more structured space, because now rather than branching 100 times, we can divide the space into, say, 4 quadrants, for instance. We kind of do some kind of bisection in 2 dimensions. And so now, say, this first node would represent all the points between 0 and 1/2 and 0 and 1/2, and similarly for the other ones. And just like before, these children are a partition of their parent. The 4 quadrants partition this unit square. And we can also sort of iterate the process where each of these regions can now be subdivided into 4 subregions. We continue until we get arbitrarily close to a concrete program. But now that we have these constrained holes, we might hope to be able to do some pruning on the search space. In order to do that, we're going to evaluate these programs, which these generalized partial programs I'll call abstract programs. And for concreteness, we'll consider Q sharp, sharp as in it's an abstract program rather than a concrete one. And where before the semantics of programs were Booleans, now the semantics are going to be abstract Booleans. So false, true, or top, where top represents sort of non-deterministically false or true. So now the semantics, rather than returning Booleans, is going to return abstract Booleans. And now if we evaluate Q sharp, we might see it predicts false on the first trajectory, and it returns top on the second trajectory. So our objectives before mapped a set of Booleans to a real number. Now we're going to map these abstract predictions, these abstract Booleans, to an abstract real number, where the abstract real number is, for our purposes, just a real interval. So we had accuracy. We need an abstract notion of accuracy. In this case, I'm just lifting all of the arithmetic operations to be some kind of interval version of themselves. And finally, we consider the abstract accuracy of the abstract program Q sharp. And here we saw that the predictions were false and top. Well, it output false, the ground truth is true, so we definitely got the prediction wrong on x1, but we outputted top for x2, and so we sort of said we don't know. And so the accuracy definitely isn't 1, but it could be anywhere between 0 and 1/2. And the guarantee that we actually have is that for any concrete program inside of an abstract program, the accuracy of the concrete program is going to be contained in the abstract accuracy interval of the abstract program. And so now what this is going to let us do is it's going to let us use the upper bound of this abstract accuracy that we get out of the abstract semantics as a search heuristic. So in particular, we take the upper bound, the supremum of this abstract accuracy, and this will let us prioritize the more promising areas of the search tree. So if we're back here, what do? Well, we evaluate our abstract semantics, we compute our abstract accuracy. Because it could be any point in this parameter space, unsurprisingly, we would return top for an abstract accuracy of 0 to 1. So considering that upper bound and plotting it over here, we'd see, well, all the points, all the concrete programs in this blue region have accuracy at most 1. That's not that informative, so we'd continue search. So then if we consider this one, we might output false top. And we already saw that the abstract accuracy there was 0 to 1/2. And so now we know that all the points in this purple region achieve accuracy at most 1/2. We could sort of continue. We'd see these regions are also at most 1/2. This last region, well, it outputs the prediction false for x2, which is correct. So its abstract accuracy is going to be between 1/2 and 1. And so now intuitively, it sort of makes sense that we should pursue this region first. It could be that the optimal program lies in the purple region, but that's only true if the best accuracy we can get is only 1/2. Whereas as far as we know, you could have something better in the blue region. So we could expand that. We could compute the abstract accuracies. And in this particular case, we'll see that we have these two blue regions with abstract accuracies 1 to 1, which guarantees us that any point we pick in those regions is going to have a concrete accuracy of 1. So in fact, in this case, we know we can just pick anything from those regions, and we're done. We've found the optimal solutions, and we don't even have to consider the rest of the search space. So this is our algorithm. We implemented it on 2 different domain-specific languages, the first of which is from some prior work called Quiver. This is actually the language that I was just showing you. It's sort of regular expression or temporal logic style. There's prior work called Near, and they have a DSL that's much more map-fold style, where they manipulate lists. And finally, we consider the F1 score objective instead of accuracy. This is a more realistic metric that's used in classification tasks. But the naive abstraction you come up with by just looking at the arithmetic formula and plugging in abstract transformers there doesn't actually work well, and we're able to derive a better abstraction. We evaluate on these 2 different languages, and on the Near language, we use their data set, which has 2 mouse behavior classification tasks. On the Quiver language, we have 6 mouse classification tasks and 10 traffic classification tasks. We compare our approach to the SMT-based approaches, as in metasketches. We consider how the time it takes to find the optimal program changes as a function of data set size. These plots are log. Our approach is in blue. As you can see, we do several orders of magnitude better than those approaches. We also consider the ablation, where we use breadth-first search instead of a heuristic, and find that the heuristic search is indeed important. So to conclude, in this paper, we efficiently find an optimal solution to this optimization problem by using abstract interpretation to construct an admissible A-star search heuristic. This happens over a space of generalized partial programs, and it's orders of magnitude faster than prior SMT-based optimal synthesis approaches. And we evaluate on 2 existing DSLs for data classification. So, thank you, and I'd be happy to take your questions.
Hi.
Hi.
Nice talk. So if it terminates, then you will have the optimal solution.
Yeah.
What if it does not terminate, or if you have some time budget, you have to stop, then?
Yeah, it's actually very conducive to some sort of online thing, because you have your search frontier, and for every item in that frontier, you have abstract bounds. And so you indeed get a lower bound as well. So in fact, in the experiment I didn't show, we do sort of have that, where you can kind of, over time, terminate early, and you'll at least have some sorts of upper and lower bounds.
Thanks.
Hi. So your initial motivation was more like an unsupervised learning problem, in the sense that you might want to look at abnormalities of some kind.
Yeah.
I'm sorry.
Or, no, go ahead.
So I was just wondering whether you have any ideas on how I could just find anomalous behavior by not giving any information at all.
So we do consider supervised learning just like the very small data regime. So in all this, we sort of assume that Like in some of them, there are like 2 labeled positive examples from a user and 10 negatives. So it is supervised in that sense. It's just like synthesis makes it very data efficient, and that's important. In terms of finding anomalous behavior, I think there's probably a whole literature in machine learning for that, and maybe this could be plugged in there, although I haven't studied that myself.
Okay, thanks.
Hi, great talk.
Thanks.
So do you have any issues around either loss of precision from the abstraction in the interval domain, and or kind of limitations due to kind of the dimensionality growing? I think if you're doing this kind of partitioning, it might not scale very well beyond a few dimensions.
Right. So I guess one thing that I maybe didn't emphasize is you can kind of plug in any abstract domain from abstract interpretation you want here. We did, in our experiments, use this bisection domain that I showed. And because the programs we were synthesizing didn't have that many parameters, it actually worked like fairly well. But I mean, definitely there are still scaling issues to any of these things where you're dealing with these exponentially large spaces. Yeah, and I mean, one thing that's important is that your abstraction be like fairly good. If your abstraction is too loose, you just sort of degenerate to breadth first search because your upper bound is trivial. And so that, I think, is maybe a point where it might be tricky if you're trying to adapt to a new domain, is you have to make sure that your abstractions are sufficiently tight.
Oh, hi. So in your example, you kind of split your interval in half. I guess that choice of splitting, I was just wondering, in other domains, there's like different ways you can split. Like maybe you split, yeah, you might use a gradient-based thing to split based on that. I'm just wondering, how do you choose, I guess, maybe any insight on why that works particularly well as opposed to any other kind of choice of partitioning?
I think like, if you don't know anything else about your parameter space, like if you have a prior distribution, you might want to do something like split in half based on probability mass. In this case, we didn't have anything like that. We just basically had a square, and in some sense there, the simplest thing is this like binary splitting. But yeah, if you have other knowledge, you might want to split differently. You could split into different numbers of things. And indeed, you don't have to use these kinds of square abstractions. You could definitely use, I mean, I haven't actually implemented it or evaluated it, but at least theoretically, you could use something like vector space abstractions or polytopes or something like that.
So I have a question here. So when you selected the benchmarks for this neuro-symbolic programming, what was the kind of properties you considered in this kind of domains? And is it applicable in the same way for the other domains? Do you have any study here?
I guess the sort of important properties are the ones that make it work particularly well are first of all, like you need some kind of large space probably of constants. And so for instance, these real parameters are like a very good use case for that. And the other thing is you need to have like some quantitative objective you're trying to optimize. And so I mean, a lot of synthesis tasks you're trying to satisfy a correctness specification. I mean, this would be really degenerate. It would kind of work, but it would just be true-false. You'd just be rediscovering like deductive pruning. And so I think the things we've been considering are ones where you have these like real valued constants basically, and this quantitative objective that you're trying to optimize. I don't know if that answers your question. Thank you so much.
If there is no more questions, let's thank the speaker. The session ends here. Thanks everyone for nice questions and attendance, and all the speakers for the great talks. Thank you.
Okay, so the first talk is on soundly handling linearity. It is also a distinguished paper award, and Weng Hao will tell us more about it.
Yeah, thank you. So, hi, I'm Wen Hao. I'm a PhD student at the University of Edinburgh.
Mike?
I'm going to talk about how to soundly handle linearity, and this is joint work with Daniel, Sam, Garrett. Okay, so linear types is a very useful feature. It guarantees that something must be used exactly once.
Can one turn the mic higher? Could you also move the mic closer to?
Hello, hello.
No, it doesn't seem on.
Hello. Yeah. Okay, so linear types is a very useful feature. It guarantees that something can only be used exactly once, and it's used in some real-world languages and some research languages. Effect handlers is another very useful feature. It allows us to define and compose a wide range of computational effects, and it is used in some real-world languages and some research languages. And Linux, a research language mainly developed in Edinburgh, has both these features, but Linux is broken because linear types say that I guarantee something is going to be used exactly once, while effect handlers say that I give you first-class continuations, and you can use them anytime you want. So my talk is about how to make them happy with each other. So we first take a closer look at the problem in Linux. Linux uses linear types to implement session types. For example, we can write a sender function. It takes a channel endpoint C, which has type boundInt.end, which means send a value of type int and then end the communication. And we use the send operation to send 42 on the channel C and close the remaining channel C prime. We can write a receiver function, which takes a channel C of type !int.end, which means receive a value type int and then end. And we can use the receive operation to receive an integer I from the channel endpoint C, closes remaining channel endpoint C prime, and print the integer I. And we use the fork to collect the sender and receiver. So the 42 is sent and received and printed. Okay, linear types are solved in Linux. It is really hard to break it. For example, if we have a linear endpoint C and we use it twice by passing it to sender twice, we get a type error saying that we can't use a variable of linear type twice. If we try to capture it in a function and use the function twice, we get another type error saying that we can't capture a linear variable in a nonlinear function. And if we capture it in a linear function, well, obviously we'll get another type error saying that we can't use a linear function twice. So, well, yeah, it is very hard to break safety of linear types, but it is not impossible with the help of effect handlers, which give us a very flexible way to manipulate the control flow. For example, we can write a non-deterministic printer. It uses the choose operation to decide whether to print 42 or 84. And in the function type, we have an effect type, which contains the operation label choose and its signature unit to bool, which means this operation takes no parameter and returns a Boolean value. And we can write a handler for it in Linux. Here, the variable r is the continuation of the choose operation, and we invoke the continuation once with value true, so 42 is chosen and printed. We call this a one-shot handler because the continuation r is used only once. We can also use the continuation r twice, so both 42 and 84 are printed. And this is a multi-shot handler. This is a multi-shot handler, and we can use it to break the safety of linear types. So this is the same receiver function as we have seen before, and we can write a non-deterministic sender it uses the choose operation to decide whether to send 42 and 84. And if we handle the choose operation using a multi-shot handler by invoking the continuation twice, we'll get a runtime error saying that there is some channel not found. And this is because the continuation of choose captures the channel endpoint C, and during the first invocation of the continuation, the channel C is already closed, so we can't find it in the second execution of the continuation. So this has been a long-standing bug in Linux. It is first mentioned in this issue, opened in 2019 by Daniel. And so we want to fix this by tracking a new notion of linearity called control flow linearity. Okay, so before we get into control flow linearity, let's revisit what is value linearity. It restricts how we can use a value, or it characterizes whether a value can contain some linear resources or not. In a call calculus, which we call FF-POP, we define linearity as either a circle, which means linear, or a bullet, which means unlimited. And we track the linearity of value types using their kinds. So an int is an unlimited type, and a session type is a linear type, and a pair of a session type and int is also a linear type. And a linear function whose function arrow has a circle on it is also a linear type. And on terms, we also need to allocate lambda abstractions with their linearity. So here, the second lambda abstraction is allocated to be a linear function because it captures a linear variable C that is bound outside. And then, well, we have the same problem as in Linux because we only track value linearity. And this is exactly the same program as the non-deterministic sender. So the highlighted part is the continuation of truth, and it captures a linear variable C. And if we handle it using a multi-shot handler by invoking the continuation R twice, it is well tapped, but we actually abuse the linear variable C. So to resolve this, we need to try control flow linearity, which restricts how many times the control may enter a local context. Or it characterizes whether a local context can capture some linear resources or not. So for example, for the non-deterministic sender, the continuation of truth is a control flow linear local context because it captures a linear variable. And we track this information in the effect type. The truth is annotated as a control flow linear operation, which essentially means that the continuation of truth is control flow linear. And on the terms, we also annotate net bindings with the control flow linearity of the local context is introduced. So for the first net binding, the local context is introduced is exactly the continuation of truth, and it is linear because it captures the linear variable C. And for the second one, it is also linear as it also captures C. And for the last one, it can be unlimited because it does not capture any linear resources outside. Yeah, so now we are done. We tracked the control flow linearity for the operation truth. And then if we want to handle the truth operation using a multi-shot handler, we'll get a type error because now we know that truth is a control flow linear operation. So the continuation function R is going to have a linear function type, which cannot be used twice. Okay, so we have the linearity annotation on operation signatures, and we lift them to the whole effect type. One thing worth mentioning is that there is a subcanding relation between the kinds of effect type. It is from control flow linear to control flow unlimited. And this is intuitive because say that you have some control flow linear operations. They guarantee the control may only enter their continuation just once, so we can use them in any context we want. But for values, the subcanding relation is actually the reverse because say that if we have some unlimited values, we can use them exactly once. So there is some kind of duality between control flow linearity and value linearity. And this is essentially because value linearity tells us something about values themselves, while control flow linearity tells us something about the continuations or the context of some operations. Okay, so that's how it works in FFPOP, and we have implemented it in Linux. This is the previous program with a runtime error. And after checking control flow linearity, it becomes a type error, seeing that we can't use a linear variable twice. So yeah, it needs some annotations, but that's, well, okay. And yeah, and it is merged in the main branch of Linux. So we can now, close the issue and I'll close it. Okay, yeah, that's very good. We have fixed the bug that is from 4 years ago. But are we satisfied? Well, not really, because we still need some term annotations on the syntax. So for example, if we consider this function, it is almost the identity function, but it prints 42 every time. And in FFPOP, you can give it 10 different types, and none of them is the most general one. This is very annoying. So we proposed another call calculus called QFPOP. It uses qualified types to combine all these 10 types into only one type with a constraint. And it also supports effect subtyping. What's interesting is that we found effect subtyping is very useful to make the tracking of control flow linearity more precise. If you want to know why, ask me later. Yeah. Okay, so that's all. We have more things in the paper. We have the formalization of these two call calculus. One thing worth mentioning is for QFPOP, we use qualified types to do both linear types and effect types based on some previous work. And we have a type inference for it, which does not require any annotation at all. Yeah. Okay, so and my takeaway is consider checking control flow linearity if you want to have both linear types and effect handlers in your languages. Thank you.
Oh, his mic is still not working. Can someone check that it's on for a start? One of the student volunteers? Or someone? No, it's definitely not working. Can someone turn it on, maybe?
Keep that mic with the speaker.
Okay.
So I heard about some prior work by Olivier Donvy, back to direct style, where he observes that if you convert a term into continuation passing style, the continuations are used linearly after the transformation. And such terms can be converted back to direct style. I'm not sure if the notion originated with him, but it sounds to be related because the continuations, of course, are functions, and they're typed linearly after the transformation. So is there a connection with your notion of control flow linearity?
Yeah, I think they are related, since a control flow linear continuation is essentially a linear function. But I guess one difference is we also use the terminology control flow linearity for operations, which refers to the linearity of their continuation function.
So yeah, we have time for question. I guess if no one asks, we'll take a break to synchronize. You can also ask via Discord, but I don't think we have questions there either. Oh, okay. How do we do that? And you repeat it, yeah?
Are you allowed to discard the linear continuations, or is it affine, or is it actually linear?
They are linear, yeah. They are not affine, yeah, but it is. Oh, the question is, are the continuations linear or affine? And in our current formalization, they are linear, but it should be standard to extend it to affine types. Hello. Oh, yeah, it works.
In the meanwhile, it seems we solved even the mic problem. So if there are no more questions, I guess we can thank the speaker again. Minutes, right? Okay. Okay. With the previous speaker. So this is for whom? For me? The speaker has it? For the speaker.
Oh.
Yeah, we anyway need to wait. So, can you take this off?
Oh, sorry. Thank you. Oh. Is it right?
It seems to work. Yeah, we need to wait to synchronize with the other session. So we have 1 more minute. Okay, so the next talk is on answer refinement modification, and Fuga will tell us more about it.
Okay. Hello, I'm Fuga Kawamata. Today, I'm going to talk about our work as a refinement modification, refinement type system for algebraic effects and handlers. So first, let me introduce 2 things, algebraic effects and handlers, and refinement types. So first, algebraic effects and handlers are mechanisms to structure programs with effects in a modular way. They can represent many kinds of effects, such as exception, state, I/O, and so on. And in algebraic effects and handlers, effects are represented by special terms called operations, and they are handled by handlers. So let's see how algebraic effects and handlers behave with this example. Here's an example, and it has 2 operations, tick and tock. And they are handled by the handler H. In the evaluation, first the operation tick is handled, and its continuation, this yellow part, is captured.
and it is bound to the variable k in the close for tick. And then the handler replaces this captured handling construct with this expression, 1 cons the continuation. So this example evaluates to this one, and the continuation moves here, and the argument unit is embedded into the whole of the continuation. And next, the operation talk is handled, and the continuation is captured. Here, continuation is delimited at the nearest handling construct. And then, according to the cause for talk, it evaluates to this one. And finally, the unit value is handled by the return clause in the handler, which returns an empty list. So the program returns a list with 1 and 0. And as for types, the type of the handling construct is determined by the types of the clauses in the handler, because this handling construct will be replaced with one of these clauses. So here they all have the type int list, so the handling construct also has the type int list. And as more example, these programs which have different body expressions also has a type int list because they are handled by the same handler. And next, let me introduce refinement types. Refinement types are types endowed with predicates. For example, 1 plus 2 can have this, the first refinement type, and which states that the expression to be typed is exactly equivalent to 3. And also, 1 plus 2 can have the different refinement type in the second line, which represents the positive integer type. So refinement types can represent more specific properties than ordinary types. So they can be used as a tool of program verification. And so our main contribution is that the development of a refinement type system for algebraic effects and handlers. So with our system, we can type this previous example with the most precise refinement type. That is the type of the list with 1 and 0. Our type system enables precise verification of algebraic effects and handlers, and it can be built on top of existing languages. In fact, our implementation takes programs written in OCaml5, which has built-in effect handlers. But the construction of our type system was not easy. One challenging point is that naive addition of refinement types to ordinary type systems does not work well. So consider these programs again. And when we naively extend the types with refinements, this will become like this one. And for program verification, we want the most precise type of these 3 programs. And since they have different body expressions, they return different values. So the precise refinement type should be different. But in this naive approach, they all have the same refinement type because they are handled by the same handler. So that is, this naive approach is not aware of the structure of the body expressions. So we cannot distinguish the types of these programs. So to solve this problem, in our approach, we have adapted a concept called answer type modification that comes from studies of delimited coordination. So then what are answer types? Answer types are types of contexts or return types of continuations. In languages with algebraic effects and handlers, answer types corresponds to the types of the closest outer handling constructs. So consider this
expression where the expression E is surrounded by a handler-free evaluation context F, and it is handled by the handler H. Here, H is the closest outer handler for E. So the answer type of E is the return type of this yellow handling construct. And in ordinary type systems, answer types corresponds to the return types of these captured continuations. They all have the same answer type because they are handled by the same handler. However, when we consider refinement types, actually, answer types may be modified by operation calls. So let's see how the answer type is modified in this example. First, we focus on operation talk. The continuation captured by talk is this yellow part. These two are the same one. And its type is this one, because when it is applied to a unit value, the unit value is handled by the return clause, which returns an empty list. However, when the operation talk is embedded in the whole of the continuation, this returns a singleton list with 0. This can be explained as follows. First, this yellow continuation is bounded to the variable k in the clause for talk. So the type of k is this one, which is the same as the type of the continuation. And then this expression in the clause for talk should have this blue type, the type of the singleton list with 0. And this corresponds to the type of the handling construct, this one, because this handling construct is replaced with the expression in the clause for talk by the handler. So in other words, embedding the talk in the continuation changes its answer type. This is called answer type modification, or ATM. And especially here, only the refinement is changed. So we call this answer refinement modification, or ARM. And the yellow one is called initial answer type, and the blue one is called the final answer type. Then how about the ATM or tick? The captured continuation is this yellow one, and in fact, its return type is the same as the final answer type of talk, because the handling construct in the second line and handling construct in the third line is semantically the same. And so the initial answer type of tick is this yellow one. And in the same way as before, the type of the variable k in the clause for tick is this one, and the expression in the clause for talk has this blue type, that is the type of the list with 1 and 0. And so tick changes its answer type to this blue type. And actually, this blue final answer type corresponds to the type of the program itself. So by tracking the change of answer type, we can obtain the most precise type of this program. And so formally, ATM is tracked with this type syntax. T is a type for value, and C is a type for an expression. And important point here is that when an expression changes its answer type, its type should be in this form in the last line, which specifies its initial and final answer types. And this sigma is a kind of a type of handler, but I omit these details here. So with this type syntax, we can type the previous example as follows. First, from the definition of the handler, we can give these two types to the operations tick and talk. They have the information of their ATMs. And here, the final answer type of talk is matched with the initial answer type of tick. So these ATMs can be composed into this one. And this is a type for the body expression, where the initial answer type is 01 is the same as the type of the return clause. And finally, we can use the final answer type as the type of the handling construct. And also, this process can be viewed as backward reasoning on continuations. That is, first we start from the empty continuation, and it has this yellow type because the return clause is executed at the end of the continuation. And next, we extend the continuation by prepending the operation talk, which changes the answer type to this green one. Similarly, we extend the continuation with talk, which changes the answer type to this blue one. And finally, the continuation has become the entire program itself. So this blue final answer type turns out to be the type of the program. And formally, such reasoning is realized by these typing rules of our type system, but for more details, please see our paper. And finally, I show some typing examples. I will show only the top-level types of the programs, but typing derivations of similar programs are explained in our paper. So first, the first program is the program of a mutable state, where the handler implements the behavior of the state in a manner like a state monad. And the second one is the program of non-determinism. Operation decide. The operation decide represents the non-deterministic choice, and the handler returns the maximal result of the non-deterministic results. And our type system can give these most precise types to these programs. So we can verify that the first program returns N1 plus N2, and the second one returns the greater one of N1 and N2. And so far I showed the basic mechanism of our type system, but in the paper, we also show a more sophisticated type system with some advanced features and prove its type safety. We also present the implementation of our type system with ATM. Also, we argue about another way of refinement type verification of effect handlers via CPS transformation. For details, please check out our paper. That's all. Thank you.
Okay, we have time for questions. Sam will start.
Hi, this is very nice work. Thanks for the talk. Do you have, what kind of results do you have regarding type inference? Do you get principal types in your implementation on top of OCaml5, for instance?
For type inference, it is difficult to, we don't know the principal type can be derived. So, but yeah, our implementation infers the type using constraint solving. So, yeah.
Thank you.
We've got a question from the Discord. Effect handlers come in two variants, deep handlers and shallow handlers. Can this work be adapted to both variants of handlers? Brackets, same types, different typing rules for handlers.
Yeah, and our system uses deep handlers and yeah, shallow, but our method can be used for also shallow handlers.
Hello. Very good work. Very nice work. I would like to ask, perhaps I don't understand correctly, but so this is built on top of OCaml5, but OCaml5 doesn't have any effect system, so there's no effect signatures whatsoever. But what does this? Does this embed such a type system with refinement types and effect types on top of OCaml5? So it's like, or is this another language embedded in OCaml5?
Sorry, could you repeat again?
So is this work, is this creating a type system with refinement types and effect signatures and effect types on top of OCaml5? Or is this an extra language that you build on top of OCaml5?
For implementation?
Yes.
Oh, implementation. Implementation first, we infer the types without refinements using OCaml library, and after that, using that types without refinements, we our implementation infers the refinements.
Right, so this work, you can use it to reason about, for instance, OCaml programs with effects.
Sorry.
You can use this type system to give precise types for programs written in OCaml with effects.
Yes.
Right. Okay. It's not just a language. Yeah. Okay.
Got another question from the Discord. What fragment of OCaml5 do you support? And do you know how to CPS translate OCaml?
Sorry, could you repeat again?
What fragment of OCaml5 do you support? And another question with the same question. Do you know how to CPS translate OCaml?
Oh, sorry, once more again, sorry.
What fragment of OCaml5 do you actually support? And do you know how to CPS translate OCaml?
No, for the first one, and we support some parts of OCaml features, such as functions, recursive functions, pattern matching, or like so. The features frequently used one. And for second questions, the CPS transformation we define is not for OCaml, but generally I think OCaml program can be CPS transformed. Thank you.
Okay, do we have more questions?
So very nice talk. I'm curious about are this answer refinement modifications highly depend on how the implementation of the handler. For example, you have this non-deterministic choice handler. You first feed the true, second feed the false, and when you first feed the false, second feed the true, that will reflect to the type of your answer modification.
So, please repeat the last part again.
I'm just curious about because it's for one, if for operators, there's different implementation versions. For example, you can first feed the true, then feed the false, or you do that reversely. Is that your answer refinement modification will reflect this implementation details?
Yeah. When the operation is used twice, then if these two operations is handled by same handler, we can distinguish these answer types of these two operations. But when the handler is different one, and our system cannot we don't know that about it, so it may be possible, but we think it is difficult. So I think that's interesting future work. Thank you.
Okay, thank you.
Yeah, so I think the other authors also had something to add, but let's discuss that at the break. Let's thank the speaker again.
Thank you.
Mike, you still have the mic? Yeah, I'll get it. No worries. Could you put it on the screen side? Your right or middle? Yeah. Okay, so as soon as the slides show up, can you put the mic higher? On your right side? Your right side? Okay, so the next talk is on effectful software contracts, and Cameron will tell us more about it as soon as the slides show up.
I can try start and restart, yeah. Good start.
Go for it.
Thanks. All right, so my name is Cameron. I'm going to be talking about effectful software contracts today, which is work done with Christos Demoulas and Matthias Fleisen at Northwestern and Northeastern, two different places, very important. So this is an effect handler session, but not a contract session, so I maybe want to give a little bit of a background on contracts before we start. So one maybe broad question is, what are contracts about? This is a question probably anyone who studies contracts is going to give you a different answer. I will give you one possible answer, which is contracts are an approach to specification, which takes the philosophy that specifications are code. Okay? So here's a concrete example of that. Suppose you're writing a cryptographic library. So say for generating RSA public-private key pairs. And it's a function that takes in a func that's going to give you a pair of random prime numbers and gives you back a func that's going to generate key pairs. Okay? So here's a bit of pseudocode for the contracts for that function. And you don't have to read the whole thing, but I want you to pay attention to this part here. Is prime, okay? So in the contract world, this is just a regular predicate from the host programming language, okay? And it may come from the math library, and the programmer can just use that normally. And this is really quite convenient. We get a really expressive specification that's easy to write down, and get to reuse code that is in the host language. So of course, this is a bit of a trade-off compared to a type system. So typically in contracts, we're checking these things at runtime. But it's really easy to express very rich specifications. Whereas in a type system, you may have slightly less rich specifications, unless you go to a more sophisticated type system. But you get those statically. So for the rest of the talk, I'm going to assume that we'll be checking these at runtime, although there are certainly ways to check contracts statically as well. OK, so that's a bit of background. So is prime is code. And of course, code can have effects. So that means contracts can use effects as well. And we might just try to ignore that and say, oh, well, maybe that's not that useful. Or it might end up using them accidentally.
But actually, in this paper, we're interested in contracts that use effects intentionally. And it turns out that it's actually quite useful to use effects in contracts. And we did a bit of a literature review, and we found actually quite a few papers that did so. So what's an example of a contract that's going to use effects intentionally? Here's one example from a paper from quite a few years ago about doing interop between two languages. You can imagine ordinary ML and a variant of ML that has an affine type system. Okay, and you want to do sound interop between these two languages. Okay, so to do sound interop between the two languages, you want to make sure that when you have values that flow from the ordinary ML to affine ML, that it's not going to violate the invariance of your type system. So you want to ensure that if you have a function that goes from ordinary ML to affine ML, that you're going to use it at most once. And that requires a dynamic check of that property because, well, this is an interop setting. Okay, and in this scenario, that dynamic check requires state because you have to keep track of whether or not you've applied the function in the past. So you have a bit of state that's going to keep track of that. That's an effect. Okay, so that's one example of where you might use effects in a contract. And there's a bunch of others. And actually, there's probably more than what we've found here. This is just a selection that we considered in this paper. Okay. Now, people have done implementation work. They've studied specific instances of contracts that perform an effect. But what about a theory for this? Well, what you could do is you could take a traditional model of contracts and just simply add whatever effect that you want to it. So if you want state, you can take a traditional model of contracts that's pure, add state, and say, oh, we're done. And you could certainly do that. But what's going to end up happening is, well, you might violate some assumptions. So one question we can ask is, should contracts use effects in an arbitrary way? Or should there be some constraints on the kinds of effects that contracts can use? And I would like to argue here that contracts should only use effects in a reasonable way, okay? Which is not very precise, but we can think maybe more precisely about what does it mean to be reasonable? What does it mean for a contract to use effects in a reasonable way? Okay, so informally, contracts, well, what's the role of contracts in a program? The point of a contract is to ensure that your program does not violate its specification, okay? So to raise an error if it detects that something has gone amiss. The purpose of a contract is not to do any really useful computation. So it shouldn't really interfere with your program proper, all right? So that's the informal way of putting it, that your program and the contract have two separate roles, even though they're both at runtime. But how do we say that a little bit more formally? What we can say is that if you have a program with contracts in it, and it evaluates successfully, so it terminates and it runs to a value and not an error, that should mean that when you erase the contracts, it's going to run to the same value, always, which means that the contracts are not sort of interfering with your program. So we would like this property to hold of whatever model that we come up with for contracts that use effects. And of course, if we just do the naive thing, we take the pure model of contracts and we add whatever effect to it, you're not going to get this property. It's just not going to hold naively. So the purpose of this work is to construct a model that we can express all of these systems in where erasure holds. And this is the goal and what we've achieved here. Okay, so how do you do that? Well, the session is a bit of spoiler because effect handlers, right? So to reiterate, our goal is to have a unified model satisfying erasure, and that theory, moreover, should be implementable, okay? So let me just introduce a bit of notation, which is probably familiar. It's very similar to the kinds of things that we've seen in prior talks. So I'll write do v to indicate performing an effect, and we're going to pass a value up to the handler. And then handle b is the body, and h is going to be a lambda that's going to accept a value describing the effect, and also a continuation. OK. Now, why would we want to use effect handlers, other than they're great? Well, why are they great? One reason is it's a uniform means of expressing lots and lots of different kinds of effects. So if we're trying to build a model that's going to be able to express all of those different systems that I've shown, I want something that's pretty generic. And so effect handlers are one way of doing that. If I just have a base model with effect handlers, I don't have to think about, do I want this specific effect or do I want this other kind? We can just have effect handlers, and that's enough. OK, well, that's maybe more a general reason, but there's a more specific technical reason why we're using effect handlers in this work. And that's because in order to get this erasure property, I need to distinguish between effects that are performed in two different contexts. So I need to say there's a certain kind of handler that is going to handle effects that are performed in your main program, in your normal execution. And I'm going to have a different kind of handler that is going to handle effects that occur in the extensive contract checking code. And these two don't interact with each other. So it will just, if you have an effect that's performed in ordinary code and you have a contract handler around it, it will just bubble through sort of normally. Okay? So that's the key technical device that we need in order to get this erasure, or one of the key technical devices to get this erasure theorem. Okay, so I want to give a little example of this. So suppose you have map, and you give it a function and a list, and you're mapping the function over the list. We're very familiar with this. And I'm going to show you the contract for on f, which is a function, in this case, anything to anything. But the interesting part about this is I want to guarantee that you use this function at most n times, where n is the length of the list. Okay, so there's some dependency going on here. And the contract that we'll implement is this use at most n times contract. And we're going to need an effect for this. Okay? So it's a bit of a generalization, I guess, of the interop example I gave earlier. OK, so how are we going to do this? So suppose we have a function from x to y. And I have the ordinary function contract at the bottom with a normal arrow, x to y. But the additional thing that I'm going to do is I'm going to allocate a mutable reference that's going to contain the number of times that I'm allowed to call this function in the future. Okay? So the key thing to take note of here is this ref n, okay, a mutable reference that contains n. Okay, so then what do I do with this? Well, I need to ensure that when I apply this function, I'm going to make sure I don't go too low. All right? So I actually need an additional piece here on the domain. So instead of just x, I'm going to add an additional conjunct that says I can only use this n times. And the way I'm going to do that is I'm going to pass in this reference that I've allocated. Okay? Right, so now we've punted, and we have to define this max uses thing. And so this is going to do pretty much what you expect. We get in the reference. And this is going to be applied when you apply the function. And we're going to say, get me the value that's inside the reference. If it's 0, then that means that we've used this function too many times. So we're going to give back false, which means that the contract is going to fail. Okay, this is what we call a flat contract. It's just a predicate that says, yeah, you've called this too many times. Otherwise, we're going to update the value that's inside of the immutable reference and then give back true. So hopefully this is actually quite intuitive, and I think that's the idea. And one of the benefits of contracts is that even if you're checking something that's pretty sophisticated perhaps, you can write these pretty easily. And I think programmers can write these quite easily. OK, so that's the implementation of the contracts. But of course, we're using effects. We're using mutable references. So we actually need to execute this in the context of some handler that's going to handle these operations. Okay? So you can imagine that the entire program is going to be run inside of this, this run with mutable references in the side of this thunk. So you have a top-level handler, which is a pretty normal thing to do. And the key thing about this handler is that I have handle diamond, which is the contract effect handler, okay? Because we are performing effects in contract code, okay? So you would put the implementation of mutable references where the ... is. But there's one kind of funny thing about this, which is you have to constrain the kinds of handlers that you can put in here to satisfy erasure. So this is the second caveat about this design, is that if I did something like this, where I had a handler that just threw away the continuation, throwing away the whole program, that's going to violate erasure, okay? Because, well, certainly if you perform this effect in contract code and then you throw away the program, you're doing something different. So that's going to violate the property. So if we actually have to constrain these handlers in a certain way. And if you're interested in that, you can look at the paper in more detail. Okay? So one other thing to mention is that it seems like, well, there's quite a few constraints here. And this is certainly true. We've tried to make this system a little bit more expressive. And it turns out that if you make it a little bit more expressive, you end up violating this erasure property. So we found a pretty unique design. We've gone as far, I think, as we can without violating the property. OK, so that's just summarizing. The two key technical ideas is this distinction between main effect handlers and contract effect handlers, and an appropriate restriction on contract effect handlers. OK, so just to sum up, in the paper, we have more theory and more practice. So more theory, we have some more variations on kinds of contracts that perform effects, which we call main effect contracts and contract handler contracts. And those are used to implement various different kinds of contracts. And we have a blame correctness theorem, which is a kind of standard theorem that you prove of a contract system. So that holds for the one we've constructed. And then we have two implementations. One is a standalone hashlang that is a fully faithful implementation of the model. And then we also have an implementation that is in Racket itself, which is inspired by the paper, but is backwards compatible. So we've made a small adjustment to Racket's contract library that allows you to express some of these contracts. But we had to stay backwards compatible, so it's not fully faithful. And finally, an evaluation. So we actually use these implementations to implement toy versions of all those systems that I showed earlier. OK? All right. Thank you very much.
OK, so.
Hey, nice talk. There's been work on statically removing contracts from programs, like soft contract verification, work like that. Do these play well with this, or could they be extended to play well with this?
It's a very good question. I'm quite familiar with that work. And this is certainly something that we want to do in the future. And I think there's no reason that it couldn't apply to this other than we need some people to engineer it. But certainly, I think the techniques could apply. Yeah.
Thanks, Cameron. This is really nice. Could you say a bit more about what the restriction is on the handlers? I guess I have two particular use cases in mind. One, I imagine you don't allow multi-shot continuations.
Correct. Yep.
Right. And then two, do you allow anything, any kind of handler in which the continuations escape?
No. Yeah.
No.
So it's basically use exactly once in tail position. It's quite restrictive. Yes.
Okay. Thanks.
And we would like maybe if we could relax that a bit, but we haven't figured out any way to relax it anymore.
Yeah, I guess the obvious one I mean, one of the main uses for handlers is where you do some form of concurrency, and you only run your continuation linearly, but maybe not just yet.
Yeah.
You still don't let it escape as such, but yeah, I wonder if that could be useful or not.
Yeah, that would be interesting to think about. Yeah, certainly.
Got a question from the Discord. In the bounded application contract, what do you gain from using an effect handler for state as opposed to a primitive mutable reference? Is it easier to restrict effect handlers so that they're well behaved?
The point of using the effect handler is to really, for the purpose of a model and to prove this property. So certainly, if you were doing this in Racket, you can just use Racket's built-in mutable references, and that's perfectly okay. But for us, we're interested in proving this property and having it apply to all of these systems. So in practice, yes, you can certainly just use built-in effects, and that's fine. But if you want to know that erasure holds, then effect handlers, I think, are the way to go.
Yeah. Got another question from the Discord.
Maybe I can add on the previous question, and that's like, is this more expressive than state? Like, do you have other use cases?
Yeah, so basically all of the practical instances that we've found are state-like. So maybe not exactly global mutable references, but something kind of like that. And we are certainly interested in perhaps examples that go beyond that. But certainly we haven't found any in the literature yet.
One more from the Discord. Do you have nice examples of contracts that use more power from control effects than just mutable state or continuation?
Yeah, so that's similar to that question. So, but we're interested in more, I think, is what I would say. Yeah.
Take one here, and then if you have more from Discord.
Hi, thanks for the great talk. A couple slides in, you had a sort of big line of checks of things that you could successfully do. One of them had a little asterisk on it. What's the asterisk?
Yep. Yes. Yes, I can say a little bit about that. So that particular paper had contracts, but those contracts actually violated a little bit of what we would, some of the, I guess, one of the principles we would say about contracts. And so it had expressive power that was a little bit beyond like normal kind of contracts. So that's why that asterisk is there. We can do it, but maybe a little bit less powerful than what they had in the original paper. But if you're interested in more specifics, we can talk later, certainly. Okay.
Yeah, we need to switch speakers, so I guess we'll stop here, and there's more questions on Discord. You can take them later.
Thank you.
Okay, so we're still waiting for the slides.
Thank you. Oh, it's Zhixuan. Zhixuan, yeah. Zhixuan, yeah. Thank you.
Do you mind if we use
Yeah,
this one?
sure. I can switch to this one.
Yeah.
Thank you.
So
no. No. Ain't embarrassing. Okay, and how can I? It's quite embarrassing. I need to customize and with swap. How can I swap the screen?
You need to go to your display settings.
Somewhere I should be able to swap the screens.
Yeah, here, do you want me to?
That's
Oh, that is not what I wanted to do. well, now your texts are on there. Can you...
Hooray. Thanks, everyone. So the last talk of this session is about how to add algebraic laws back into algebraic effects. It's called Algebraic Effects Meet Hoare Logic in Cubical Acta, and Zushan will present.
Yeah, thank you. Yeah, sorry for my embarrassing technical difficulties. And it turns out I don't know how to use Keynote. And yeah, it is so much difficult than using Acta. Okay. Hello, everyone. I'm Yushe Yang. Welcome to my talk. This is my joint work with Ocean Kelly and Nicholas Wu. Algebraic effects meet Hoare logic in cubical Acta. And this paper technically is quite simple. It's very simple. It is about optimization of algebraic effects, also known as universal algebra, in cubical Acta, making use of cubical Acta's function extensionality and higher inductive types. And this part is written in a mechanized tutorial style, so if you want to know about algebraic effects in a mechanized tutorial style, then I encourage you to have a look. And then we define a effect generic Hoare logic on top of algebraic effects, and then we finally show some sort of interesting theorem about this Hoare logic. I can give this talk by walking you through how these things work, but I think you probably can know a lot more by just skimming over the paper for 15 minutes. So instead, I will focus on explaining why we did all this, why we think this is useful. But let's first revisit a very basic question. What do we want to formalize if we want to formalize a programming language? It is easy. Step one, formalize the syntax. And this is usually not so difficult. We have a range of ways of doing this, depending on how abstract we want our syntax to be. So, for example, we can formalize intrinsically well-typed terms, or we can first formalize raw terms and a typing relation. And if we want to be really, really concrete, we can formalize strings and a parser. And in whichever way, this part is really not so difficult. So step two, let's formalize the semantics. But what is semantics? What is the semantics of semantics? One approach is operational semantics. Operational semantics treats a programming language like a symbolic abstract machine, just like this lovely universal Turing machine here, which fits into one picture. So programs in operational semantics are treated as states of your machine, and computing is just transitioning in your machine. So operational semantics really models the aspect of a programming language as a computing device. But we shouldn't also forget that programming languages are also languages. And in its ordinary sense, a language is a phonetic or visual system for describing things or denoting things. Like here, this lovely English letters here denotes this lovely situation shown in this picture. But the thing with operational semantics is that it is not always so clear what the language tries to describe if we look at the operational semantics. So for some low-level programming languages like Turing machines or even PCF, by looking at its operational semantics, it's very clear that they just try to model the informal computing processes that we do as humans. But for some higher level programming languages that we designed in 2024, I think the situation is so. And I'm pretty sure I'm not the only person who had the experience of looking at symbols jumping around in an operational semantics and had a low clue at what the language tried to describe. But in contrast, most of the programming languages that we design are designed for describing some things. Sometimes they are designed to describe some mathematical concepts, like sets, domains, sheaves, infinity groupoids, and QBS, you name it. And sometimes we invent programming languages to describe some computations that enjoys some nice properties in some operational semantics, which is usually covered out by some logical predicates or relation. And sometimes we use languages to describe terms up to some operational equivalence, like contextual equivalence, applicative by similarity, and so on. But in both of these cases, our languages are designed to describe some things. So let's formalize this aspect. So after formalizing syntax, we should formalize the intended denotational meaning of our language, which may be based on some operational semantics. But as soon as we have one model, there is no reason to just have one model. It is very common that we do care about multiple aspects of our languages. Like we may care about, we may want to use our language to do mathematics, but also do computations. And we may not only care about how our programming languages compute as an abstract machine, but how they actually compute in real machines, which can execute languages like PHP. So this motivates our final version of our language formalization checklist. So after formalizing syntax, we should formalize first a general notion of models. And then we define the concrete models that we are interested in. And then after formalizing our languages, we can actually formalize the programs written in our programming language and do program verification. And of course, this approach is nothing new. This is just the traditional approach in the study of logic that have been employed for more than 100 years. And this also shouldn't come as a surprise to programmers, because as programmers, we all know program against the interface rather than implementations, if possible. And here, this general notion of models is the interface, and the concrete models are the implementations. So after my rather long motivation, let's come back to this paper. And if you don't remember, this paper is about algebraic effects, or formalization of algebraic effects in cubic data. But the way I see it is that it's a framework for formalizing first-order programming languages and doing program verification. So you may immediately react, first-order languages, who still use first-order languages in 2024? And my excuses for working with first-order languages is that first, even though some languages that we invent is not first-order, but usually the interesting part is the first-order. So in such cases, we can only formalize the interesting part, which is the first order, and just reuse cubical agdas function types by shallow embedding to formalize the functions. And another excuse is that because we are working in a simpler setting, there are more things that we can do which are not possible in more general settings. And I will show that in a minute. And so coming back to this framework, from the point of view of the user, to formalize or specify a first-order language in the framework, the user just needs to specify a set of operations of the language in the framework and a set of equational axioms of all these operations. And then the library then provides the general definition of models, which are just sets implementing these operations. And the library also provides a free model for your language, which are syntactic terms quotiented by the equational axioms. And then the library also provides a bunch of reasoning tools on this free model. So for example, suppose we want to formalize and doing program verification with a non-deterministic parsing DSL. Then as a user of this framework, we just need to specify that we have 4 operations which can be divided into 2 groups. The first 2, get input, are for accessing the token stream. And the next 2, or and fill, are for non-deterministic branching. And the axioms can also be divided into 2 groups. And the first group of axioms says that each operation from the first subgroup commutes with every operation from the other group, which intuitively says that the thing you do to your token stream in one non-deterministic branch doesn't interfere with the other branches. And we also have some more standard equations on each of these operations. Like here, this one says O is an associative operation. And then we can define a bunch of models, including the free one, which is free. So it is given by the library. And we can also have mathematical models, like modeling this language as functions from string to a bag of A, where A is a result of parsing. And we can also have some more operational models, like we have terms and we quotient them up to bisimilarity, which is defined by an operational semantics. So having specified this language in the framework, we can write some actual programs with the free model. Like here, it is a fragment of a parser of binary trees where the leaves are a diamond and spades. And so this char, this char is defined on get input. It simply consumes 1 character from your token stream. And that funny infix operator is our operator for non-deterministic branch choice. Another comment that I should make is that notice that this program takes an additional natural number parameter. That's because the free model, our term model, is inductive. But this parsing program is inherently recursive. So we need to have an explicit step indexing to limit the depth of our recursion. Otherwise, it won't be terminating in cubic argda. So after formalizing this little cute language and writing some programs, the next thing that we want to do is to actually reasoning about the program and verifying that they meet our requirements. Since this framework is based on equational axioms, so a natural way is to do equational reasoning. And in this framework, for every two programs, S and T, in the free model, S equals T in cubic argda, if and only if S can be rewritten to T using the equational axioms specified by the user. And by the very definition of what a model is, it is also equivalent to S and T have equal meanings in all models. So working model independently can be achieved by working with the free model, which is nice. So coming back to our parser example, for example, we may want to verify that our parser program satisfies this equality, which says that for every trait T, if we print it out as a string and we push all these characters into our token stream, and then we pass a tree, all this thing is equal to just return the trait T. So this equality specifies how this parser should behave. Can be sort of as the specification of T. And in principle, we can show this equality from the equational axioms that we use to specify the language. But it is actually very painful. That's because the equational axioms that we use to specify our language are usually too primitive for doing actual program verification like this one here. So this motivates us to develop more reasoning tools And in this paper, what we do is to formalize an effect generic Hall logic, which was first introduced by Schroeder and Mosakowski. And I emphasize it is just a generic Hall logic rather than the generic Hall logic. And in particular, this Hall logic is about partial correctness, and it is demonic with respect to non-deterministic choices. Let's see how this works. The idea is that assertions of this Hall logic are just computations, P and Q, which returns a proposition in cubic character. So suppose your language has state, then P and Q, your precondition and postcondition, they can just read the state. So that's how the assertions can access your state. And then the validity of a whole triple, P, T, Q, where T is a program, and P is a precondition, and Q is a postcondition, and Q can also refer to the return value of T. This whole triple is encoded as the equality over there. So that's an equality between two programs. On the left-hand side, the program first executes your precondition P, and executes your program T, and then executes your postcondition, and then it returns the result of your program X paired with A implies B. That's a new proposition. And on the right-hand side, it is all very similar, except that it always returns true. And how this works is that it basically, this inequality asserts that whenever, roughly speaking, whenever you have some A implies B on the left-hand side, which is not true, then you should be able to use your equational axioms to rewrite to show that these execution passes are not possible, so that it is equal to the right-hand side, where it always returns true. So the last thing about this Hall logic is that this Hall logic is built on top of equational reasoning. It is defined to be an equality. So Hall-style reasoning and equational reasoning are just inherently tied together in this framework. But there's an even sharper connection, which says that a proposition established using Hall logic can be used in equational reasoning. And more specifically, let T be a program. And suppose we establish using our Hall logic that without any precondition, after executing T, the result X always satisfies some proposition phi. And we say that under the assumption of phi x, fx is always equal to gx, then we can conclude that the inequality over there, T then F, is equal to T then G. So this very intuitive proposition is also not very difficult to prove classically. By classically, I mean assuming law of excluded middle, by just doing a case analysis on whether phi x is true or false. But it is surprisingly difficult to show constructively. And it took Ocean and I several months to do that in cubic character. And in the end, we ended up with also a very bizarre proof. And our proof works something like we inspect the proof of the Hall triple. So remember that the validity of such a Hall triple is always a program equality, which also equivalent to some derivation of the equational axioms. And then we very carefully modify that derivation to obtain our desired program equality. So it is kind of a very combinatorial proof, which is very rare to say in universal algebra, because in algebra effects and universal algebra, basically all your proof is very conceptual. It's like taking some kind extension and you are done. But this proof is very different. So, but maybe it is just us overlooking some very simple proofs, but it is what we got after like 4 months or 5 months. And this, okay.
To end up soon.
And this main theorem, the so-called main theorem, is useful in practice because we can really turn in some very tedious equational proofs to first doing a detour to Hall logic, and from our Hall logic to deduce the program inequality that we actually wanted. Like this one here, we may want to first use a whole logic to establish our parser satisfy this very intuitive whole triple, which says that if we started with a token string that is a tree followed by anything, after parsing, it is a tree and with the remaining stuff. And from this whole triple, we can more easily deduce our desired program equality. So we end up with a much more manageable proof for the equality compared to just doing equational reasoning. And to wrap up, I think if there's only one message that I can deliver at POPL, that would be your programming languages are more than fancy calculators. They are languages, and we should make use of this fact. And another message is that and we shouldn't also restrict ourselves to just one reasoning style, whole logic with a whole style reasoning or equation reasoning, and actually they can coexist, and it is very beneficial to do so. Thank you.
So does anyone have quick question? I see Andy Pitts at the back.
So what compelled you to use cubical actor?
I wanted to use quotient types and function extensionality, and I want to remain fully constructive.
Right, but you could have done that in other. I mean, cubical actor is, provides univalence and higher inductive types. Those are the characteristic features with a computational content. But I don't think either of those things are particularly what you need, right? I mean, you need just quotients.
Right, that's exactly true. I just need quotient and effective quotient, actually. So I don't think I have other implementations of current proof of system allows us to do this formalization. But that's true, I don't use the full strings of cubical actor. Thank you.
Okay, so we'll take one more quick question here.
Hello.
I don't see you.
Here. Hello. Hi. So very nice work. I wanted to say that I'm familiar with work about using extensions of separation logic with languages with effect handlers, and their Hoare triples they have the notion of protocols that defines how an effectful expression communicates with the handler. But in your case, your Hoare triples, there's no extra notion of protocols, but from what I understand, there's also no notion of handlers. So your reasoning is based on reasoning just about the equations of the effects, but is there any, did you consider extensions about reasoning with languages with handlers?
Yeah, that's a very good question. So the question is, I didn't say anything about handlers, and that's true. But I think this work can be extended to also take handlers into account. Like the whole logic here I introduced, it doesn't currently have a rule for how, what is the rule for effect handlers. But I think that can be done. It is not done yet, but can be done, I hope. Thank you.
Cool. Let's thank the speaker again.
Ça va? Ça va. Rouge.
before in the preview a sort of the rest of it session, which I thought was not right. So it's on automata and complexity, and the first presentation will be on Parik's theorem made simple, I thought first, but it's actually symbolic. So take it away, Matthew.
Okay, thank you. I just noticed my web browser's being weird, so let's try and get out of that. Okay, so hello everyone, I'm Matthew Haig. I'm at Royal Holloway, University of London, so quite local. And this is joint work with Arthur Jez and Anthony Lin. So I'm going to start off by using the limited time I have by shamelessly promoting the fact that we are looking for new lecturers. So if you're looking for a new academic home, then please consider us. Let's go on to the talk. So the talk in abstract is about kind of symbolic automata. So one of the contributions is we look at the idea of parametric context-free grammars and equivalent definition of push-down systems. So that's like a symbolic version of a well-known theory. And then we go on to look at the Parik images of these things. In particular, we show that the Parik image of symbolic context-free grammar can be encoded as a small existential formula. So the great thing about this is we can actually use it for our favorite SMT-based verification techniques. So either you know the whole talk, or the rest of the talk I'll go through what those things mean. So we are interested in strings, like this one here. So obviously strings are a ubiquitous data type in computer science. So one way that you might not think of straight away is we can think of these strings as being a trace of a program. So when we're verifying programs, we're generating the strings that are generated by those programs. Also, if we're doing some verification of programs that handle text, then we also have to handle strings. So we might be looking for things like code input injections or code injections, which are about the string inputs. And then finally, this kind of work has found recent application at places like Amazon about access control policies. So I'm not going to spend too long on these, but I'm just going to show you quickly what they look like. So here is a push-down system. It's modeling a program, and it's generating a string. And we might want to ask questions like, do we read as many things as we write, and things like that. Here's a kind of a bit of JavaScript that handles strings. So this is taking some kind of input from the user, in particular a username, escaping their username to try and avoid anything bad happening, and then using the username as part of some JavaScript. This looks like it's doing good things, but actually it's not. So actually we need some proper verification to actually check that the code injection is not possible. And finally, here's an access policy. This allows students to access an exam, but it denies them from accessing everything else. And this kind of reject and this kind of matching is done using sort of what look a bit like regular expressions. They're a bit weaker than that, but it's basically string analysis. So if we want to check that our access policy is kind of robust, we have to do some string verification. So we need to do string analysis to check whether programs behave well, websites are safe, and so on. OK, but what's the kind of problems with this? So one big problem is undecidability. So I saw context-free languages are useful for modeling programs, but as soon as we have context-free languages, things start to get undecidable very quickly. But even in the worlds, if we're just looking at strings, we're not interested in kind of context-freeness, then just being able to concatenate strings together and do transjunctions, much like the HTML escape or the JavaScript escape that we saw before, then things also become undecidable. There are also just other problems about computational difficulty. So even if we're just dealing with neither regular things, then we might end up having to intersect lots of regular automata, and that gets kind of pretty big very quickly. That's an exponential blow-up just to intersect them. One kind of observation is that constraint solvers, SMT solvers, are getting much better at strings. That's been a hot topic over the past 10 years. But they've been very good at integers for a long time. So their kind of support is much more mature for numbers than it is for strings. So that's how we segue into the Parik image. So what is a Parik image? So I'm going to start off with a definition. So here is a language. So it contains a number of strings, either A, AB, BCB, AAB, or AABBBC. And the Parik image of that is kind of an abstraction of that language in terms of like numbers. So what we're going to do is count how many, for every word in this language, we're going to count how many A's we've got, how many B's, and how many C's. So we can see that the word A can be represented as this vector that says there is one A and no B's and no C's. AB can be represented as 1A, 1B, and no C's, and so forth. We're just counting the number of each time each letter occurs. One nice property of the Parik image is that it is possible to take a kind of a regular language, in fact a context-free language, and encode the Parik image of that as a small integer linear integer constraint. So we can write a short SMT formula that characterizes all of the kind of counts available in that language. So this is really useful because we can use it in our SMT solver. We can use it to abstract context-free languages, so those undecidability issues, they kind of go away. And then furthermore, we can abstract strings using numbers. So we can kind of leverage the kind of mature, kind of quite robust and quite quick numerical support to be able to kind of answer queries about strings much more quickly. The cost of that, of course, is that we're abstracting, so we lose some information. So if we're still in the situation where if the result is unsat, then we know the answer is actually unsat. But if our abstracted constraint is satisfiable, then we actually don't know. It could be sat, it could be unsat. So that means we have to actually grapple with the strings themselves. So here's an example of this. So this is an example taken from a paper from FM 2023. So this is a simple kind of string constraint that says it has variables x, y, z that should take string values. And we should be able to kind of assign values to those such that the equation at the top holds. So zyx equals xxz. And moreover, x is in A, y has some A's followed by some B's, and z is in B star. So most solvers actually fall over on this, and they can't solve it, even though it's quite small. But it's easy to disprove by counting things. So we can count the number of B characters. So the first observation is that x has to be all A's, so that can't have any B's. So that doesn't contribute much. But y, which appears on the left-hand side, must have at least one B character, because it's got in the expression A plus B plus. So that means the left-hand side has at least one B, so the right-hand side also has to have at least one B. Since that can't appear in the x variable, it must appear in the z variable. However, the z variable also appears on the other side. So if you think about this, that means that we have to have twice as many B's on the left-hand side as we do on the right-hand side. So this is just, since we're required to have at least one B, this becomes numerically impossible to solve. So a bit of integer reasoning gets rid of this constraint, and we can dispatch it without needing any string solvers. So the way we would encode that to an abstraction we'd first say, here's a kind of abstraction of the variables, of the x, y, z variables. We have one for the ZA counts the number of A's in Z, YA counts the number of A's in Y, and so forth. So we can rewrite the equality like this to say the same amount of characters appear on each side. And then we use that kind of short image encoding to do the rest of the formula. So we can check that the x variables are actually a parity image of the regular language that x has to belong to, and then the same for the y and the z. So we can do an encoding like this, throw it at our SMT solver, and it will give us pretty much an instant answer on that. OK, what is the drawback of this? So one of the main drawbacks is alphabet size. So if we just have A, B, and C, it's not too bad. But if we have the full ASCII character set, that's 128 variables for every string we have. That's already feeling a bit funky. In Java, we'll need 16,000 variables. In Unicode, it would just go crazy. And then if we want to do something fancier, like have streams of integers, then we need an infinite number of variables. So that means that we're not going to do very well if we just go naively for this. So string constraint solvers have had to deal with large alphabets for a long time, because that's one of the main kind of artifacts of dealing with strings. And there is a standard technique that exists, and that's that of a symbolic automaton. So here's a symbolic automaton. I'm actually going to describe a parametric automaton instead, which has the same ideas, but a little bit extra. So here it's going to be a generalized symbolic automata. It's actually a parametric automata. This just has two transitions. So this p here is a parameter. It can take any value. So the idea is that if for an accepting run of this automaton, you first have to pick a value of the parameters, and then you have to try and run the automaton. So this says the first character we see has to be something that matches the parameter value we chose. And then every other character we see has to be something different, so something different to that parameter. So this kind of pretty small automaton is actually encoding quite a lot. So if we wanted to do this without a symbolic representation and without parameters, we would need, I don't know, 128 transitions at the start, and then for every one of those, we'd need 127 other transitions. So that would be quite a big automaton. So using these parametric automata, we can compress the representation quite a lot. So here's an example of what that might accept. I won't go into that too much. OK, so the kind of first contribution we did was said, well, first of all, let's define the concept of a parametric context-free grammar. Let's be able to use symbolic representations in our context-free languages. So we define a context-free grammar and also a notion of parametric push-down systems, and we show their equivalent, so just as you might expect. So here's an example of parametric context-free grammar. We have the rewrite rules here. So we start from S. We can either rewrite to nothing, or we can rewrite to X, followed by S, followed by Y, where X and Y must satisfy this constraint, where X is smaller than the parameter and Y is bigger than the parameter. So we can write things like this. Has my computer just frozen on me? That is not ideal. I think it's is it possible to carry on using the kind of Parric image? So what is the Parric image of a symbolic automaton? So the difficulty here is we might have a possibly infinite number of characters to keep track of. So we have one very simple idea, which is instead of counting all the characters, we allow the user to give us the predicates that define the characters we're interested in. So your predicates might be X is equal to A, that's one predicate, or it might be that X is within a range, it's either A to Z, or we're only interested in even characters, and so forth. So we ask the user to give us a kind of a bunch of predicates, and the Parric image is how many times we see a character that satisfies that predicate. So our image is like this. We say how many times something satisfies the first one, how many times a character satisfies the second one, and how many times it satisfies the third one. So one example, if we only had one predicate, and that predicate was true, it was true for every character, then the Parric image would just count the length of the words. That would be a simple example. OK, so one of the benefits of the Parric image is we could construct a small SMT formula that would allow us to kind of characterize that Parric image and use it with other constraints. But how about if we do this with a symbolic version? So one naive problem with this is that a character A could satisfy this predicate, it could satisfy this predicate, and it could satisfy this one. So characters don't uniquely satisfy one thing. So this kind of gives us an exponential blow up in that every character is kind of a 0, 1 vector. It satisfies some predicates, it doesn't satisfy others. Fortunately, we show that you can actually encode this Parric image still as a small formula, but we have to use some kind of funky, kind of fun combinatorics to avoid a naive exponential blob. But that is possible. OK, so we did some experiments to kind of see the usefulness of this approach. So we applied this to do some string constraint solving. So we took, for example, here's the constraint we had before, and we kind of applied this kind of, we encoded all of this as symbolic automata, and then we applied our Parric image, and then we saw whether the unsatisfiability was still witnessed. So the kind of idea was we took some benchmarks from the SMT competitions, and we also generated some of our own using regular expressions from regexlib. We focused on some hard benchmarks. So by hard, we mean Z3 took more than 10 seconds. The reason we did that is because this is an approximate technique. It won't replace a string solver, but it's quite potentially a technique a string solver could use to try and dispatch some cases before getting into the meaty string stuff. Have I frozen again? OK, the image, I don't have too much time to explain it, is that if a line goes high up very quickly, then we're doing very well. If it kind of goes low down, not very well, then it's not doing very well. So our solver is this red one here with the diamonds on it. And in general, we can see that it does very well. It actually solves things pretty quickly. So on paper, on these pictures, we're doing really well, and it's actually quite a useful technique. We also need to mention the fact that this is approximate. So these results, some of them are very quick, but they're not accurate. So on these benchmarks, we weren't very accurate. But on the other two, we were quite accurate. So there's a trade-off of accuracy there. OK, so that's kind of all I wanted to present today. I kind of didn't think I'd have much time for future work, so I was a bit lazy about this slides. But I think in terms of future work, one of the main things would be to integrate this properly into solvers. At the moment, we're just taking the whole constraint and turning it into Parric image, which is a bit of an axe. It should be a much more focused usage of this would benefit solvers better. And then also to look at other applications, because the Parric image is applicable to so many different areas of verification. Okay, thank you.
So we do have time for questions. Maybe, yeah.
Thanks for the talk. Oh, that's very loud. Do you think this could be extended to work with tree languages?
I think that's a good question. So there's always a connection between context freeness and trees. And I believe we've been in contact with someone who has been doing some similar work related to trees. So I think there's definitely something that could be done there. I'm not sure of the exact notions myself.
Okay, thanks.
May I just also interpose a question? So for the alphabet sizes, a common technique is to actually look at the expressions and see actually whether you can partition just by looking at the expressions, the alphabet into basically what would correspond to disjoint predicates. How would that compare, or is it applicable to your technique?
I think if you're just dealing with strings and Unicode, there's the kind of the interval representation, and interval representations are nice in that you can actually split them down without an exponential blow-up. So you could actually use that instead, I suppose. But if you want to generalize to kind of more interesting data types, so like it's sequences of integers, for example, then that's harder to do. The predicates can be much more general. Then you get this overlap, and you need some tricks to kind of avoid a blow-up.
Hi, thanks for the nice talk. Can you say anything about how the symbolic automata affect the closure properties of the languages you're considering and generating the representing?
That's a good question. There's a lot of work. So Marcus Venus et al. And other people have been investigating symbolic automata and closure properties for a long time. So there are lots of results out there. They generally behave quite well, to my knowledge. I feel like I'll be missing some dangerous case where they don't quite work well by saying that, but they generally behave pretty well. You can do intersection and complement language equivalence, and all of that seems to be generally well behaved.
Thank you.
Hi, thanks for the great talk. So you mentioned you get small integer formulas. So are there pathological cases where the formulas aren't small? And when you say small, like small in relation to what? Can you expand a bit?
Okay, yes, I think maybe I deleted them when I was trimming my slides down, but by small we mean polynomially large. So in the case of Parric images, the non-symbolic version, the formula is actually linear in size. For us, we go up to n log n, so it's not a huge blow-up in that sense. That said, I mean, there's kind of a bunch of stuff that has to go into the encoding. So, I mean, it's a linear blow-up, but it does become a bit more complicated. So when we're talking about pathological cases, we did have to employ some optimizations to stop the solver getting lost looking for representations of minimum spanning trees and things like this. So you have to be careful sometimes.
Thank you very much. If you do Perl programming.
Okay, welcome everyone to my talk. I'm Konstantinos Mamouras, and I will present joint work with Agnieszka Chattopadhyay. So as you probably all know, classical regular expressions, or regexes, are built using concatenation, non-deterministic choice, and Kleene star. Due to their simplicity and their immediate correspondence to finite state automata, they have very nice computational properties. But real-world regular expressions, on the other hand, use more constructs than just the regular ones, such as bounded repetition, look-around assertions, and back references. In this work, we specifically focus on the challenges brought by look-around assertions, which are further subdivided into positive look-ahead, negative look-ahead, positive look-behind, and negative look-behind. So why do we care? Well, regexes with look-around are widely used for extracting information from unstructured data. They have found many applications in domains such as network intrusion detection and malware detection. The key computational problem here is called regex matching, which is about finding occurrences of patterns in data sets. Unfortunately, existing regex engines that support lookaround rely on backtracking search, which is a very inefficient algorithm that has exponential running time. In this work, we show that we can actually do much better than this. So let's start with an example that shows how lookaround is used. Suppose that we want to extract the area code from a US phone number. This is the pattern that we would use for this extraction task. Let's go over it bit by bit. This is a character class that matches a single digit. This is a pattern that matches 3 consecutive digits. This suffix pattern describes strings that start with a dash, followed by 3 digits, followed by a dash, and then followed by 4 digits. So the positive look-ahead for this pattern is different in that it does not capture the suffix substring. So what are the main observations here? First of all, the entire string must have the form of a phone number, but only the first 3 digits of the string are extracted or captured, as we say. The substring, on the other hand, is not, the substring that corresponds to the suffix pattern is not captured. This means that in this example, the look-ahead specifies the context within which the area code should occur. Let's look now at another example for specifying password requirements. This is the pattern that we will use. The character class dot matches a single character. So this sub-expression matches at least 8 consecutive characters. This sub-expression matches a string that contains at least 1 lowercase letter. This matches a string that contains at least 1 uppercase letter. And this matches a string that contains at least 1 numerical digit. Notice that the look-ahead assertions do not capture the string, and they overlap. This means that the entire string must satisfy all 4 password requirements. So in this example, lookaround encodes a form of intersection or conjunction. As you probably know, classical regular expressions have a very simple semantics where each expression is interpreted as a set of strings. Regexes with lookaround, on the other hand, require a more complex semantics because they additionally describe the context within which a match should occur. Before I show you the definition of the semantics, let's go over some terms. A position in a string W is a number in the range 0, 1 up to n, where n is the length of the string. We should think that positions mark the boundaries between characters. In particular, position 0 corresponds to the left endpoint of the string, and position n is the right endpoint. Now, a location in a string is a pair I, j, where I and j are positions and I is at most j. Remember from this slide that positions are points, but locations are intervals. Now we are ready to present a logical semantics for lookaround using a satisfaction relation. This is a ternary relation that relates a string, a location within the string, and a pattern. We read this as follows. The pattern R has a match in W at location I, j. And this is an illustration of a match within the string. The satisfaction relation is defined by induction on the structure of R. And I will not be showing you the full definition, but let's go over the cases of lookaround. So for the positive lookahead of the pattern R, we say that it has a match at location I, j, if and only if I is equal to j, and the pattern R has a match at location I, n. The case of negative lookahead is similar. Now, for positive look behind and negative look behind, the definition is completely symmetric. There is one important observation that we have to make here. look-around assertions should be thought of as being interpreted at positions. This is because an assertion only holds at locations of 0 length. Now that we have seen the formal semantics, let's go over one more example. Let's consider the pattern BC, but only if it occurs within the appropriate context where it is preceded by some occurrence of A and is followed by some occurrence of D. We can see in the string that there are 3 occurrences of BC. Now notice that the pattern .*A.* has a match at location 0,6, which means that the look behind holds at position 6. Similarly, the pattern .*D.* has a match at location 8,15, which means that the look ahead holds at position 8. From all these, we deduce that the top level pattern has a match at location 6,8. And in fact, this is the only match in this string. There are 2 common approaches for regex matching. One is backtracking search, and the other one is automata-based simulation. The advantages of backtracking are that it is easy to implement, and also it allows for the easy integration of advanced features such as look-around assertions and back references. The main disadvantage is that it has worst-case complexity that is exponential in the length of the input text. This can get pretty bad, and it even has a name. It's called catastrophic backtracking. In the case of automata-based approaches, typically NFAs or DFAs are used. There is a memory throughput trade-off that can be explored here. Generally speaking, NFA-based approaches are much more memory efficient, but DFA execution can be much faster. Notice that some popular regex engines, such as Google's RE2, use a hybrid approach that combines NFA simulation and DFA simulation. Unfortunately, none of the existing automata-based regex engines supports lookaround. So if we want to use lookaround, then we're currently stuck with catastrophic backtracking. There is a fundamental obstacle when using automata for lookaround. It is known that there exists a family of regexes with lookaround such that the smallest DFAs recognizing them have doubly exponential size. An implication of this fact is that any deterministic streaming algorithm for matching regexes with lookaround requires exponential memory. For this reason, we propose an algorithm that is not streaming in the general case. Our algorithm may perform several passes over the input text. In particular, it performs left-to-right passes for evaluating look-behind assertions. Correspondingly, it performs right-to-left passes for evaluating look-ahead assertions. Each pass performed by the algorithm should be understood as the execution of some non-deterministic automaton. I will explain now the algorithm using the example that we saw before. So the pattern we're looking for is BC in the context that I described, and at a high level, we perform the evaluation in a bottom-up manner. First, we start with a look-behind assertion, and we evaluate it with a left-to-right pass. So notice here that we're searching for an occurrence of A. So in the beginning, the output is 0 until position 4, and it becomes 1 from that point on. Next, we evaluate the look-ahead assertion with a right-to-left pass. Similarly, we're searching for the occurrence of a D. So the output is 0 until position 11, and it becomes 1 from that point on. Now, we abstract the top-level pattern by replacing the look-behind with Q0 and the look-ahead with Q1. these expressions Q0 and Q1 should be understood as some kinds of queries to oracles that can immediately resolve the truth values of the assertions. For this reason, we call this highlighted expression an oracle regex, and then we proceed to evaluate it with a left to right pass. So let's see how this proceeds. So we're looking for a BC occurrence. So going from left to right, we find the first occurrence at position 4, but we don't have a match here because the look behind does not hold at position 2. We continue until position 8, where there is a match because both the look behind assertion holds at position 6 and the look ahead assertion holds at position 8. And then we continue until we find the other BC at position 15, where there is no match because the look ahead does not hold at position 15. The algorithm that I just described stores the output from the first 2 passes in data structures that we call oracle tapes. Then the next pass of the algorithm is performed using an automaton that I call an oracle NFA. You should understand this as being an extension of epsilon NFAs, where the automaton has access to both the input string and the oracle tapes. An additional feature of this automaton is that it can perform queries to the oracle tapes using special epsilon transitions that are annotated with oracle queries. And you can see 2 such transitions in the diagram on the slide. Another important observation is that the memory footprint of this algorithm is determined by the space that we need to store the oracle tapes. So the footprint is big O of Kn, where K is the number of look-around assertions that occur in the pattern. The main theorem is that the regex matching algorithm that I showed by example in the previous slides has time complexity big O of Mn and space complexity big O of Kn, where M is the size of the pattern, N is the length of the input text, and K is the number of look-around assertions in the pattern. We have also implemented several performance optimizations on top of this base algorithm. I will only discuss one of them, which is about reducing the memory footprint of the algorithm. I need a definition first. We say that a regex is unidirectional if either all look-arounds are look-behinds or they are all look-aheads. Now, if a regex is unidirectional, then the algorithm can simply perform a single pass over the input, and therefore we do not need to store oracle tapes. An implication of this is that the memory footprint can be reduced from theta of Kn to theta of K. In particular, if all look-around assertions are look-behinds, then the algorithm performs a single left-to-right pass over the input and can be therefore be regarded as a streaming algorithm. We have implemented our algorithms and the optimizations, and we have evaluated them experimentally using the Snort and Suricata datasets. We have compared our algorithms against PCRE and Java's regex library, both of which are state-of-the-art regex engines that are based on backtracking. The main observations from our evaluation are the following. First of all, both our algorithms have linear running time in the length of the input text, and the optimized version is at least 10 times faster than the base version. Moreover, the running time of PCRE and Java is superlinear in the length of the input text. In particular, our optimized algorithm is 250 times faster than PCRE for text length 1000, and it is at least 4,000 times faster than PCRE for text length 10,000. Now, I'd like to conclude with a summary of our main contributions. We have presented a formal semantics for regexes with lookaround using a satisfaction relation that relates a string, a location, and a pattern. We have proposed an efficient algorithm for matching regexes with lookaround that has complexity big O of mn. And we have shown that unidirectional regexes can be matched with a single pass over the input. We have implemented our algorithm and several performance optimizations, and our evaluation shows that our implementation has much better performance than PCRE and Java's regex library over the workloads that we considered. This is all. Thank you for your attention.
Questions?
Hi, could I ask about back references? Have you thought about those much, especially when you have the back references inside the lookarounds or the capture groups?
So that's a great question about back references. So they present a unique challenge because they take us beyond regularity, whereas everything that we consider so far is in some sense regular. I would say probably the starting point there should be to look at special cases of back references that are indeed regular, when, for example, you're capturing something that is bounded in length. And I would say maybe the next step should be the use of back references where the regular expression has some kind of determinism property. So beyond that, I am not sure how it would work out if one wanted to have an efficient implementation of back references. I think that's a challenging question.
Thanks for the talk. The example you gave had a certain number of lookarounds that were then compiled into a final Oracle NFA. But if you have nested lookarounds, do you then you have a dependency between the oracles? Does this then induce multiple paths that would be multiple passes over the string that's then reflected in the efficiency?
That's a great question. Indeed, if there is nesting, then the algorithm would proceed in the same way. You would just have to do more passes. The key thing to notice here is that if you perform the passes in order of dependence, then you already have the Oracle tapes that you need in order to perform the next computations.
So in that case, would the complexity be parameterized additionally by like the depth of nesting?
No, the bound that I showed would still be the same. Right. So there would be, the upper bound would be m times n, and in order to prove that, you have to see that the Oracle regexes that are used, the sum of their sizes is equal to m. So this is really the key observation there. So as you proceed in a bottom-up manner, you keep breaking down the regular expression, but the Oracle regexes that you consider, their sizes will always sum up to m.
Okay, thanks.
Mm-hmm.
So I had 3 questions, but one of them was just the last one, so let me ask 2 questions. What happens if you have a star and have a lookaround in it? Don't you need to scan multiple times, like the case with a nested lookaround?
That's a good question. No, you don't need to scan several times, because when you do a single pass, you resolve the output for all positions. So you store that in the Oracle tape, and then you have the answer for every position in the string. So you're free to use those outputs from that point on. So then in the start implementation, there will be a loop in the Oracle NFA, but that will consult the same tape every time.
Sorry, I didn't ask the right question. I think I understand that you can do the Oracle. What about the string one that you briefly went over?
So for the streaming case, I said that you need to restrict yourself to regular expressions that only have look behind. So you can perform a left to right pass. But then if you look at the regular expression, there can be dependencies between the look behinds. So if there is nesting, there is going to be dependence. But then you're going to perform the computation for each one of them in topological order at every step, so that every time you need something, you have already computed it. So you do a left to right pass, but within a single step, you process the look behinds in the topological order of their dependencies. And this ensures that the bound holds.
Thanks again, and also for the answers. Next talk will be given by Ruben. and it's going to be, as it says on the complexity landscape of checking progress in proofs. In circular proofs.
Oh, okay. Okay, so I'm Ruben Rowe, also from Royal Holloway, and this is joint work with my colleagues Liron and her student in Israel, and my colleague Andre in Sheffield. So we are looking at the infinite descent property, which is central to checking the validity of derivations in cyclic proof theory, and is also a core aspect of the size change approach to checking program termination. So there exist a couple of algorithms in the literature already coming out of these applications for deciding infinite descent. And what we do in our paper is we propose two new algorithms. We carry out comparative parameterized analysis of the time complexity of these algorithms. And we also implement and experimentally evaluate them within the cyclist theorem prover. So to give you a bit of intuition about what infinite descent is, I'll talk about it in the context of an example from cyclic proof. So cyclic proofs are artifacts of really the proof theoretic formalization of the logical principle of reasoning by infinite descent. So we could consider, for example, Euclid's infinite descent proof of the irrationality of the square root of 2. So here I have an example derivation, which and the statement that it derives at the bottom is expressing that it's not the case that the square root of 2 is rational. And that's expressed as there existing two natural numbers x0 and x1, such that the square of x0 is 2 times the square of x2. Over here on the left, I've abstracted some straightforward arithmetic reasoning, which allows us to then infer that, in fact, x1 is strictly less than x0, and that, moreover, there exists another natural number x2, with the relationship that the square of x2 is half the square of x1. I can then apply some analogous reasoning, which I've abstracted over here, to further derive that there's a further natural number x3, and so on and so forth. And formally, we represent this as an infinitely deep derivation. And in order to justify that the statement that it derives at the root is a valid logical inference, we can do a proof by contradiction. So assuming for contradiction that it's not valid, this would then entail that there is an infinite sequence of natural numbers represented by variables that we can trace through an infinite path in this proof, such that at various points in this proof, infinitely many points, in fact, there is a strict decrease with these numbers. So this would entail an infinitely descending chain of natural numbers, which is the contradiction. When such infinite reasoning is regular, we can represent it as a finite derivation with cycles. And so the infinite descent property here is really the core thing that allows us to justify the logical statements that we derive with these cyclic proofs. So over the last couple of decades, this cyclic proof treatment has been applied in many different contexts very successfully, since it's a general and flexible technique for applying inductive reasoning implicitly, by which I mean you don't have to come up with inductive invariants up front. But what all of the different cyclic proof systems, or at least most of them that we find in the literature, have in common is that they're all different instantiations of the same basic abstract framework. So when we're considering infinite descent in general in cyclic proof systems, of course, we're not interested in the specific logical statements. What we're really interested in is the underlying structure of the proof derivations. So we abstract these simply as graphs. The logical statements get abstracted as vertices, which have edges representing So we have edges from vertices representing conclusions of inference rules to vertices representing the premises. We also have to capture this notion of being able to trace elements through the logical statements in the proof, and we do this by associating a collection of abstract entities that we call positions with the vertices. And the other piece of information we need is to know how we can track these, the relationship between these positions through the paths in the proof. And so for that we use things which we call sloped relations, and these say whether consecutive positions, whether they're in a non-increasing relationship, which we represent with this horizontally sloped arrow, or whether they're in a progressing or decreasing relationship, which we represent with this downward diagonally sloped arrow. So this can also capture naturally the size change termination context. We can think of the graph structures representing the call graph of a program, the positions as representing the parameters of the functions which are called, and then our sloped relations correspond to what are called size change graphs in the literature. So we've called these relations sloped relations, and for that reason we call these abstract graphs sloped graphs. And then in this setting, the infinite descent property is expressed through the statement that for every infinite path in this sloped graph, we can trace a sequence of positions that progresses infinitely often, and where progression is given, of course, by two consecutive positions being related by one of these downward slopes. So I've mentioned that there are a couple of algorithms already in the literature for deciding the infinite descent condition. One of them is automata theoretic and checks inclusion between omega automata. The other is relation-based and relies on Ramsey theoretic principles. It's known already that the infinite descent property is p-space complete, so unsurprisingly, the time complexity of these two algorithms are exponential in the size of the underlying sloped graph. What I'll do now is I'll give a quick overview of these existing algorithms, then I'll talk about the new algorithms that we've given in the paper. The automaton-based algorithm constructs two Buki automata which recognize infinite sequences consisting of vertices in the underlying sloped graph. So we have an automaton that we call a path automaton, and this recognizes all infinite paths in the graph. We have another automaton called the trace automaton, and this recognizes all such infinite paths that have an infinitely progressing trace of positions. And then checking the infinite descent property amounts to checking an inclusion of the path automaton within the trace automaton, which of course is equivalent to checking emptiness of the intersection of the path automaton and the complement of the trace automaton. So it's this complementation operation which leads to the exponential complexity of checking the infinite descent with this method. And in this context, for this construction, the trace automaton, the size of the trace automaton is dependent on both the number of vertices in the underlying graph and also this quantity which we call the vertex width, which is the maximum number of these positions which occur in any given vertex of the graph. And so because the trace automaton depends on both, then the exponential component of checking this inclusion also depends on both of these parameters, as well as having some polynomial dependence on it as well. In contrast, the relation-based algorithm works by computing a set of sloped relations for each pair of vertices, and each of these sloped relations corresponds to the composition of all of the relations along some finite path between those two vertices. This can straightforwardly be described inductively, where we start out with singleton sets containing sloped relations which we obtain from the underlying graph, and then we saturate them by composing the sloped relations in each of these sets. And with this method, to check infinite descent, what we have to do is we have to check that for each relation corresponding to a path from a vertex to itself, it has a loop with one of these decreasing slopes in it. So this can be seen as an instance of the algebraic path problem, and so we can use the generalization of the Floyd-Warshall all points shortest path algorithm for it. So this is straightforwardly seen to be polynomial, in fact, cubic in the number of vertices of the graph. Interestingly, it is only exponential in this one parameter, the vertex width. So there's a separation in the complexity between the two parameters. This algorithm also has some nice properties, which is that it allows early termination when the underlying sloped graph doesn't, in fact, satisfy infinite descent. And it also allows practical optimization, which doesn't, in fact, change the overall complexity, but makes a difference in practice, which allows us to lift an ordering on the slopes to become a partial relation on the sloped relations. And so we can get away with only considering sloped relations which are minimal with respect to this partial order. A question is raised, can we come up with an automaton-based approach which mirrors this separation in the complexity between the two different parameters? And the answer is that we can, and we can do this by changing from constructing automata that recognize vertices in the graph to recognizing instead sloped relations. So we have the same scheme. We have a path automaton which recognizes sequences of these sloped relations that do correspond to actual infinite paths in the underlying graph. But now the trace automaton, it recognizes sequences of sloped relations that simply admit some decreasing trace and aren't necessarily connected with the underlying structure of the graph. So this means that the trace automaton now only depends, in fact, linearly just on the vertex width. And so the exponential component in checking the inclusion in this scheme also only depends on the vertex width. And what we see is that we've traded off exponential complexity in the number of vertices for a bit of extra polynomial complexity there. We can also improve the relation-based approach by taking advantage of some symmetries inherent in the problem. So in fact, we don't need to consider all paths between vertices. So for example, if we have edges between two vertices, V1 and V2, if we check the alternating path between them that starts from vertex V1, well, this will have a descending trace if and only if the infinite path, alternating path starting from V2 has a descending trace. So we can modify the Floyd-Warshall-Kleene algorithm to avoid considering unnecessary paths by fixing an arbitrary order on the vertices. And this means that when we're computing the sets of sloped relations, we only need to consider paths between particular vertices that pass through intermediate vertices which are less than or equal to the smaller of the endpoints according to this order. So for this reason, we call this modification of Floyd-Warshall-Kleene the order-reduced algorithm. And what we see in the complexity analysis is that it actually saves an exponential factor in the vertex width compared with the original Floyd-Warshall-Kleene. What we see is that we have quite a complex landscape in terms of different algorithms that exist, and the relationship that they have with each other really depends on how the values of these two different parameters compare with one another. So in order to evaluate how these algorithms perform in practice, we implemented them in C++ and integrated them within the cyclist theorem prover. And we tested it on a selection of test cases which were present in the cyclist framework already. And we also handcrafted some examples which were designed to elicit the worst case behavior of these algorithms, which fix one particular of the parameters and then vary the other, and testing on both positive and negative examples. So what we found is that for the so-called real-world examples, we found a clear improvement with the relation-based methods over the automata-based methods. So the relation-based methods are shown here in the yellow and red lines. We also saw, in line with the complexity analysis, that the order-reduced algorithm performed slightly better than the Floyd-Warshall-Kleene algorithm, although kind of in these real-world examples there was not so much in it. So testing it on the worst case benchmarks, we sort of see improvements of the order-reduced algorithms over the standard Floyd-Warshall-Kleene, which was mirrored in both positive and negative examples, but the performance of the automata-based methods really depended on whether we were testing positive or negative examples. And then lastly, on the examples that vary the vertex width, here we saw that the relation-based methods were clear winners. So just to sum up, we studied infinite descent in an abstract logic-independent setting. We proposed 2 new algorithms for deciding the infinite descent property. We analyzed the complexity trade-offs which were inherent in the different algorithms and experimentally evaluated them as well. Thank you.
Questions?
Thanks for the talk. With the order reduced method, did you notice any practical difference with the ordering chosen? Did you just generate it at random, or?
Yeah, that's a really interesting question. So, in fact, it does make a difference what ordering you choose. We just, in our experiments, we just took a sort of natural ordering in the definition of the graphs. But what you want to do is you want to order the vertices which are sort of hubs. You want to put them last in the order, because then you can discount more paths. But we did some experiments which we haven't reported in the paper with different orderings. But sort of what we found, at least in the real world examples, is because the values for the parameters are quite small there, the overhead of actually reordering the vertices kind of took over the running time of the algorithms. Yeah.
Okay, thanks.
So I would have imagined that the graphs that you have from proofs have much more structure than being arbitrary graphs or even captured by small w. So are you sure that this is p-space complete even for the class of proofs that you get?
Yeah, I mean, this is also a very interesting question. I don't really have an exact answer about what are the structures that we see in practice in proofs. I can say that we noticed that the vertex width of proofs in the wild, it's sort of comparable to the number of vertices. I mean, so we can do a procedure that minimizes the number of vertices while kind of keeping the topology the same. And once we do this, we kind of see that we get similar vertex width to the number of vertices. But we saw vertex widths going up to maybe 12 in some cases. So I don't think it's really the case that in proofs in the wild, the vertex width is always very small. Sometimes it can be large. But I don't have...
There's nothing like, it's not bounded tree where there are other kinds of measures of graphs?
I mean, I think you could maybe do something like trying to bound the tree width as you're doing some proof search, to restrict the proofs that you actually find. I'm not sure if a priori there's some kind of restriction, no.
Okay, thanks.
Thank you very much.
All right, thank you.
Okay. Next talk is going to be by Satya on positive almost sure termination.
Okay. Hello? Yep. Okay. Hi, everyone. I'm Satya. I'm here to talk about a positive almost sure termination. I'm going to talk about what it means. I'm going to give the complexity of it, of deciding it. And I'm going to talk a little bit about a few techniques you could use to prove that your program is positive almost surely terminating, right? So our setting is that of a probabilistic Turing-complete programming language with binary, probabilistic, and non-deterministic choice. This means that in our program, the programming language allows for precisely two options at probabilistic and non-deterministic operators. And we resolve non-determinism in our language using schedulers F. This is just standard semantics of probabilistic languages, right? And in this world, there are three notions of termination that have been studied in the literature. The first is almost sure termination, under which the termination probability of the program is 1, no matter how the non-determinism is resolved. The second is positive almost sure termination. This is what we take a look at. Here, the expected runtime of the program is finite, no matter how the non-determinism is resolved, right? And the third is bounded termination. Here, the expected runtime, the supremum of the expected runtime across all possible schedulers is a finite value. And it looks a lot like positive almost sure termination, except that the quantifiers are swapped, right? And now notice the superset relations over here. This means that there are certain programs that are passed but not asked. There are certain programs that are passed but not passed. And we'll illustrate this with a simple example. I call this example the long tail end. And this is because this over here, these two states from DEC to this terminal state. This is the tail end, and the length of this tail end depends on the scheduler. So in this program, the executions are initiated at this state P, the probabilistic state, with the single program variable n being 1. From P, with probability half, you get to the terminal state immediately. And with the remaining probability, you get to this non-deterministic state ND. From ND, well, the scheduler can either choose to move the execution back to P or move it to the tail end loop over here, right? And when the scheduler moves the execution back to P, it quadruples the value of n. Now, consider the scheduler that once it gets to ND, for the first n times it's in ND, it moves the execution back to P, and the last time it moves the execution to DEC, to the long end tail loop, right? Under the scheduler, the one execution that goes over here to P, then to ND, then back to P, m times, and then reaches DEC, would set a value of, the value of n when this execution reaches DEC would be 4 power m, right? Meaning the length of the tail end loop over here would be 4 power m. Meaning that the expected runtime of the program under the scheduler would be 4 power m by 2 power m. It's at least 2 power m. Meaning that the expected runtime of the program depends on the scheduler, and importantly, meaning that the program is not BAST, because there is no supremum expected runtime, no finite supremum over the expected runtime, right? However, this program is definitely passed because the single remaining scheduler would just keep the execution between P and ND. So because it just keeps the execution between P and ND, it never reaches the tail end loop, and the expected runtime is bounded above trivially by a small constant. So this program is passed but not passed. And now that we've motivated how that pass is a bit different, we move on to our first contribution, which is a complexity result, where we show that deciding passed is pi11 complete. And this is a significant jump up in terms of difficulty from the other two notions of termination that I've just described. So, well, what does all of this mean? What does it mean that passed is in pi11? Well, to talk about that, let me talk a little bit about the arithmetical hierarchy. The arithmetical hierarchy is a hierarchy of undecidability. This means that every level of the hierarchy contains problems that are more undecidable than the levels under it, right? So at the bottom of this hierarchy are all the decidable sets. Over here, you'll see all the recursively enumerable sets, that's sigma 0, 1. Co-RE sets are pi 0, 1, and these guys are just more undecidable than these, right? As an example, well, the classical halting problem is here at sigma 0, 1. Ast is here, and BAST is here, meaning that these are both already harder than the halting problem. And to go to pi11, well, what can you do? You take all of these guys, and you drop it to the bottom level of another hierarchy of undecidability, the analytical hierarchy, of which pi11 is at the first level and past is in pi11. So all this just means that past is like significantly harder than any of the other termination notions that we have seen so far. So as a note, placing past inside pi11 is not too difficult. So we're going to skip that argument, and we're just going to focus on why past is pi11 hard. Okay? To show that, let me introduce a canonical pi11 complete problem. This is the set of recursive, well-founded omega trees. Well, what does this set contain? Well, take a look at this guy. This is a tree. Every node in the tree is a natural number. So 34 is a child of 3, 7 is a child of 179, and so on. This is an omega tree because every node can have countably many children, meaning it can potentially have infinitely many children, right? It is a well-founded tree because it has no infinite branch, and it is a recursive tree, meaning that the characteristic function of this tree is decidable, meaning that for every tree T in omega rec, right, it is associated to a program PT such that as long as for every node in the tree is validated positively by the terminating program PT. All right? So because of this relationship between T and PT, we can rewrite or equivalently think of omega rec as a set of programs characterizing well-founded omega trees. Right? Now, all right. Now, to be able to reduce this program to past, well, what you would think that you would need to be able to look through all possible infinite branches in these trees, right? And make sure that every possible branch is finite. That's kind of what you need to do. To do that in past, we need two small subprograms. The first is a subprogram that enables a scheduler's choice of a natural number, n, any natural number. And remember, in our programs, we only have binary, not deterministic choice. So to be able to do this, it requires a little bit of work, but the details are in the paper. I'm not going to talk about them now. And the second component is a simple technique to increase the expected runtime by a finite value. In this case, it's just 1, right? So how do we use these two things? Well, for any input program M, we need to make sure if M M characterizes a well-founded omega tree, right? Well, we start by setting the variable node to the root, and we generate a n and append it to node. What this does is it takes a potential child of node and then checks if this node is in the tree characterized by m. If it is, you increase the expected runtime by 1, and then you go back and check for another child of the current node which you know is in the tree. If not, you just terminate the program. So what happens if this program over here is not passed? If this program over here is not passed, it is possible to show that this loop over here must happen infinitely often. And that means that this over here must say yes infinitely often. And this immediately means that, well, the tree characterized by M has an infinite branch. It's not well-founded. And therefore, M is not an omega rec. And this is kind of the base of why past is pi11 hard. All right? Now, we noticed that as we worked the proof out, the only probabilistic branching we needed in our proof was like this, where in the left branch you do nothing, and in the right branch you immediately terminate the program execution, right? So, and this is a strange proof, a strange kind of program syntax. We call these kind of programs Knievel form programs after Evel Knievel. And because of pi11 completeness, we have a procedure that transforms programs to Knievel form in a way that preserves past, meaning that if the original program is passed, the transformed program in Knievel form is also passed. And we know that this procedure exists, right? And because of this, we are able to motivate the second contribution, which is a sound and complete proof technique for past in Knievel form. Right? So how does this work? Well, let's start with some basics. All right? Let's start with ranking functions for deterministic termination. Take a look at this particular program where x is n, and it's just x is reduced until x becomes 0. And take a look at the function f of f from the set of states to some real number, which just takes the value of x in each state and outputs that value, right? This function is something that decreases by 1 in each execution step. And these are called ranking functions. And ranking functions are known to certify termination of deterministic programs. All right? Now, we have in the literature generalization of ranking functions for the probabilistic case, which are called ranking supermartingales, which are also mappings from the state space to the reals that reduce by 1 in each execution step. And these have been shown to be sound and complete for BAST. Okay? Now, ranking supermartingales are incomplete for PAST. And why is that? Well, take a look at the long and tail loop program I just talked about. And here, as I mentioned, because of the scheduler that loops between P and ND m times and then goes to DEC, there is a path from P to DEC and then to a terminal state in 4 power m steps over here, right? Now, if a ranking function were to exist for this, the terminal state would have to be given a value 0, and the DEC state would have to be given a value of 4 power m, and meaning that the state P must be given a value of at least 2 power m. And this is true for every m, which is not possible, meaning that P has to be given, cannot be assigned a real number, right? However, if you think about it a little, the transfinite ordinal omega kind of measures P quite well, right? Because any possible DEC for any possible value of n can be given the value 4 power n. And from P, you know that you reach DEC with some value of n in bounded amount of time, because from P to get to DEC, you just need to get out of this loop, which does not require infinite amount of time, right? So based on this, we have our proof rule, which assigns to each state a rank, an ordinal rank, such that the expected time to reduce the rank is bounded. We captured this boundedness using ranking supermartingales, and we just note that in our proof, in our paper, we have certain programs whose rank goes all the way up to every ordinal under the Church-Kleene ordinal, the first non-computable ordinal, right? So a small note on the applicability of our proof rule. It is complete for all past programs, but it is sound for programs in Knievel form. And this just means that you need to apply the transformation to Knievel form before applying this rule to show that a program is passed. So in summary, well, I have studied positive Almoshar termination. We've shown that, well, the complexity of deciding past is pi11 complete, and we've presented sound and complete proof rules for this. Thanks for your attention. Happy to take questions.
Hey, thanks. How do you rank with ordinals the probabilistic stuff of your program?
We don't. I mean, so as in the probabilistic stuff is more or less, so here,
can you show the
right?
can you show the your program?
Of course.
Yeah.
Yeah.
So you said you can rank the state P with omega, but how do you rank, for instance?
So let's say you have DEC comma n, right? That's a program state. So DEC comma n, just map it to n, right? Which is a good enough rank for n for DEC. For P, map it to omega, such that, well, the rank of the required time to reduce the rank from omega to DEC is bounded, right? Because from P getting to DEC is the overall probability of just escaping is the same as the probability of escaping these sets, right? And this is a bounded value.
But say that DEC also had a probabilistic choice whether to.
No, from DEC onward. In this particular example,
okay.
DEC does not have a probabilistic choice. If it did, we'll have to do something different.
Okay.
But in this case, we don't have to think about it. This is an illustrative example. We have better ones in the paper.
Thanks.
So this reminds me of my first class in logic, where Anne Rogers at Rutgers actually, and by the way, Rogers is from 1967, so we had to work with bootleg versions of Rogers' book. She said, like, aren't you interested not only in how that it's undecidable, undoable in practice, but also how undecidable it is, right?
Yeah.
So coming back to the pi-1-1 completeness, and the combination of probabilistic and non-deterministic computing is very hard. So can you just tell us a little bit about what the story is then? If you take the non-determinism out, would the whole thing fall down into the
as without non-determinism, past and past coincide, right? Because the non-determinism is what makes past a lot harder than past. So take the non-determinism out, and they all become arithmetical. They don't become easy, but they become arithmetical. Yeah.
And the other way around, if you only have non-determinism, well,
then it's gonna it depends on how much non-determinism you have. If you have unbounded non-determinism, it remains pi-1-1 complete. If you have bounded non-determinism, it reduces to the halting problem.
Okay. Well, yes. Thank you.
Welcome.
So maybe it's not as bad as after all. Yeah.
Yeah.
Questions?
Can you assign something like an expected runtime to such programs, but in terms of expected ordinals or something like that?
I don't know what that means.
Me neither. But
I tried thinking about this a lot, but no, we just decided that this is sufficient as a model for this stuff. Yeah.
Thanks.
Any last questions? Very high up on the analytical hierarchy. Okay, well, thank you very much. Oh, yeah, we have a break.
basically all we want is
Very similar to the final case, but it's often a bit easier.
yeah, because each, and I think we can. So I was thinking about. So initially, our idea was to, based on the Perique. Terminals.
please. Yeah.
Welcome to the concurrency session, and this is the most important session of POPL. It's not me saying it, it's Shaz Kadir saying it. Concurrency is pervasive in computing, concurrency and distribution. Moreover, for us academics, it is difficult, and its applicability is widening, its styles are changing. So plenty of research contributions there. The first talk is going to be given by Siddharth and Ugur. They have promised, even though it's concurrency, not to talk concurrently. And it is a universal sound and complete forward reasoning technique for machine-verified proofs of linearizability. Thank you.
Thank you. Hi, everyone. I'm Siddhartha Jayanthi from Google Research. My co-author, Ur Yavuz, and I will be presenting this paper on possibility tracking, which is joint work with Prasad Jayanthi of Dartmouth and Lizzie Hernandez of Microsoft. The informal and perhaps more informative title of our paper is A Simple Way to Prove Concurrent Objects. Let me start with the motivation. Asynchrony makes concurrent algorithms hard to reason about. In fact, subtle race conditions have plagued even mission-critical concurrent code. For example, concurrency bugs jeopardized NASA's Mars rover, were one of the causes of the Northeast blackout, and resulted in radiation overdoses that ultimately caused 3 deaths. The bottom line is that fundamental concurrent algorithms and data structures are deployed in all sorts of systems, including some which are critical to the life and well-being of people. Consequently, rigorous machine-verified guarantees of correctness are critical for concurrent data structures. In this talk, I focus on our technique for machine-verified proofs of linearizability. Linearizability is the gold standard for concurrent object correctness. In a concurrent system, operations run over intervals of time. In the picture, I've depicted an example run of a queue, which comprises of NQ and DQ operations by 3 processes that overlap in time. Linearizability states that while the operations take place over an interval of time, they must appear to take effect atomically, that is, instantaneously at some point between invocation and completion. In the example, these linearization points are marked in green. A straightforward technique for proving linearizability is through forward simulation. To prove an implementation, the prover maintains a copy of an atomic reference object. He considers an arbitrary run, and as the run unfolds, the prover identifies the linearization points of the operations as they occur, and shows that the return values of the actual implemented object match those of the atomic reference object. The example run depicted here can be proved in this way if the prover is able to identify the green linearization points as they occur, since the return values of 2 and 1 are consistent with these linearization points. But what if the last part of the run unfolded differently, and the last operation returned 3 instead of 1? Then the proof would go smoothly until the last DQ returns 3, but would fail there, since the atomic reference object would have returned 1. Does this mean that the run is not linearizable? Actually, no, the run is linearizable, just with different linearization points. Notice that the linearization point of the DQ in question did not change. Only the linearization points of the operations in its past did. In other words, we can't always determine the linearization points of operations as they occur. Sometimes our choice of linearization points for past operations may have to be future dependent. Future dependence is a key hurdle in proving implementations linearizable. It shows that the simple forward simulation proof technique is not complete. This leaves us with a question. Is there a simple proof technique for linearizability that's complete and can be used to obtain machine-verified proofs? Previous work since 1990 has made partial progress on this question. Many proof techniques beyond forward simulation have been discovered, including prophecy variables, aspect-oriented proofs, commitment points, and partial order maintenance. These techniques have been used to prove future-dependent algorithms, including the Hurley-Ewing queue, but most of these techniques are incomplete. Schellhorn et al. Showed that backward simulation is complete. However, this technique requires reasoning backwards rather than forwards in time, and is therefore unintuitive for algorithmists. So what do? We contribute the first universal sound and complete proof technique for linearizability that requires only forward reasoning. Our proof technique can be used to prove the linearizability of any implementation of any type. We call our technique possibility tracking, since it tracks all possible linearizations rather than just one, like forward simulation. We also show that a variant of our technique called single possibility tracking is complete for strong linearizability, a stronger criterion used principally for probabilistic algorithms. Finally, we demonstrate the efficacy of possibility tracking by giving machine-verified proofs of several data structures, including for the Hurley-Ewing queue and Jayanti's snapshot, which have been noted for their intricate future-dependent linearization structure, and the Jayanti-Tarjan union find object, which are widely used in applications such as clustering, model checking, and graph analysis. So how does possibility tracking work? We saw earlier that forward simulation is incomplete, since the single atomic reference object it maintains may be insufficient to capture all linearizable future behaviors of an object. Our main idea is to avoid this pitfall by not maintaining just a single atomic reference object, but actually maintaining all possible atomic reference objects that correspond to linearizations of the current run. Specifically, to prove the linearizability of an algorithm A, we design an augmentation A star, which tracks the set P of all possible atomic reference objects corresponding to all possible linearizations. Thus, we see that A is linearizable if and only if P not empty is an invariant of A star. Proving this invariant is the possibility tracking proof technique. Let me clarify what possibilities look like with an illustration. Consider this run, visualized here until time t1. There are 3 pending operations. In this case, one possibility is that none of the operations have linearized. In this possibility, the Q object is still in its initial empty state. Pi1 and Pi2 have pending NQs with arguments 5 and 9, and Pi4 has a pending DQ. Another possibility is that Pi1's NQ alone has linearized. In this possibility, the Q contains 5, and Pi1's operation has linearized with a return value of ACK. In general, a possibility simply maintains the state of the object and a triple for each process. The fields of the triple are the current operation, its argument, and its response if it has linearized. A blank in the last field reflects that the operation is yet to linearize. A blank in the first field reflects that the process is idle. Other possibilities include just Pi2's operation linearizing, Pi2's operation linearizing before Pi1's, all 3 operations linearizing in the order Pi2, Pi1, then Pi4, and many more. The augmenting variable P will be defined to maintain all of these possibilities. But how can we maintain this set P as the run unfolds? Well, we simply update the set of possibilities as each new step of the system unfolds. For example, if the next step of the system happens to be Pi4 returning 9, then all possibilities that are inconsistent with this return event are filtered out of the set P, as they are no longer possible. For example, the black possibility suggested that Pi4's operation was yet to linearize. So it was filtered out since Pi4's response field did not match the return value 9. The remaining possibilities, which are consistent with the run until the latest step, are kept and modified to reflect that Pi4's operation is now complete and it has become idle again. Now I describe the full technique for maintaining P. This consists of initialization and 3 update rules. Initially, P contains just one possibility P naught, in which the object is in its initial state and all processes are idle. The 3 update rules are as follows. When a process pi invokes an operation, each possibility P is updated to reflect that pi is no longer idle and has invoked the operation op with argument arg. As we saw in the example, if pi returns r, then possibilities that don't reflect pi as having linearized with response r are filtered out, and the remaining possibilities are modified to reflect that pi is now idle. The most involved case is that of pi executing any intermediate line of code. That is, a line of code that's neither an invocation or a return. In such a case, we evolve each possibility p to reflect that any set of pending operations, that is, operations that are invoked and yet to linearize, can linearize in any order. This can lead to an explosion in the number of possibilities. But that's okay, since the augmented algorithm is for proof purposes only. When written out in symbols, the possibility tracking initialization update rules for maintaining the set P look something like this. So for a given algorithm A, the possibility tracking proof technique is to generate a machine-verified proof that P not empty is an invariant of A star. Now let me hand it over to Ur to walk you through the Hurley-Ewing Q case study.
Hey folks, for our case study, I'll be talking about the Hurley-Ewing Q implementation, which was given as an example in the first paper that introduced the concept of linearizability. This implementation uses two base objects, X, which is a read and fetch and increment register, initialized to 0, and Q, an infinite array of read, write, swap registers, each initialized to baud. I will explain how NQ and DQ are implemented through an example run, and here I visualize the initial values of X and Q. X is set to 0, Q is set to all bauds. And let's start our run by having a process NQ5. This process first fetches and increments X. Namely, it writes the old value of X into a local register I, and then increments X. So now X is 1 and I is 0. In the next instruction, it writes its argument into QI, in this case, writing 5 into Q0, and then it returns. Let's say we have another NQ, this time 10. The process once again fetches and increments X, and then writes the old value of X into its local register I, and then writes 10 into QI, in this case Q1, and then it returns. As for the DQ, we first read X into a local register L, and then start a loop from 0 to L with the looping variable J. We loop until we reach either reach L or find a non-bot element QJ. And in this case, Q0 is non-bot because it is 5, so the process swaps bot into its place and then returns a retrieved value, here, that value being 5. So say we have another DQ, we once again read X and start the loop. Now, since Q0 is bot, we move to Q1, and then as Q1 is not bot, we swap bot into its place and then return the retrieved value of 10. Now let's talk about what makes this implementation interesting, which is its linearization points. The DQ operation has a fixed linearization point, exactly at the instance where it swaps bot into a non-bot register in Q. And it might be enticing to think similarly about the NQ, but that's not the case. And through another example run, we will see that NQ's linearizations are actually feature dependent. Once again, we start with the default initial values of X and Q. And let's have a process P execute NQ5 to completion. And then let's have it NQ10, but pause after the fetch and increment line. And now let's have another process Q execute NQ15 to completion. And then once again, NQ20 execute completion. And now if we have Q executing two successive DQs, we note that the first one is going to remove 5 from Q0, and the second one is going to remove 15 from Q2. And then continuing with another DQ, this time examining how the process loops through the indices more closely, we see that Q0 is empty, so we move to Q1. We see that Q1 is empty, so we move to Q2. And now, instead of iterating further, if we pause here and instead continue the pending NQ by P, we will see that it writes its argument of 10 into Q1 and then return. And let's now consider what the possibilities are for the states of the implemented Q. And this is going to be a function of the upcoming DQ operations. For instance, if we assume that there's another process that comes in and performs successive DQs to completion, the first one will find 10 at Q1 and then return it, and the second one will find 20 at Q3 and then return it. And the return values of these successive DQs tells us that right at the instance we pointed out, 10 followed by 20 is a possible state, since 10 is returned first and 20 second. Let's make a note of this possibility. What if we continue Q's pending DQ? In that case, Q proceeds to Q3 and removes and returns 20. And then if that were followed by a new DQ, that would remove 10 from Q1 and then return that. In that case, 20, then 10 is very much a possible state as well. This is a little unusual, and we note that in the state 20 followed by 10, things appear in an inverted order compared to how they are present in Q. And this is something worthy of making an observation about. Specifically, Q3 followed by Q1 is justified as a possible state, by the existence of this dequeuing process past index 1, whose looping range contains 3. And we can also talk directly about permutations of the non-empty indices in Q. Specifically, instead of talking about the justifiedness of the state Q3, Q1, we can say that the permutation 3.1 is justified by the existence of this dequeuing process. And here's an important insight. Since we have two possible states depending on how the future dequeues might be taking place, if we start thinking about the tracker, this tracker must contain possibilities with states corresponding to both 1.3 and 3.1. Otherwise, a future scenario might make P empty. And we can adapt the definition of being justified to a more general one if we say that any permutation of indices is justified if for any inversion we have a dequeuing process between the inverted pair. And now we can adapt our insight to the following statement. P must contain a possibility corresponding to each justified permutation of indices. And now let's ask the question of how does this insight help us with the proof? Well, we call that with our technique, we want to prove the information generalizable through proving the non-emptiness of P in the augmented implementation. And let's also restate the insight. P must contain a possibility corresponding to each justified permutation of indices. Then it sounds like the key to prove that P is not empty is to prove that this set is contained in P. And that's exactly what we do. In our proof, we define a set S of possibilities, which exactly corresponds to this set, containing a possibility for each justified permutation. And then what remains is to prove that S is not an empty set, and it is contained in P. And this, in turn, implies that P is not empty, which is exactly what we want. And then moving on to the machine-verified proof, we prove this by induction, strengthen it with simple observations in order to make it an inductive invariant. And we can, this can be proven using any proof assistant. We chose TLA Plus and the TLabs proof system. And specifically, if we express the augmented implementation in this specification language, TLA Plus, and then prove the invariant correct by induction, namely assuming it holds true in the current configuration, any line is going to keep it holding true in the next configuration. Yeah, this wraps it up for the case study. I'll hand it over back to Siddhartha.
So I think we'll just keep this conclusion up here and move to questions.
Thank you very much. I see a question here.
Hi. So, I mean, in these papers that relate linearizability with simulations, I mean, they start from restating linearizability as a refinement towards a specification, which in general is non-deterministic, and this is why you need backward simulations. Now, is it like your technique, like saying that it's equivalent to determinizing the non-deterministic spec using some subset construction and then reducing, now that you have determinized the spec, now of course you can use forward simulations?
So I'm not able to process exactly this path in my head and say whether that's exactly what we do. But we can handle, using this method, non-determinism and non-totality. So if the type spec is non-total or the algorithm is non-deterministic or the type spec is non-deterministic, this can be handled using the possibility tracking method.
Yeah, I'm just saying that it looks to me like this possibility tracking is like determinizing the non-deterministic spec using subset construction. But
I see. It's possible that that's one way to view it. I would have to think about it more carefully to answer definitively, but that surely sounds like a possibility.
Thanks.
So Herlihy-Wing's the classical paper, in their appendix, they define exactly the notion of possibilities, and they actually have an algorithm following exactly like what you presented. And they also apply their algorithm on the Herlihy-Wing Q. I don't know if you have tracked that, and I haven't so far I haven't seen any difference between their algorithm and what you presented now. Are you aware of that or not? The appendix of their paper.
Yes, so I am aware. So their algorithm is, of course, the same algorithm that we're proving here.
Okay.
The technique, to my understanding, is not the same as what they have. They also have something which they call possibilities.
Right.
But the proof technique that is used here is different to that.
It would be great to see what's the difference.
So I would have to take this offline with you, because I would have to look at that more closely.
Last question, and Zhengdong should be setting up in the meantime.
Thank you for your talk. I would like to know precisely what you're proving. So if the examples you showed looked like they were proving linearizability of a concrete history. But when I think of linearizability of an algorithm, I'm thinking of linearizability of all the possible histories. So how does that work?
That's a great question. So the intent of all of the things that you saw up there is that you are considering an arbitrary run. So consider an arbitrary run, induct over the time steps of that run. And what the cases of the inductive proof will look like is there'll be the inductive step will have cases, one for each line. So if some process pi executes line 5, its program counter is there and executes it, we'll show that the invariant, if it held before, will continue to hold. So this is going to be the general case. Okay, I think it's time to hand it off.
Yeah, please thank the speakers. And we'll move from possibilities to predictions, and Zhengdong is going to talk about predictive monitoring against pattern languages.
Hello? Hello, everyone. I'm Zhendong from National University of Singapore, and this work is collaborative with my advisor, Umamoto. So nowadays, concurrent programs are widely used. We could see have web servers, browsers, database systems, and operating systems. So writing reliable concurrent code and automated concurrency bug detection has been the subject of many researches for more than 5 decades. So as a result, a wide range of techniques do exist today. For example, we have static analysis and some model checking, but some disadvantages like false positives and low scalability limit their usability. So another technique is dynamic analysis. One looks at traces or executions of a running program and analyze them to declare the presence of or absence of bugs. So in this talk, I will focus on dynamic analysis. So formally, dynamic analysis problem is a membership problem. So we witness execution, sigma, and also we have a bug language L which contains all buggy executions. And the question is asked whether this execution sigma belongs to this language L. So this technique is automated and often do not have false alarms and can scale to large software systems. But when it comes to concurrent programs, there is some problem. Why this is because concurrent programs are sensitive to thread scheduling, which means we might miss many bugs. So here is an example. We have two thread T1 and T2. Thread T1 will write to a buffer, and thread T2 will close the buffer. In naive dynamic analysis, we might notice an execution like this. So thread T1 first write to the buffer, then thread T2 close the buffer. Now, of course, it's OK. There's no problem. But can we just declare that there is no, the program is correct? Actually, we might. OK, sorry. But there is a very similar possible execution like this. So thread T2 might first close the buffer, then thread T1 will write to the buffer. So we want to ask, if we just witness a good execution, can we predict the existence of a similar but buggy execution? So this motivates the idea of predictive monitoring. So in naive dynamic analysis, we ask this membership problem. And in predictive monitoring, we ask a problem is a bit different. So here we ask if we have a execution sigma, whether there exists a execution sigma prime, that sigma prime belongs to the language L. So we would like to use the power of prediction to enhance the coverage of dynamic analysis. So predictive monitoring has been used in many works to detect specific bugs, such as data race, dialog, or atomicity checking. So in our work, we would like to understand the difficulty of predictive monitoring problem. However, so far our problem is not formal enough. The first thing we need to make clear is the notion of the notion of similarity. So in concurrent program analysis, Mazurki's trace is often used to model executions. It provides a way to partition executions into equivalent classes. So Mazurki's traces start from defining independency between events in executions. So two neighboring independent events can be commuted without changing the behavior of the execution. So if you are in the Keynote session earlier today, it is an example of using commutativity. So then the equivalence relation is obtained by swapping events consecutively. So here is a formal definition, but we can take a look at an example. So here we have an execution with two threads. So first, we know that event 5 and event 6 can be commuted. So then we got equivalent execution. Then furthermore, we can continue swapping event 3 and event 4. Then we have another one. Then later, we can also swap event 4 and event 5. We have another equivalent execution. But here, can we swap event 2 and event 3? Actually, we cannot, because if we put read x before write x, it might read a different value, and it might change the control flow. So this is our notion of similarity. So in our work, we will ask predictive monitoring under Mazurki's trace. So let's take a look at the difficulty of the problem. So let's start from the naive dynamic analysis. So here, L can be any language. So it might be undecidable, but in many cases, L is just a regular language, like in data race dialog. So it means that it can be solved by a DFA. So it can be solved in linear time and constant space, and in a streaming way. It's very fast. So we also want our predictive monitoring can be solved in such efficient way. Why? Because in real-world programs, like web browsers, they generate millions of events in a very short span of time. But if the language L is regular, can we always have such an efficient algorithm for predictive monitoring? Unfortunately, the answer is no. So this is our first contribution. We provide a conditional lower bound for predictive monitoring against regular languages. So here we use fine-grained reduction. We assume that the strong exponential time hypothesis holds. Then we show that even for a very special subset of regular languages, star-free regular language, the predictive monitoring cannot be solved faster than the order of the length of the execution to the power of alpha. Here, alpha is a constant related to the alphabet, and in concurrent programs, so the alpha is usually to be the number of threads. So, but in fact, in 1989, Bertoni, Maudi, and Sabadini proposed an algorithm to solve predictive monitoring against regular languages in this time and space complexity, which means our result is a matching lower bound, and the algorithm is very likely to be optimal. But we can observe that it is not suitable for dynamic analysis in practice. So in our work, we want to find a class of properties or languages whose predictive monitoring problem can be solved in constant space and also linear time and in the streaming way. And we also don't want to sacrifice its expressiveness, which means we want it to encode various useful program properties. So based on these requirements, we propose pattern languages. A pattern language contains all executions where some events occurred in a certain order. It is motivated by many real-world concurrency bugs, and there is a hypothesis called small depth hypothesis, which means that those bugs can be encoded in a very short pattern, meaning the D is very small. It's usually just 3 or 5. So here are some examples. For example, those examples are from Java standard library. Here it says that we cannot concurrently iterate a collection and modify it. And the next one says that we cannot write to a buffer after close it. And our result says that predictive monitoring against pattern language can be solved in linear time and constant space, that's by automata. So here we will briefly discuss our streaming algorithm to solve the predictive monitoring problem against pattern languages. So our streaming algorithm is based on 3 insights. So here first we consider a very easy case. If we are given D events, how can we check whether they can be reordered in the correct way? Here we can construct a very special partial order based on Mazurkiewicz trace and check the partial order between pairs of events. The good thing is the partial order can be checked in constant space, and we only have D square pairs. So the whole checking can be just use constant space, and we have a DFA to solve the whole thing. And next, we'll ask how can we check for any D events? Okay, it is very easy because we just need to add non-determinism to this automata. So now we have an NFA, which non-deterministically chooses D events and do the same checking. But the problem is the space complexity is very large. So the last insight use a special monotonicity property such that we don't need to check every D event, and we reduce the space complexity to the order of D factorial times the size of alphabet. So remember that in most practical case, D is very small. It's just 3 or 5, and yeah. So actually, this space complexity is very small. Remember that the major component of our algorithm to check the partial order. And we also have a vector clock-based algorithm. We use this very classical vector clock, and the vector clock of an event it maintains the number of events in each thread that the event E knows about. And to check the partial order between 2 events, we just need to compare the 2 vector clocks. And our vector clock-based implementation uses space which is linear to the number of threads. So the last part is evaluation. We implement our algorithm in Rapid, which is a framework of dynamic analysis on concurrent programs. So we encode some Java standard library properties in pattern languages and test them on some open source programs. And here is an example. So here we have a class and with 2 methods. One method will iterate the set subtitles, and the other one will add something to this set. So our algorithm can predict the violation of the property from a good execution to a bad one. So here we'll see that the modification will interleave between 2 iterations. Our evaluation also shows the scalability. We compare our algorithm with a traditional algorithm proposed by POPL'24. We can see that our algorithm works well even when the execution is very large. However, the traditional algorithm uses up spaces very quickly. Then, to wrap up, in our work, we focus on predictive monitoring under Mazurkiewicz traces. And for this question, we construct a conditional lower bound against the regular languages. This is a matching lower bound. And since we want predictive monitoring algorithm suitable for real-world programs, we propose pattern languages which capture executions where some events occur in a certain order. And then we design the algorithm to solve its predictive monitoring problems and in constant space, near time, and in a streaming way. Finally, our evaluation shows its ability to find perturbations and its scalability. Thank you.
Thank you. Questions? So I'll start with a naive question. In those pattern languages, are there any constraints on the sigma? For example, you said if I open a file, I write, I close, I write again. Well, and there were sigmas in between. How do I know that in that sigma in between I didn't open it again?
Yes.
And then it would make it valid.
Yeah, that one is a case that we cannot encode it in pattern languages. And we're also thinking of more generalized pattern languages. So in the middle, we don't have sigma, but some sigma 1, sigma 2. So we can just, then for those languages, we can encode this file open, file close. But for that one, we yet don't have a very efficient algorithm.
So you mean that if I had a trace where if I had a pattern that said I'm not allowed to write after I closed, and I had a trace where I closed, I opened, I wrote, then this would fail the check.
Yeah, because you have the close and the write, so you don't care about what is in the middle.
All right. Other questions, comments?
If instead of this kind of linear A1 through AD, I wanted to kind of model a DAG. Let's say I want to say A1 followed by A2 or A3 and then followed by A4. Would things differ greatly?
Yeah, I think there is some efficient algorithm to solve this. If it is not linear but a DAG.
So then maybe can we generalize that to low DAG width graphs? Or
sorry?
Can we go more wild from DAGs and go to low DAG width graphs?
Yeah, I think then we might need some width in the complexity. Then I think a very similar algorithm should also work. But I need to think it.
I guess it's worth thinking about it because that would be a great generalization of the pattern you currently have up there.
Okay, thank you.
Thanks.
Hi, thank you for the talk. How do you handle critical sections? Like if someone acquires a mutex and does iter next, iter add, how it will be reflected in the model?
In the model, then we cannot swap any critical sections. And this is also a weakness of our model. And so in the future work, we are trying to relax this part and to get a better model.
Hello. Is it possible to have properties like LTL within this model? LTL properties cannot be done?
So LTL is just equivalent to star-free language, regular language. So I think it's also fit in the matching lower bound.
In constant space streaming?
I think we cannot do. Oh, you mean constant space?
Constant space streaming algorithm might be.
But we cannot do it in linear time, because our this conditional lower bound says that it's very likely that we cannot have a faster algorithm than this polynomial one.
So one last question, and in the meantime, I would like to ask Dominic to set up, at least to connect his laptop, not take the microphone yet. Is there any last question? I'm sorry, I have got one more. those A's that are events like open, close, and so on, can they have some arguments, and can you express properties of those arguments? Can I say that if I push something and I pop it, then it should be the same?
I think that should rely on the log, meaning if you have a very good instrumentation tool. But I think the argument, the problem is you might have some infinite possible arguments. Yeah, I think I need to think about it later. Okay, thank you.
Okay, let's thank Zheng Tong. Going to talk about using commutativity to simplify proofs of parametric programs.
Okay. So, hello everyone. My name is Dominic, and I'll be presenting some joint work with Azadeh. Maybe many of you have seen her keynote this morning, and my advisor, Andreas Podelsky. And if you've seen the keynote, you'll recognize some things, right? So we also work in this field of commutativity reasoning for verification. And in this work, we have extended it to parametrized programs. That is, programs with an unbounded number of threads. The main observation is already the title, namely, in this context, also commutativity simplifies the proofs. And in the next 15 minutes, I'll explain to you in a bit more detail what exactly that means, and I'll give an overview over the detailed contributions that you'll find in the paper. So we start with the object that we study. Parameterized programs, as I said, are a formalism for concurrent programs. We are given a thread template, just a single template, here given as a control flow graph. That control flow graph uses a number of variables, some global variables that are shared between all thread instances, and some local variables that are local to each instance. And the parameter that is responsible for the name parameterized programs is the number of threads, which in this talk I will call n. So that means that for any value of n, I can instantiate the program. I get an instance p of n by taking n copies of the thread template. I'm going to do some renaming of the local variables so that they can be distinguished, and I will take the parallel composition of those n copies. And the verification problem that we are interested in is to show that p of n is correct for any number of threads n. So we want to show this correctness in one verification run for all n. Correct here means safety properties, particularly let's assume that the thread template contains some assert statements that we want to never be violated. So to make this super concrete, a very, very simple example that we'll see throughout this talk. We have a thread template, a control flow graph with two locations, and each thread, therefore, alternatingly increments some variable x and decrements it again. X is a global variable. In this example, we don't need local variables. And the specification that's part of the thread template says whenever some thread is in this location L plus here, then x should not be 0. And this should be always the case when the thread is here. So even if some other thread then decrements x, we need to prove that x is still non-zero. We assume that x is initially 0, so that this actually holds. So if you think about this for a few seconds, you can probably convince yourself that this is indeed a correct program. But we'll see that if we want to prove this and prove this in an automated fashion, we're already encountering some challenges, even though this is such a simple program. Yeah, so let's look into that. How would we verify a program? Well, we'll of course start by looking for an inductive invariant, as we often do. And when we talk about the inductive invariant for a parameterized program, we mean one invariant which is inductive for any number of threads n again, right? So again, we have this challenge that we want to cover any number of threads. So here, this means this invariant must talk about the local states of an unbounded number of threads, because we don't know the number n, and that means we have an unbounded number of local variables. So to make that somehow tractable, one often looks at a specific kind of invariance, namely thread modular invariance. Those are simply invariants that start by quantifying over all thread IDs, so for all thread IDs from 1 to n. And then we have an assertion here at the end that talks only about the local variables of the thread instance I, the global variables, and possibly the location of the thread instance. And through this quantification, we can talk about these unboundedly many variables. And that's very nice and intuitive. The only problem is, in general, that's incomplete. We will find programs for which no thread modular invariant exists, even though they are correct. There is a standard solution for that in the literature, and that is to introduce some ghost state. So we're going to introduce some fresh ghost variables into the program that are updated at certain points, but they're not actually used by the main computation. We only use them in the invariant to relate them to the actual program variables, and typically we use them to record some information about the computation that has happened. This is very nice. It gives us a complete method, but for automated verification, we still have some challenges. Namely that, what kind of ghost variables could we look at? We could design them ourselves, tailored to the program and property we want to prove, but if you're an engineer, verification engineer, that's nice. If we want to automatically do this, this is very difficult to synthesize. There are approaches for it, but it's still a big challenge. There are some canonical definitions, so a history variable would record basically every step of the computation. But if you want to express something meaningful about the history, you very quickly end up with some undecidable logic, and then for automated verification, that's again a problem. Or you could look at the local state of some other threads. You could represent that through some ghost variables. If you had only a fixed number of threads, that would already be complete. But in the case that you have an unbounded number of threads, as long as you look only at finitely many other threads, you're still incomplete. So this picture is quite unsatisfying for automated verification. We still can't prove many programs. And this we'll see in our example even. Right? So even though this was a very simple example, let's look at all the traces that this program could execute. Well, it's the union over all the traces of all the different instances for different numbers of threads. And these traces look very different, right? So here we have different colors, meaning different thread instances, and we have wild interleavings between them. There are some increments by the first thread in yellow, but in the middle there could be some increment by the second thread in green. There could appear a third thread that increments and only decrements much, much later, and so on. You have a lot of possibilities, as you can imagine. And the result of this is that it's very difficult to give a proof for this. In fact, there is no thread modular proof for this program if you don't have ghost state. Right? Basically, the problem is you want to say something about x, this variable that's incremented and decremented, but unless you know what all the other threads have done, whether they have incremented or decremented or both, you can't say anything meaningful. And yeah, this is where our solution comes in. We are going to use commutativity. So I'm just going to very quickly reiterate what commutativity means. This is this observation that for many statements of different threads, the order in which you execute them doesn't actually matter. And then we say these statements commute. So for instance, in our example, whether I first increment thread x in thread 1 and then decrement it in thread 2, or I do it in the opposite order, doesn't make a difference. The effect in both cases is that x in the end has the same value as in the beginning. And therefore, we can say that traces, this gives us an equivalence between program traces, going back to Marcinkiewicz, where we say traces are equivalent if they only differ in the order of commuting statements. The key property that is maintained by this commutativity is that if one trace is correct, all the equivalent traces that only differ in this order of commuting statements are also correct. And this enables this key proof rule that you can take a reduction, which is a subset of traces which has one representative for each equivalence class. And if you have shown correctness of the reduction using some invariant, then you can implicitly conclude that the entire program is correct, even if your invariant is not actually inductive for the entire program. And let's do that in our example. right? So what would a reduction of this program that we saw look like? As we saw in the previous slide, the increments and decrements commute freely against each other. 2 increments and 2 decrements also commute against each other. So we are very free in choosing our representatives. And one thing that we could do is choose only those representatives in which we first take all statements of the first thread in yellow, and only after the first thread has no more statements in our trace, we start taking some statements of the second thread in green, and if there's a third thread, it only starts its computation after the second thread has finished, and so on. So in this particular example, we in fact have basically a sequential program where we order all the threads one after the other. This isn't always the case that it's the sequential program, but the technique works in other cases as well. Now, what's the advantage of this? Well, now we can give a much, much simpler invariant. In fact, we can simply say that the invariant is, for all thread IDs, it holds that if the thread I is currently in its initial location, which was L-, then x is greater or equal to 0. This holds initially, so that's fine. Whereas if the thread is currently in the location L+, it has just executed the increment, then x is greater or equal to 1. And this was an inductive already for the previous program, but now this was an invariant of the original program, but now it's inductive, because if we're in L+, previously some other thread could decrement, and then we no longer know that x is greater or equal to 1. But now the only thing that can happen when we're in L+ is that either the thread I decrements, so we move to L- and x is greater or equal to 0, or if another thread now makes a step, it must be its very first step. And then the very first step is an increment, and we still know that x is greater or equal to 1 after the increment. Right, so through this reduction, we had a program with no thread modular proof, and now we have this very simple thread modular proof. What a wonderful observation. But how can we actually use that in a verification approach? Well, one first problem that you'll encounter when you want to do this, especially in an automated verification approach, is that you need to somehow represent this reduction. Right? Here it was an infinite set of traces. We were going to need some finite representation. And a very nice observation that we had is that you can actually represent your reduction again as a parameterized program. This is a bit surprising because the traces that we saw here, they look much more nicely ordered and not as chaotic as the traces of a parameterized program. But if we manage to do this, it has a big advantage, because now we can compute this reduction, represent it as a parameterized program, and any verification technique for parameterized programs can be applied on the result. The verification doesn't actually have to know about commutativity. I'll not show you the details, they are in the paper. We do this through a transformation of the thread template, so we're going to add some new variables to it and instrument the code. And the result is that in this instrumented program, the execution of any trace that would not be in the reduction will at some point block. Some guard will be violated, the guard uses the new variables, and therefore this trace cannot continue to execute. Let's make this practical. We, as a proof of concept, applied this using the verification technique of thread modular verification at many levels. This is a technique from POPL'17 for parameterized programs, and this technique has no idea about commutativity. It works through a translation to constrained horn clauses. We applied this on 19 benchmarks, parameterized programs, all of them correct, that we collected from the literature and added some custom ones. And I'll just give you the headline results. For the original programs, 4 of them could be proven with this technique. In 11 cases, the constrained horn clause solver actually determined that no thread modular proof exists. And in 4 cases, it timed out. With the reduced programs, we can now prove 14 of them, so a significant increase in the expressivity. In none of our benchmarks, we actually determined that no thread modular proof exists. And with that, I'll come to the conclusion. So just to summarize the contributions, we extended commutativity-based reductions to parameterized programs through an encoding of the reductions as parameterized programs by transforming the thread template. In the paper, you'll also find a discussion of different reductions, different choices of representatives for a program. This is important because different reductions often enable different simplifications, so you want a lot of choice here. We then characterize in more detail the kind of ghost state simplification that you can and cannot achieve through this. For that, we use the framework of Ashcroft invariants. So these are thread modular proof where you fix as ghost state that you look at a bounded number of other threads. And that allows you to nicely characterize the simplification. We applied this in thread modular verification at many levels. And because this translation to constrained horn clauses, with the reduction, it gains a lot of expressivity, but you have some performance issues. And we showed that through a kind of symmetry reduction on this encoding, you can significantly improve the performance of this, of the CHC solvers on the translation. And with that, I am finished, and I would be happy to answer your questions.
Thank you very much. Let's get to the questions immediately.
Thank you for the very interesting talk. I had a question about the commutativity relation. Thinking about fixed size integers, for example, when you have 32 bits, and it's still true that you can swap plus and minus operation because you could reach integer overflow error. So did you take into consideration these kinds of memory models, these kind of situations?
Yeah, so we take this into account. In some cases, you could still convert this, right? If your integers wrap around nicely, then plus and minus still commute. In our implementation, we encode this as an SMT formula, and we ask an SMT solver to determine if things commute or not.
Okay, okay, makes sense. Okay. Thank you.
Hello. So thank you for the nice talk. So I have a very technical question, which is, I guess you're again doing the same tree automata LTA business under the hood for reductions. What happens to the alphabet? I mean, when you have infinitely many threads, then the alphabet becomes, so how do you encode this?
So here we are not directly working with the automata. We're really applying the transformation on the thread template, on the code, so to speak, and then we are translating this to constrained horn clauses. And then it depends up to the constrained horn clause solver how that is solved. So we're not working.
So you're not looking for all possible reductions?
No, here we're fixing a reduction, right?
Okay.
So we have a parameter of our construction, these pairwise preference orders gives you different reductions, but in one verification run, we fix the reduction.
Thank you.
Thank you.
Thank you. That's a really elegant proof. The example you've given as motivation is kind of one that seems to fit nicely with kind of counter abstraction. So are all the ones that you've got to work better here ones that fit with counter abstraction, or is there sort of something else as a good example?
Yeah, that's a nice observation. In this example, indeed, you might just do it with a counter, but this is not always the case. So we have a motivating example in the paper where you're talking about some kind of queue of messages, and that you cannot capture with a counter, but you can simplify the proof with this technique.
Another one here.
Just a very quick question. I was wondering, like, I guess your reduction doesn't really depend on the data types, right? I mean, you have like, by some chance you have integers here, but I guess if you talk about CHC, then you can go to any kind of local whatever data types. No?
Yeah, yeah. In principle, that should work similarly.
We have got 2 minutes, so other questions? I have got one. I'm not clear. Can you the threads have loop inside them, and can you have different threads rather than many copies of the same thread?
We can have loops, right? We're looking for an inductive invariant, and that would, if we find one, we can prove that the program is correct no matter the number of iterations. So that works. In our tool, we also support a number of different templates. So we have a slide extension where you can have a finite number of templates, and you can also have some threads that you only instantiate once if you want a server and an unbounded number of clients, for instance.
Last question, and please swap the laptop, but don't take the microphone yet.
if I saw correctly, you have one example in which you timed out, one more example that you timed out, right? Do you have any insight to why that happened?
Yeah, that's actually a good observation. It turns out this constrained horn clause encoding with all the additional variables that you add, it doesn't always make the solvers faster. So there's actually one program that we can prove without the reduction, and then there also should exist a proof with the reduction, but the constrained horn clause solver just gets confused by the extra variables and times out.
Thank you, Dominic. So we'll finish, we started the day with Azade's talk, and we will finish with Azade's talk, and she will be answering some of the questions that she left open this morning, coarse equivalences for causal concurrency.
Okay, yes, me again. This is joint work with Umang, and probably after this he will have more energy to answer the questions than I do. But let me make sure that this is connected, because it's not reacting yet. Anyway, if not, I'll just use this. So this story starts with focus on the concept of equivalence relations on program runs. And you heard me talk about things, you heard other people talk about things. I wanted to kind of pay attention to this definition for a second, that because we are in a particular context of runtime monitoring, what we care about out of an equivalence relation is soundness, is that whenever we take a run, any other run that is equivalent to it is also a run of the same program, right? So it's basically, I've seen a run, all the other ones that I'm declaring to be equivalent to them, I can also infer them to be the runs of the program. So this is soundness. Then once I have a sound equivalence relation, I can define the core problem that we are studying in this paper, which is called the problem of causal concurrency, or the dual causal orderedness. So you have a set of equivalent runs. If two actions that appear in all these runs always appear in the same order, it means that their order matters according to that equivalence. So we call them causally ordered. But if it's okay that in an equivalent run the order of the two actions change, then we call them concurrent. So what we did in this problem is study the decision problem for causal concurrency or causal orderedness. So the decision problem basically picks two actions and asks, can we declare them ordered or concurrent? And this is very relevant to runtime monitoring. I'll give you just one example, but there are others in which if we pick two accesses to shared variables, that at least one of them is a write, and we know that they're causally concurrent, we have found ourselves an actual data race in that program run. So it's kind of like the core decision problem that would let me check for data races. And then there are other examples. First thing that we did is we took one of the most famous kind of notions of equivalence from the literature, which is called the reads-from equivalence. And to define it, we have to focus on a particular alphabet of actions now. So imagine reads and writes to shared variables and thread IDs appearing in individual actions. And then reads from equivalence declares two runs equivalent if, first, the actions from the same thread that appear in two runs appear in the same order, so you cannot reorder within a thread. And then the second thing is every read has a most recent write, so it reads the value from that write, and that cannot change from one equivalent run to the other. So if you have satisfied these two things, if you think about it for a second, you will see that if one run is a run of a concurrent program, then any other equivalent run by this notion would be a run of an equivalent program. And this one happens to be sound, but also the coarsest equivalence relation that is sound. So beyond this, at least with this much information in the alphabet, we cannot have soundness, anything looser than this. So we studied the decision problem of causal concurrency and causal orderedness under this equivalence, and it turned out to be hard. The core hardness is that if you want to do a streaming algorithm, you cannot do it in constant space. You have to have at least a space proportional to the length of the execution. There are a bunch of other kind of hardness issues that are in the paper. I'm not going to go over them because I want to spend the rest of the talk talking about this particular one, which is the key one. So if you have this sort of hardness and you're dealing with really, really large logs of systems in which you're looking for violations, you're in trouble because your monitor has to basically have storage space proportional to lengths of the runs, which are millions and sometimes billions of events. So we don't want to do that. We want something better. And if you forget about reads from equivalence and ask yourself, okay, that coarse equivalence bad, what about other equivalences? Can this problem become simpler in those cases? Then there is a classic notion, which I talked about already today, that if you have a commutativity relation, it induces an equivalence relation automatically on program runs. And there is a commutativity relation on the same kind of alphabet of actions that then would be sound. So I would not let you reorder or swap things that belong to the same thread. So this way you will preserve the order of things in the same thread. And I will not let you reorder things that access the same shared variable and at least one of them is right. And this would preserve the most recent write before any read. So in some sense, I can defer to the soundness of reads from equivalence and say, anytime you make any of these swaps, you will remain sound. The runs will remain equivalent, and you can infer them to be the runs of the same program. Now, it's sort of a folklore knowledge, but we kind of give the description anyway in the paper because there is no precise citation for it, that under this equivalence, the causal orderedness or concurrency can actually be monitored using a constant space algorithm. So all of a sudden, things are much better. You don't have to have a space proportional to the length of the run. So then we found ourselves in this kind of in the middle of these two ends. A nice coarse relation, hard kind of complexity, much more tight relation, easy algorithmic result. And we asked ourselves, is there something in the middle? And just to tell you why we care about coarseness is the coarser you are, the more runs would be equivalent to a run, which means you're kind of doing your runtime monitoring or whatever over a much larger predictive set. So you want the more the merrier, basically, here. So, and the answer was yes, there is something in the middle of these two. And the solution came from taking the view that rather than focusing on commutativity of individual actions of your runs, you can actually look at blocks of these actions and talk about their commutativity as well, and arbitrary blocks for that. So for example, if I had marked those two tiny blocks for you, you would see that because that read and that write are non-swappable, under just commutativity of individual actions, you're sort of stuck with this arrangement. You cannot change it. Whereas if I take the blocks as they're marked, because each read is together with its corresponding write, they can kind of move together. And I haven't changed the read-write relationship that I told you I want to preserve. So these things we call grains, these blocks, and the grains don't have to even just belong to the same thread. So you can basically take any sequence of consecutive actions belonging to any number of threads and call it a grain. And then we kind of have a notion of equivalence based on such grains. So the moment we kind of do this view shift, things look easy enough. We say that, OK, up to a homomorphism, you can pretend your grains are your new letters. And then you can use non-determinism that everyone from automatic theory understands how it works to kind of guess all possible choice of grains. And then, as such, you will have basically, you're sort of defaulting yourself back to whatever method was working for individual actions under this sort of commutativity relation. And because you're guessing all choice of grains, you're guessing anyway individual actions as grains as well. You're just now adding more options to it. So you get something strictly better than the baseline. And this one can also be monitored, causal concurrency can be monitored for this in constant space. Except I deceived you a little bit. When I showed you this and I said, oh, those two, the reads are together with the writes, they can move. Yes, that part was correct. But it matters what comes after this. So if after this I have another read, that other read was originally connected to the write on the right. And if I swap the orders, it's going to kind of now match with the write on the left. And this is going to break things, right? So I waved my hands. I didn't really tell you the whole story, but there's a difference between these two scenarios. But if the next action on variable x is a write, I'm good to go. I can swap those things because any other follow-up read is going to match to that write or something later. So this kind of gets us to the point that this sort of context after grains matter. They matter in whether I can soundly actually commute things. So the soundness of the commutativity relation now depends on this context, but it's really not a worry because we can always choose grains, and then based on the choice of grains and our choice of whether we decide to say that they commute or not, we can discharge this sort of conditions on follow-up context and check that our choice in the future is unproblematic. So to kind of show you the big picture again, the same idea, we kind of have those ideas that I mentioned before, but now we can also add non-determinism one more layer to say that I will just guess my commutativity relation. And the moment I made a guess, now I'm committed to make sure that the future is okay with my guess, that context that appears afterwards. And if it's not, I will just abandon this kind of choice. If it is, I will kind of stick with it. And all kind of hand waving works fine, and I will have an actual sound now way of verifying these things. Of course, once this worked out, we got greedy. We said that, okay, here is kind of like a schematic thing in which I really badly want to be able to move those x operations against the other x operations, but this kind of one grain of salt or sand appears in the middle and is stopping me from reordering those two grains because they share a thread, and reordering them would be violating thread orders. So I want to actually be able to pick the grains you see on the right, but the grains on the right are not contiguous anymore. And this kind of got us to this concept of scattered grains. And with the scattered grains, I can kind of tell you the shorter story of, yes, we can handle scattered grains as well, but somehow, as a surprise to us as well, the notion stops to be a kind of purely commutativity-based notion. Because once you kind of have scattered grains like this picture, you can see that my grain G2 is sort of stuck inside my grain G3, right? And talking about these two grains that are sort of entangled to each other and talking about commuting them is a little bit of a nonsense, right? Exactly, this is one example, but exactly for cases like this, rather than make this a notion purely based on commutativity, we sort of build this graph that throws constraints between the grains and says, what grains should be ordered, what parts of what grains should be ordered before the other things, and then we can answer the question of causal orderedness or causal concurrency based on analyzing this graph, which we call a grain graph instead. But of course, I'm jumping over a lot of details which are in the paper. So we make this happen using all the trickeries that I mentioned to you before, with the choices of non-determinism, guessing grains, all of that. But I wanted to, I don't have time to give you the solution, but I wanted to mention the challenges that are there to actually have a constant space algorithm based on this grain graph. So the moment and end arbitrary in the future. So there is this kind of contiguity is out the window. This doesn't immediately kind of sound bad. Then you kind of realize that when you have scattered grains, you can at any point in time have an unbounded number of grains that are open. That means you're in the middle of them. This means that that graph, if you're not careful, is going to have unboundedly many nodes, which is against a constant memory kind of algorithm. And finally, through other grains that come later, you can have these constraints form between grains that have already been in the past, started and finished, and you decide that there is no constraint between them, but some other things happen in the future that are going to indirectly connect them. So one has to be clever about this algorithm, but I'm kind of just giving you the good news that we have tricks that we can resolve all of these issues and have a constant time algorithm for this version as well. Now, I have 2 minutes. I'll finish on a future kind of looking view. You kind of saw me wave my hands and say, we use non-determinism for this, we use non-determinism for that. All of this is fine if you just want to give a theoretical result that this is doable in constant space. But of course, the moment you want to actually implement this, all this non-determinism on the parameter, on all the other parameters that are not the length of the run, for example, the number of shared variables, the number of threads, they become an issue. So if we wanted to really have a serious implementation for this, we really need a way of carefully, cleverly resolve this non-determinism so that the monitor on the constant side of things does not become too heavy. So that's part of the future work. I sort of already mentioned earlier today that this is just kind of one decision problem, causal concurrency for runtime monitoring. There are like tons of other decision problems that are related to testing or verification. It would be nice to see whether something like this or something similar to this would help us with those decision problems, making coarser commutativity applicable to those domains. And finally, it would be kind of nice to see that we have put one foot forward. We have now these grain-based notions. Is there still something further after this before reads from equivalence that can give us even more kind of relaxed equivalences over concurrent programs that we can exploit in all these domains?
Thank you. 5 minutes for questions. And again, a lot of contention.
No, I mean, I just have a stupid question, possibly. So when you say like constant space, do you assume something like the number of possible actions is bounded or something like that?
Because no, that is exactly constant space on the number of actions, so the length of the execution. The ones that I'm not constant on are the number of shared variables and the number of threads. So those are the parameters that I assume to be constant.
Hello, sorry, this can also be silly, and thanks for the talk. I was wondering, it was reminding me of some results, for example, on various equivalents, for example, on the runs of contextual Petri nets and so on. And I was wondering if you had a check if there is any connection with
contextual Petri nets?
Yep.
But in what sense contextual?
Meaning
I haven't heard of the term, that's why I'm asking.
Oh, well, simply meaning that basically you have some kind of asymmetry and then you have to decide causal dependencies, not just based on commutativity, but I mean, analyzing exactly the behavior.
Oh, I see what you mean. So you can really view this as that commutativity that is there. We are kind of trying to expand it from just commutativity of atomic actions to commutativity of groups in some sense, right? To expand this. So if we can figure this out, then maybe we can bring in symmetry and things like that and mix all of this together. But it's just kind of pushing the front on one dimension at the moment.
Thanks.
Other questions and comments? So I have got one in the meantime. You said that something that intrigued me. You said that it is possible to have grains that are closed, but something happens and they are unrelated. So far, something happens in the future makes them related. So I found that very puzzling.
I might have something in this picture already that I can show you. So, I mean, in some sense of the word, if you look, there is a path that goes from G1 to G2. G1 top left to G2 the rightmost, okay? But that path was only closed. I had the G3, G2 connection. I had the G1, G4 connection, but the path was really closed down here. If you think that all these dots are like a million events later, on this execution. I established something between G1 and G2 that were long gone, long over. Down here, like a million events later, when the lowest kind of pink arrow that you see appeared. And this is exactly the problematic thing, right? They're gone. I want to really forget about them, because if I don't have a strategy to forget, then my memory keeps growing. But I need to be able to then say, oh, you know, this arrow. So you need to remember, but you can't remember too much. This is really the balance.
Thank you. Other questions? Comments? Okay, I think we'll ask you afterwards if you have got still the capacity. Thank you very much.
Thank you.